Have a sound? Yeah, good. Very good. It's nice to see people physically here again to this UiO Energy Forum 2021. I think we'll just get started here. And we are very happy that the University of Oslo now has a vice rector for climate, environment, and cross-disciplinarity. And we're even more happy that she's here to open this one-day conference on sustainable energy and the energy and transition. So, Mette Halskov Hansen, she is a professor in China Studies at the Department of Cultural Studies and Oriental Languages, and now also vice rector. She has a lot of experience from interdisciplinary research herself, including air pollution, climate, and so on in China, which is heavily connected to energy, definitely. So she's, perfectly fit to open this conference. I'll just give the word to you, Mette. Go ahead.
Thank you very much, Vebjørn, for the very kind introduction. It's really a pleasure for me to be here today and to open this UiO Energy Forum. It's really difficult to think of a more important research topic in our times than energy, especially if you stay a little bit open-minded and approach it from different academic disciplines and sectors. And first of all, I would like to applaud our strategic program, UiO Energy, led by Vebjørn, for helping us all to doing just so. Because when UiO Energy was first established as a strategic priority area for our university, I know for a fact that many humanities scholars and social scientists, they felt that an energy program, that's maybe not really for us. That's something for the technologists, for the natural scientists, and maybe for the odd political scientist. Not to offend anybody, but that was how many thought. So in the past years, I have honestly been impressed by the ability of UiO Energy to expand its profile and include so many dimensions of how people respond to changes in energy systems, how we can promote fair and just energy transitions, and not least, what fairness and inclusion in such processes actually mean. As Vebjørn mentioned some years back, when I had time to be a humanities scholar, I had the privilege to lead a project in China that was partly supported by UiO Energy. And it involved, among others, a number of chemists and environmental engineers from US, China, and Norway. And some of the interesting findings came from villages in China's richest province. We simply went into people's kitchens. And then we talked to people and we observed what they were doing in their kitchens. And it was interesting for all of us, regardless of academic discipline, to see that people mixed at least 4 kinds of energy in their everyday lives in the kitchens. So in most individual households, for instance, you had coal briquettes. Quickly, you could heat up the whole house. It was cheap. You could just turn on these briquettes. Of course, the walls would be a bit dirty and maybe your lungs, but never mind. You could do that. Then you had a huge traditional stove for burning wood. That was for large parties, the 2-week celebration of New Year, weddings, and so forth. Then you had in the kitchen also a very small rice cooker, because people realized it's so convenient to cook your rice on electricity, but it's too expensive, so you only do it for rice. And then finally, people had like one top gas cooker for the daily use. And this kind of collaborative research triggered a lot of new questions for those of us who were involved. And it just became so obvious that the topic of clean and affordable energy was also about culture and tradition, health and well-being, quality of education, inequality of men and women, and not least inequality between rich and poor. So therefore, I was also very impressed and also very happy, I have to say, when I saw the program for this year's Energy Forum. It reflects very well both the need for collaborations across academic disciplines, but also the need for expanded dialogue and collaboration across different sectors. So between the academia, the industry, the public sector and so forth, not only in Norway, but globally. And this is also one of the things that we now want to achieve with a new university strategy or action plan for climate and environment that is now on the table for our board to hopefully soon approve. I know that many scholars get a little bit tired maybe when hearing that, okay, yet another university strategy. But I'm really optimistic for this one, because it is both quite comprehensive and it's also quite concrete in its ambition. And with this new strategy, we want to unite and integrate relevant climate and environmental work within all of the university's core activities. So that is in a way the key, to include it in core activities, not just add it as something that comes on top of everything. So we want to offer the possibility for all our students to attend research-based classes related to climate, environment, or sustainability. We want to facilitate more interdisciplinary research in this field, and we want to stand out with green solutions and low emissions on our campuses. And UiO Energy obviously plays a very important role in this. So you can say, of course, okay, that's the same in all universities, and I would then add, fortunately so, because this is what we need for the universities. But I'd also like to add that the draft to this strategy, which was, of which Vebjørn was one of the main authors, it has really triggered a surprising amount of debate, not only within our universities, but even in national media. Comments have ranged from suggestions to just throw the whole thing to the garbage, or to be much more ambitious and daring. And I actually know a few other countries where a single sub-strategy from a university has managed to reach such a large audience and get exposure in the largest national media. And since I'm an optimist, I take this as a sign that it matters what we do here. And equally, I think your forum today matters. It's clear from the program, with topics ranging from what energy transitions look like from the perspectives of the industry, to the challenges and opportunities presented by the technology of carbon capture, utilization, and storage. And I also particularly appreciate that students have been given a designated place in the program with a pitching session this afternoon. Our students will bear the brunt of the challenges posed by climate change, and many of them will for sure be part of the driving force of the transition that we need. So as a university, I do think we have a responsibility to help our students excel, and I therefore especially wish all the students good luck with their presentations today. And of course, I also hope that everybody joining the Energy Forum will have an exciting and stimulating day, and I look forward to hear some of the first presentations. Thank you very much for the attention.
Thank you so much, Mette. And as you said, my name is Vebjørn. I'm Vebjørn Bakken. I'm the director of UiO Energy, and that is really a fun job. I think it's one of the most fun jobs at the University of Oslo. And it's been also really interesting to follow this strategy and all the discussion that has arisen from this. So we're very much looking forward to seeing this now through the university board and so on. But as you said, there's actually part of the strategy as well, that we should open up and be in the discussion with society around us, which is why we're very happy to have both many external participants here listening in on the forum, but also presenters, which moves us on to the first talk here today. I'll try to find that here, which is Jim Stian Olsen from Aker Carbon Capture. Jim Stian holds a PhD in mechanical engineering from NTNU, and he's now the Chief Technology Officer at Aker Carbon Capture, which also means that he's part of the Aker system, where I think a lot of exciting things are happening. That's one of the places where there's really things happening in the industry in Norway. So we're very excited to hear about that. That should be ready. And Jim Stian is also a member of the SAB, the Strategic Advisory Board of UiO Energy, which we haven't been able to fully utilize now because we would like to gather the advisory board and so on, but that has been difficult. But we're very happy to have you here at least, Jim Stian. And we know that you have a lot of experience in this intersection between industry, business, and research. And we're looking forward to what you're going to tell us. Go ahead.
Can you hear me with the microphone? Is it working? Or no? It's working? Okay, good. So thank you so much for inviting me to talk here. I think collaboration between industry and universities and academia is important, and I think it can be a powerful tool. Today I'm going to bring maybe a bit more of a industrial perspective into this. We are going to look a little bit on the big picture of what we see as an industrial player, and also being part of an industrial conglomerate, the Aker Group. And then I will focus in on carbon capture, which is what I work on a daily basis. And there's a lot of talk about that, both also in the media, has been with the Breivik project and other things going forward. So let's start with the problem that we're all facing. It's we're emitting approximately 37 billion tons of CO2 every year through human activities. And this is what we need to do something about. This is sorry. This is distributed between industries, power and heat generation, sorry, transportation, and of course the heating of buildings and things like that. And traditionally we see that you start out with energy efficiency, reducing the energy you need to perform certain tasks, and then it's of course shifting to renewables, and then you have some industries where you actually can't solve it by switching to renewables or switching to clean hydrogen, like the cement industry and other hard-to-abate industries, and then you need carbon capture, and that's where we come into play. And then we have to take all of these emissions to reach the Paris Agreement, and we have to be at zero by 2050. And it's quite a formidable task. And it's very, when you look at all the reports and the scenarios that are being built by IPCC, the IEA, they're pointing towards 2050, right? And they put up these, we have to be reduced so much by 2050, and they're also moving towards 2070. And so for the world, it's sort of a staggering scenario to get there by 2050, but it's far away. So it seems a little bit into the future. So the urgency is not necessarily that present in the body. And for the industry, this, of course, has a flip side, a positive upside, because what we see as a clean tech company, and you see with all the hydrogen companies being started and the renewables companies being started, there's a huge opportunity for business development, right? That's what we see. But again, if you point towards 2050 and you say, well, we're going to earn trillions of dollars of making hydrogen plants or carbon capture plants, it's still a sort of a strange scenario to be talking about. So what I wanted to focus a little bit about here today is a little bit more near term, to show you that even the near term task is quite formidable. So when you look at what is going on in the world today versus what we need to do by 2030, that's 8 years from now. We are currently doing quite okay on solar and wind. We're building quite a lot of solar plants and wind power plants these days. Approximately around 100 to 130 gigawatts is being installed every year. The International Energy Agency say that we have to be at 630 and 400 gigawatts on each of those added per year by 2040. So if you look at the wind turbine side, for example, the largest wind turbine that exists today is 16 megawatts. That's 24,000 wind turbines that needs to be built by 2030. And they are 200 meters high, several tons. So you then you're starting to understand that it's a formidable task. We need new solutions for manufacturing these. We need to have a different focus than we've had, for example, in the oil and gas industry, where we build equally large structures, but one-off that is going to earn billions of dollars with a high margin on it. And the margin of these projects is much, much smaller. And then I represent the carbon capture market, or carbon capture technology and carbon capture company. And CCUS is being pointed as a necessary tool to reach the targets for the Paris Agreement, in addition to renewables. And there the story is even more challenging, because today there are approximately 20 plants, large-scale plants operating in the world today. And we're capturing approximately 40 million tons of CO2 every year. This is the numbers from 2020. And then in prospect, I think there are some 80 million or 100 million tons being developed. And IEA points to that we need to capture 1,670 million tons of CO2 in 2030, every year. And we are working now on building a Brevik, the Brevik cement factory outside Porsgrunn, where we're going to do a carbon capture plant that captures 400,000 tons. This is a huge project. It's going to take 3 years to finish. And this means that we need to build around 3,500 or 4,000 of those by 2030. And to put it in another perspective, we need to store this CO2 somewhere. And the first storage project that's going to come online, that's the Northern Lights project outside the west coast of Norway. On the first phase, they're going to capture 1.5 million tons. So you need a little bit more than 1,000 storage projects of that size to store this CO2. And we have to do it within 8 years. So the question we have to ask ourselves, are we moving fast enough? And is it possible to accelerate this? And then if you look a bit back into history, during World War II, not a similar problem, but still the world had a huge problem that they needed to solve. And if you look towards the US, they spent, I believe, $4 trillion on the war effort over 4 years. And during that time, they built 297,000 aircrafts, 17 aircraft carriers. They built 86,000 tanks and over 2 million trucks within 4 years. So they mobilized the entire country. So all the men were out fighting, and all the women went into the factories in the US, and they started building these things. And there's a picture of Lockheed Martin where you had this B-24 plane lining up on a series production, and they built one in every 63 minutes. So it's possible to, if you mobilize, it's possible to do something, but you have to sort of go all in order to do it. But it gives some hope then that it's possible if we all can agree that this is important enough and we want to put the efforts in to do it. But it also says a little bit about what it requires to get there. And I think that was it's interesting to go back and see how that can work. And then what do we need to get there, right? We working in the carbon capture market, we need our customers to have some incentives to buy a capture plant. A capture plant is expensive. It's expensive to operate. It requires a lot of energy. So what is the incentive? Some of this industry we operate in, they are covered by the ETS, and the ETS is the carbon price is rising. I think it had a peak of around 70, and now it's a little bit down again. But the analysts point towards that it's going to reach high hundreds, 120, 40 by 2030. And what we see in our calculations is that if we can go above 100 or 130, 40, then we're at a stage where we can actually make it work financially, and it actually pays off for our customers to install a carbon capture plant. But then you have industries that are not covered by ETS, like waste to energy, waste incineration, for example. They're not covered by this ETS carbon price. So what is their incentive? And they also don't have an opportunity to just stop incinerating waste. So they have to emit the CO2, so they have to do something as well. But it's moving in the right direction. We see the ETS price increased 170% over the last 12 months, which is a significant bump, much faster than any time in history. And then, of course, the other thing that we need to get moving is capital. And during the COP26, there is an alliance that is called the Glasgow Financial Alliance for Net Zero. It has, I think, around 40% of the financial assets in the world. So it constitutes $130 trillion or euros. I don't remember exactly. And they have now committed to adhere to the climate or Paris goals. So they're committed to be net zero by 2050. So then it means that we have that capital available to reach our goals. So in some aspects, it looks like, from our perspective at least, that the industry and the financial players are more progressive and more forward-leaning than the policymakers in terms of taking big steps. And this is, of course, why the Aker Group as well has focusing on this. We see that they have access to capital. They have a history of industrialization. We've been doing industrialization since 1841, so close to 180 years, and we've followed the tides of the society. So we started out with shipbuilding, we've been through hydropower, oil and gas, and now into the energy transition towards renewables and clean tech. So in the summer of 2020, Aker Horizons was established, and the purpose of Aker Horizons is to contribute positively towards the goal of net zero. Two companies were spun out of Aker Solutions. That was the Aker Offshore Wind, which is focusing on floating offshore wind. Aker Carbon Capture, which I represent, which I will share more about in a minute. And then half a year later, they started Aker Clean Hydrogen, who has the goal to realize large hydrogen projects in the world. And then they bought Mainstream Renewable Power, which is a global renewable company who has a significant amount of installed capacity globally in the world. So this is the basis of Aker Horizons, and they're continuing to develop their portfolio with smaller companies and bigger companies all the time. And this is, of course, attractive from a business perspective because the available capital now is very cheap, and that makes it easier to boost and accelerate these processes. So in Aker Carbon Capture, we set ourselves what is an ambitious target. We said that we're gonna secure contracts to capture 10 million tons of CO2 by 2025. And given the numbers I gave earlier, it doesn't look like a lot, but it's 25% of the existing market today that we want to be part of developing in the next 3 years. And who are we? We are a pure play carbon capture company. We only do carbon capture. We don't do hydrogen production, for example. We only work with carbon capture. And this has emerged from a long-term Norwegian partnership. The Aker Group started out in 1996, where we delivered the Sleipner platform. And in the Sleipner platform, they've been storing 1 million tons of CO2 every year since 1996. So we know that storage works. That has been proven over many, many years. And then in the early 2000s, you probably remember there was a lot of talk about having a gas power plant at Mongstad with carbon capture. Then at that time, we started in the Aker Group developing our technology. So a company called Aker Clean Carbon was started around early 2000. And we went into a partnership with NTNU and SINTEF, and we launched a project called Solvit, which was at the time the largest R&D project in Northern Europe, where we over 8 years developed our carbon capture technology together with them. And that has taken us to where we are today. We went through the hype cycle of carbon capture, which then went into a slump, I would say, after around 2010. The company was demobilized, and the core people and technology was moved into Aker Solutions, where it was sort of going on a low heat for some years during some challenging times in the oil and gas industry. But we were able to sort of keep it alive and continue to develop both the technology and engage with the market. And then we saw an upswing in around 2019, and we decided to spin the company off in 2020. So we took with us 20 people from that organization, and then we have now grown it into 70 people and continue to grow. What we developed during that R&D project was a unique HSE-friendly, what we call a solvent to capture CO2, and that's what you see in this bottle here. The focus when we started was, of course, to have an energy-efficient process. It's a very energy-intensive process, so we needed to have a focus on that. But then, because researchers here at the University of Oslo, they were criticizing carbon capture and saying, hey, you can't put this into the environment. There's a lot of harmful substances coming out of capture. Because some of the solvents that are available, you have something called nitrous amines that can be emitted from the process, and these are carcinogenic. So then the fear was, of course, that if we put a carbon capture plant that is going to capture 1 million tons of CO2, what happens when you get a bunch of carcinogenic particles in the local environment? So then we shift our focus from focusing on energy to focusing on HSE instead. So we did a lot of large-scale testing. For example, we had a dome in Spain where we tested emissions and measured particles in the air and everything to make sure that we have a process and a solvent that is not dangerous to the local environment. So we're not helping climate change, but then sacrificing from something else. And this is a very simple sketch of how a post-combustion capture process works. We get the flue gas from a combustion process. It could be a cement factory, it could be hydrogen production, it can be gas to power. And then we take that flue gas into a large tower, what we call an absorber tower. This is usually around 40 meters high, so it's quite a large structure. And then we introduce our chemical solvent at the top of this structure, and that falls down in a counter-current flow to the flue gas and captures the CO2. So, and then you have a solvent that is full of CO2 coming down to the bottom of the absorber stack, and clean flue gas going out of the absorber stack with little or no CO2. And then we pump the solvent into our desorber, where we heat it up to a high temperature, and then we boil off the CO2, which we then compress and sometimes liquefy, depending on how we need to transport it to storage. For example, at the Breivik site, we're going to compress it and liquefy it, and it will be picked up by a ship and then transported to Øygarden, where it's going to be injected into the Northern Lights facility. So this is a highly simplified process. It's just to give you an idea of how this works. In this technology, we have now more than 50,000 operating hours. We have a mobile testing unit, which is a full-fledged carbon capture plant that we can travel around the world with. And we've tested on actually 9 different flue gases, and right now we are in Poland testing from char production down there. So we know that the technology works, and it's a proven technology, and it's the technology that I think will be taking the lead when it comes to carbon capture in the next 10 years, both from us but also from a competitive point of view. What we offer are 3 different plants. The focus is on our big catch solution, which is the larger plants. This is typically around 400,000 tons and above. We're looking at projects in the UK that needs to capture more than 2 million tons of CO2 per year, so it's huge plants. And then we have a smaller unit called Just Catch, which is more standardized and modularized, that can fit the smaller emitters, such as a waste-to-energy plant, for example, and other things like that. And then we have offshore Just Catch, which we can fit onto an FPSO and capture CO2 from a gas turbine there. And we talked about the urgency that we have. One of the challenges we have is how can we accelerate the carbon capture market so we get started sooner. Today, we have I will come back to that, but we have our 2 projects, and they're going to be finished around 2024. And then there's a lot of interest from customers, but they're trying to understand what it is, and then they're trying to understand what can they do. But we don't have any place to store the CO2 today, so how can we make sure that they get started? And also it's expensive for a medium-sized emitter, for example. If you think about a waste-to-energy plant owned by a municipality, to invest several 100 millions or how much they need to do to get the capture plant up and running. So what we're now offering is carbon capture as a service, where we take responsibility for the entire value chain of the CCS, from capture, financing, capture, all the way through to permanent storage with partners. In that sense, we can de-risk the project for our customers and deliver a solution where they pay per ton of CO2 captured, basically. And this, we hope and believe, can help accelerate the market, particularly for these smaller emitters. And the market is for this particular solution is quite promising. There are more than 700 emitters just in Europe, in the range between around 100,000 and 200,000 tons of CO2 every year. We also see that there is a lot of storage projects being developed in Europe, 13 storage projects that are either under development or in planning. First of the ones will come online is the Northern Lights, and then there is a lot of focus in the UK, where 2 projects has been approved for track 1 development and financing from the government. So when these come online, then we have the opportunity to actually roll this out at scale, and it makes it very promising and very interesting for us to develop this market. And today we are already started. They are digging at Breivik's Norcem's site in Breivik. The project team has been going full force since January this year, and we're on track to deliver this plant that is going to be operational in 2024, and the first CO2 is going to be delivered at Northern Lights in May 2024. It's 3 years, approximately 2.5 years away, and then we will have the first CO2 capture there. And then we're also starting up now our project with a Just Catch solution, which is for a project in the Netherlands for a company called Twence, and this is a waste incinerator. And here the CO2 is actually going to be used for utilization, and they're going to transport the CO2 to a nearby greenhouse where they grow tulips. So there they have an off-take for the CO2. So there is also always a lot of debate about should you do utilization or should you do storage, and what's the effect of utilization from a climate perspective. And we believe that utilization is probably not a sustainable solution, at least not for the short and medium terms when it comes to climate change, because if you produce if you release it into the greenhouse, CO2 is not going to stay out of the cycle for very long, maybe some months or something like that. So it doesn't really help on the climate change. But what it does is that if you're able to get paid for the CO2, you're able to actually launch the project, and then you get traction on it. And that, in that sense, it's a positive for deploying the technology. So this is my final slide. So what is the focus that we are going to have over the next years, and what focus do we think we need to have in terms of rolling this out? We need to reduce the cost. We've already taken some steps. We delivered the Mongstad test plant back in 2012. That has a capacity of 80,000 tons capture every year. Our Just Catch solution, which can capture 100,000 tons, is approximately 90% cheaper than what Mongstad was, and it's about 90% smaller in footprint. So some steps have been taken there. For a Big Catch solution, we need to reduce the cost with up to 50% in order for it to be a good solution from a financial perspective, and that's what we're working on every day to make that work. And we believe that one thing is to deliver the projects, because you get cost reductions by learning and reusing the solutions you have. And then, of course, we need to work more with standardization and modularization to get standardized products and have that focus as well. And then we believe we need to have a shift of pace in order to make this work. And that goes for what we do, but I think also in the way that we deal with this issue, all the way from the way we do research to the way we implement in technology on an industrial scale. I had a discussion with a colleague of mine at NTNU. We're discussing to do a research project together, and then what we're looking at, if I'm going to go in and do a PhD project on to develop certain technologies or certain solutions, and you follow the traditional path, which is sort of S-curve, where you get all the results at the last year of the PhD study, then I told him I support doing that and educating the people and getting the results, but in terms of doing a collaborative project, it's not moving fast enough. So how can we work together as the scientific community and the industry? How can we work together to start working differently, to be able to not have the answers, but to be able to harvest results from research at an earlier stage, so that we can take those results and make decisions in an industrial sense at an earlier stage? That is something that would be very interesting to explore in some sort of collaborative effort between industry and university. And we're hoping to start that with NTNU, that we have a long-standing relationship, but I'm more than happy to have the same conversation here at the University of Oslo as well. What can we do to move faster and get solutions faster on this topic? And then, of course, we need to work together as both public and private partnerships, and I think that is a global thing. We have to develop good projects, some with incentives, such as we see at the Longship project, the demonstration projects, get things started, but also to have the willingness from the private sector to invest in this and support the initiatives that comes up. That was it from me. Thank you for listening, and yeah.
Thank you so much, Jim Stian, and also for the invitation. I think I'm not going to, sort of find the solution here, but I think the way we are now also employing more researchers at the University of Oslo could partly be the solution to what you're saying here in terms of moving quicker. If there's one or two quick questions to Jim Stian, we can do those now. Yeah, Klaus Magnus, do we have a microphone, actually?
I'll try loud.
Okay, be loud.
Very nice talk.
Thank you.
Did I hear it correctly that you said that the cost level is roughly 100, 120 per ton? And the second question is the technology scalable to the level that you're describing here?
What I said was that according to the analysis that we've done, if the carbon price comes to a level in the future that are around, say, between 100, 150 or 100 and 150 tons per CO2, then we believe that the market can be self-driving. It's not that today, but in the say 5-10 years time, then the market will sort of handle itself, and hopefully we then don't need to invest like we do in Longship and these kind of things, but the incentives are there in the market itself. So. And in terms of the scalability, we believe it is scalable. If we're going to deliver 4,000 Brevik CCS in 8 years, we have to think differently, for sure. We cannot follow the model that we have today. Yeah.
Good. Question about microphone, but we'll bring Jim Stian up here. We'll have another talk from a slightly different perspective, and then both presenters will be back here, and we can have a chat and more questions from the audience as well. But thanks for now, Jim Stian, and you'll get back up here very soon. And then I also forgot to Mette, we have a small gift.
Oh, thank you.
Jim Stian will get his after the discussion. So, yes, and of course it's very happy to hear what you said here about also kind of the role of the university as a critical part here in terms of the worries that were about some of these chemicals used for the capture process. So I think we have Armin from the atmospheric chemistry group here. They were involved in this and have been working on chemistry as well, and kind of verifying that what they are planning is okay. So I guess all they need now is the money. But let's move on. So our next speaker is Tuka Mekitia from Sintef Digital. He holds a PhD from the University of Oslo, from the Center for Technology, Innovation and Culture, working on innovation studies. And you will also give us kind of an overview here of what's going on in the transition and the industrial transition. You've been working in quite a few different sectors, energy, shipping, also CCS, and so on. So
At least
I've-
it's starting, yeah.
Yeah, very good. And as I said, now in Sintef Digital, but the floor is yours, Tuka. Let's see what you would like to comment here. And this should work.
Great, thanks a lot. I think this microphone works as well. So hello everybody, my name is Tuukka Mäkitie. I work at Sintef Digital, Department of Technology Management, and I'm gonna say a few words from on energy transitions from innovation studies perspective, which is a kind of social science perspective on technological change and what it means to industries, companies, and so on. This kind of work is being done in several research centers, such as Intransit, which is hosted here at the University of Oslo, and also FME Entrance, which is hosted by NTNU. They are both, to a large extent, financed by the Research Council of Norway. So to start a bit, what do energy transitions mean for industries? So start from the kind of a bigger picture. So obviously it can have major implications for firms both in the energy sector, but also beyond. So obviously it may lead to growth of new industries, like we just heard from carbon capture, which is a lot of expectations on becoming a new growth industry in terms of renewable energy technologies. They are major industries already in countries like Denmark and Germany and China and so on. Those, of course, may lead to growing demand in existing industries like power producers. When everything becomes electrified, this means more need for electricity usually, and for certain types of power sources like hydropower. Of course, everybody would like to have Norwegian hydropower because it helps with to balance the intermittent production from wind and solar. But it also may lead to decline in some industries. So some industries perhaps may become obsolete, and this of course depends on what do the companies do. But if we assume that the oil and gas demand will decrease, it may have dire times for certain kinds of companies, like drilling companies, for instance. So these energy transitions may play out differently for different kind of companies and industries. So from this kind of innovations studies perspective, if we try to think about how new industries develop, there is a kind of expectation that there is a need for well-performing innovation systems around technologies to lay the groundwork for them. So it's often quite known that these kind of radical new technologies like CCS or renewable energy technologies or novel ways to capture or make use of energy, they are a result of systemic processes unfolding over time, sometimes decades before they become commercial. For instance, wind power took decades before it became self-sufficient without financial support from public sector. And it's this kind of technological innovations are also in the play of several players. So you need research organizations like universities, you need private companies, you need all kinds of other organizations. So these are kind of not a single company or organization will be able to bring these technologies to the commercial market. So we could think about what do we need to develop such technologies, and there is a kind of number of fairly generic kind of processes that are usually necessary. So of course you need new types of knowledge, and universities, they're developing their basic knowledge, companies and their R&D labs taking this basic knowledge to applied knowledge. So and this knowledge kind of has to diffuse within the innovation system in order to make a broader impact. Certainly you need engaged actors, you need incentives and pressures for different actors to become involved in these technologies. For instance, you could think of CCS, you need both universities and other research organizations, companies to be involved. Of course, entrepreneurship is important, and particularly experimentation part. So there's also, with new technologies, there is inherent uncertainty, and often this uncertainty is only you have to learn by doing. So you need entrepreneurs taking the chance to try out certain technologies. It may work out, often it doesn't, but even if it wouldn't work in some company, this whole system as a whole learns something from it. So it reduces the uncertainty of certain technologies. So this kind of experimentation and failures, in a way, is a very important part of innovation. New technologies have to be socially accepted, so users have to want this, and that they serve some kind of broader need in the society. It has to comply with regulations. Often with new technologies, this is not the case. So the regulations have to be adapted. There has to be some kind of fit with norms and culture. Markets, of course, are important, so that companies like carbon capture have certain markets. Somebody who is buying this technology, so it you need this kind of early markets to create some revenue, but also create this kind of learning effects from interaction between users and producers. And of course, resource mobilization is important. You need human capital, you need educated people who have relevant competencies in these technologies. You need, of course, financing, you need financial capital to make investments in infrastructure and whatnot. So that was about how the industries may develop. But that said, it may also mean that some industries may end up in decline. But many kind of established industries, technologies, they are fairly resistant to change in a way. So they're very robust. So if you think about conventional benzene cars, for instance, it's a great product. It performs well. It's reliable. It's are the kind of how people are used to using cars. It's very fitting with that, or it has co-evolved in a way. It fits with all the regulations and so on. So the only problem with benzene cars is that it pollutes. So then this means that this kind of industries that produce this kind of technologies, they may end up in decline or at least they may face pressures of different kinds. So these kind of pressures may emerge from the kind of the economic environment of these companies. So the demand may decrease or change. They may become disruptive technologies that change the rules of the game, so to say. Maybe weakening flows of financing competencies and materials. And of course, there are many examples of this from history. Blockbuster. I'm from Finland, so we know very well the Nokia, kind of what happened to them, at least in terms of phones. So also these kind of pressures may come from what could be called as the social political environment. So these technologies and the industries around them may face negative public legitimacy and support. These examples can be like tobacco or nuclear power, where it's no longer very much public support is disappearing and then leading to pressures and decline. So these kind of pressures, either from the kind of the socio-political side or the economic environment side, may lead to weakening commitment to these old technologies, which may then further lead to disintegration and decline eventually. But of course, companies and industries are capable of reorienting themselves. Like I mentioned, the conventional cars. Many of these major automakers are now very much into electric vehicles, so they are of course capable of surviving over time. But this means that they need to reorient it in one way or another. So a couple of ways to do that is to you can diversify to completely new products and business models. For instance, like there's like Nokia I mentioned. So they started from rubber boots, and then they were at some point producing televisions. I remember at my home we had a Nokia television back in the day. Then of course the phones, and today they are making 5G networks. So you can just survive by moving into new products. But more perhaps easier and common ways to reuse your existing competencies and knowledge in new technologies that are perhaps how you can adapt to the changes necessary. So we have studied a couple of examples on such kind of reorientation topics. So the oil and gas, we studied the oil and gas industry and its engagement in offshore wind power. So of course offshore wind power is not a major industry in Norway today, but it's an interesting case of such reorientation nevertheless. So oil and gas industry firms have been key players in this emerging offshore wind power industry in Norway over the last 15 years. And they have, while this kind of Norway is fairly small in compared to some other countries like Denmark, Netherlands, and Germany, for instance, in terms of market shares, they nevertheless have been a major impact on development of, for instance, floating wind power concepts. For instance, all of these or most of the floating wind power concepts are now pretty much based on oil and gas knowledge. So this kind of semi-submersible floating technologies, spar technologies, and tension leg platforms. So these are kind of very much building on to the knowledge developed originally in oil and gas. And some Norwegian companies are making use of such kind of opportunities to transfer these technologies to new markets. So there's this kind of knowledge development and foundation concept. So this has been, and a lot of R&D money also has been invested in this, but there hasn't really been a domestic market for it. So this has made it quite difficult for many Norwegian companies to really capture a larger share as well, because there's no home market where to get the foot in the door, so to say. And also what we have found out that there's also certain kind of lack of commitment from these players. So here's a graph where this orange reddish curve is the Brent oil price annually in average in US dollars, while the green figure is the level of activities in each year by oil and gas industry firms in offshore wind power. So we can see here that when the oil price dropped after the 2008 financial crisis, the activities in offshore wind power started to grow until oil price reached again its peak in 2011. There's like the engagement to offshore wind power stagnated, but only to shoot up again in 2014 after the oil price dropped in late 2014 again. So there's this kind of a fluctuating commitment to offshore wind power, and which suggests that the offshore wind power has been kind of like has been filling the gaps in the order sheets of some of these companies. So that is in a way very understandable, but it is not necessarily very good for the development of this industry in Norway, as many of the key players are really not there for the full term. And this of course ends in 2016, so the picture has perhaps changed a bit over the last few years. But as a kind of a, historically speaking at least, there's been this kind of transfer of capabilities, competencies from oil and gas to offshore wind power, but the commitment has been somewhat lukewarm. Another case from maritime sector. So there are a number of alternative fuel innovations in Norway here. Many Norwegian companies have been really at the world forefront in developing and adopting alternative maritime fuels already. Liquefied natural gas was some of the companies were first to adopt that, or ship owners were first to adopt it. So there's been a broad interest across the value chain, and of course here, what is notable is that Norway has really a full maritime value chain where there's been many active companies who are engaged in these fuels across the whole value chain, and for the adoption of these fuels, different kind of tendering mechanisms have been very important, and especially in terms of ferries. You have had these kind of tenders asking for zero emission solutions, where we just really help battery electric technologies. And also in offshore segments, operators like Equinor have asked for implementation of zero carbon solutions, usually in hybrid vessels. There's much going on in hydrogen, especially over the last 5 years, and first vessels are coming out. Biogas and biodiesel has been around for a bit longer time, but there's been fairly stalling interest and development and deployment over the years, and when there seems to be fairly little expectations that they would emerge as a very interesting fuel, at least in the Norwegian market, but that remains to be seen. A few words on where are these kind of alternative fuels adopted. We made a survey on Norwegian ship owners. We can see, so here are different colors. So what we have called here as laggards are ship owners with blue, who have said that they will never adopt alternative fuels. Orange is late followers, who will say that they will adopt it, but in more than 5 years. Early followers are who will adopt it in less than 5 years, and early adopters are who have already adopted alternative fuels in one or more vessels. And here we can see that, for instance, offshore supply shoots up pretty remarkably. This has much to do with this tendering agreements. The operators, their customers, expect them to have some kind of alternative energy solutions on board of their vessels. What is perhaps interesting and remarkable is the international cargo, where there's very much, which is often considered as a kind of a hard to abate type of shipping, so deep sea shipping. So there's much interest in Norwegian and expectations among Norwegian ship owners to adopt this in near future. At the other end of the scale is, for instance, coastal shipping, there's a lot of coastal shipping, coastal fishing ship owners in Norway. These kind of very small companies. So here the picture is a bit different. Not much expectations of adopting these fuels. So which has to do with well, they are often small companies and so on. So not quite understandable that. All right. So just to conclude with few words, these energy transitions may cause really fundamental transformations in the energy sector, but also beyond. So some companies will win from this. Some companies may need to reorient, and some, of course, may face some difficult times ahead. In some of these examples, there has been a kind of a lackluster engagement in offshore wind power until now, but more forward-looking value chain in the maritime sector. And what we see is the kind of key to this kind of development of such new industries is a well-functioning innovation system. So you need innovative firms, but also research organization, like was mentioned. This kind of interactions between universities and companies is very, very important. We also need engaged policymakers and, of course, customers. Last word on policy, like was mentioned, Jim Stia was saying this amount of this extent of the challenge ahead. So this may also mean that the kind of the policy making and the incentives set out may have to think in a new way. Like in these two examples I had, we saw that the kind of these early niche markets were an important factor in Norway. In offshore wind power, no home market, while in the maritime sector, strong home market, and you can really see also how the kind of these new technologies are developing and how much they are making an impact to the industries. So you may need to think about this innovation policy from a kind of that it leads to a certain kind of desirable direction, that it is really transformative. So that's all from now. Thanks a lot.
Thank you so much, Tuka. So if there's a quick question for Tuka, we can do that, and then we'll get Jim Stian up here as well. I can't see any hands, but please come up, Jim Stian. So, yeah, I guess you can just stand somewhere here. I was just wondering, what we would like to get some interaction here with the audience, so start thinking about questions. And while you think, I can just start. Because you showed this graph that was sort of 2000-something to 2016. But now we've seen the oil prices have really gone up again.
Yeah.
What has happened with the offshore wind now? Is it a bit more robust and resilient this time, or do you see the same thing where things are just?
Yeah, well, we
diving
haven't
down?
followed it up, so I can't really say based on research myself. But the kind of there's also been what is happening also. What is in offshore wind power? Offshore wind power is becoming more commercial. It is in some places it's no longer dependent on subsidies. So it's also kind of becoming a having some echo. So it's becoming a more attractive opportunity for companies, and at least more expectations that this is self-sufficient or it is commercial projects, so it's not dependent on subsidies. So people have a bit more expectations as this will be like a viable business in the future. And also, like mentioned by Jim Stian, also that there's kind of increasing financing coming to this to offshore wind and this kind of clean technology. So there's also inflow of capital coming to this, and investors are looking for projects. So this is also means that there's kind of financing is becoming more available, and of course you can see it with many oil companies are going to this kind of offshore wind power to diversify their portfolio, and also, but also perhaps to present themselves as more green and so on. So there's a lot of happening. My understanding is that there's still a little bit of that kind of dynamic, but perhaps the game is also changing from that side. But that is a bit based on not of thorough research over the last few years.
Jim Stian, you want to follow up on that?
No, I think that what that graph represents is that a lot of this technology that is being used for offshore wind has been developed by actors that are traditionally in oil and gas, and of course then you get these fluctuations because they focus where the money is. And the difference now is that you have more companies that are focusing only on renewables and offshore wind. You have a company like Ørsted that completely transformed from being an oil and gas company to be a renewable company, for example. And you have companies like Aker Offshore Wind and other similar companies emerging now, having a dedicated focus on renewables, and then they will not switch to oil and gas because the oil and gas price goes up. So I think you will see a difference because of that as well.
Good. So, yeah, good. Let's start here. Oh, okay, sorry.
Hi, thanks for the great presentations. I guess this question's for Jim Stian, but feel free to chime in, Tuka, as well. What are your perspectives on direct air capture? Because I guess even if we are capturing from emissions, the concentration of CO2 is still very high in the atmosphere. Yeah. So how is the technology advancing there?
Yeah, it's a great question. During COP26, direct air capture got a lot of attention, what we're seeing now is that there's a lot of activity, a lot of focus on direct air capture, and I think that direct air capture is going to play a role in this domain. But today it's very expensive, obviously, because the energy requirements that you need to capture the CO2 is very high. So I think it will always be cheaper to capture CO2 from point sources because you have a higher CO2 concentration there. But we see that, for example, in the US, there's a proposal now to increase the 45Q regime to include direct air capture. So then they will put $180 per ton captured in direct air capture. So it's only a question of time. So when the cost and the incentives match, direct air capture becomes a good idea. And then it's a matter of scalability there as well.
Good. I have another question.
Yeah, I have a question, or two questions actually to Jim Stian. So, what you show is that your company is actually focusing on the European or Norwegian market, mostly targeting cement industry and waste to energy. But we all know that the biggest problem is actually the new coal power plants that's coming online in India and China, or the very recent facilities. So, is Aker Carbon Capture targeting this market as well or not? And my second question is, you show that we need to scale this technology up very quickly. And what is you as the CTO, what is the main technological risk you see in this major upscale? And what do you do also to tackle the environmental risks? Because you have mentioned those.
Yeah. No, for the first question, we're currently focusing on Northern Europe and Europe, and that's because here the customers are relatively mature, they're interested, we have good support from the governments and the EU in terms of establishing these projects, if you look at what's happening in the UK, for example. We're also looking towards North America to see if there is, that's traditionally been a good market for carbon capture, although they've been focusing on EOR, which is not something we want necessarily to be associated with, but there is a shift there as well. And then when it comes to coal and Asia Pacific, we've not focused on that region, and we probably won't be focusing on that region, because what you see, they're building new plants now, but there is a shift even in Asia in terms of developing coal power plants as well. So we see some groups, activist investors, for example, buying power plants and shutting them down before their expected lifetime is over. So we believe we will see a decline in coal, so we'll probably not focus on that from our side.
Good. Yeah.
Oh yeah, sorry. For us, the technological risk is. I'm going to give you an example. In the UK, the Energy Agency is putting out a policy where they expect companies like ourselves to disclose the recipe for our chemical solvent, because they talk about public acceptance and being able to have traceability. Of course, if we are forced to do that, then that's a significant risk from a technological point of view. Then we have to change our strategy related to technology development and so forth, because of course we don't want to do that. I think that's one of the primary risks. And then from I think in addition to building the first mega scale capture plant, of course, is an associated risk with that. It's huge process plants that has technical margins in terms of making it work, and we know that the technology works, but then building it and doing the engineering correctly and making everything work on the first couple of projects constitutes some level of risk. But once we get over that hurdle, we believe it's going to work well. And just on the emission part as well, there we believe there is a good solution either inherently in the solvents like we have, or also from a technical point of view, you can use hardware to mitigate that.
Sorry. Yes, Magnus?
A question for Tukka. In your graph showing the adoption of alternative fuels, actually two things. You mentioned briefly that you thought of correlation between the company's size and the willingness to adopt. Do you actually see a correlation there? And what do you propose one could do with it?
Yeah, that's a good question. So yeah, we see a correlation between that. The early adopters are large companies, and the laggards and the late followers are often small companies. So we see this is like a statistically significant correlation here. And this of course have something to be said about what we consider as an adopter here. So this doesn't mean that smaller companies they have fewer vessels as well. So for them, if it's a company that has one or two vessels, the risk and the expense is higher, relatively high compared to their revenue. While then how we understand early adopters here, they can be large companies who maybe have experiment with some of these vessels, some of these fuels in some of their vessels, and they may own 100 vessels, for instance. So for them, it's the risk and the cost is relatively smaller. So yeah, that's a open question. What could be done with it, and what we also saw that many of the smaller companies they have also simply less knowledge and in-house regarding these fuels. So they don't really. This was reported as a higher barrier for them, so that they don't really know much about this, the technologies necessary and how this would affect them as well. So there is something to be perhaps these smaller companies could be help to get into some kind of research projects or build up these competencies in-house. So there are some probable policy measures that could be how this could be supported. Also, simply to how to get support for adoption of some of these fuels. So there could be something to be done there. So for larger companies with more resources, or perhaps even an R&D department or something like that, this is of course a kind of a less of a challenge to adopt something completely new.
Yes, I have a question for Jim Stian. So you said that this carbon capture is quite energy intense. How energy intense is it? So if you have a gas power plant that nets output, let's say a couple of 100 megawatts, how much energy we need to put in that process to scrub it, if you will?
We're talking
Like say percentages.
percentage I don't have in my head, but we have done together with partners looked at what impact it has on gas power plants, and it's not it's not eating up the whole capacity, but of course it has some effect. So it depends. It becomes this game of cost benefit. So if the power price is high, then the impact is huge. But if the carbon price is high, then the impact is less. So it's sort of a balancing it. A couple, some few percent maybe on the total efficiency of the entire plant, I would say.
So you had one final question. We can do one more. I don't see any hands, so I'll yeah.
Just to follow up on this graph from Tukka here, because I'm kind of surprised that there's so much difference between aquaculture and sea fishing, for instance. I mean,
Yeah,
in a way they're in the same line of business, right?
Yeah, I can't comment on that. I simply haven't gone into those specific segments so much, and we don't. There are also not so many respondents from some of these segments. So, for instance, coastal fishing and international cargo, there were a lot of respondents, but from some of these, there's also maybe 10 respondents from some of these segments. So it's also, we don't focus so much on them because we can't really say so much for certain.
Yeah, hi. I just wanted to ask a quick follow-up question related to some of the other questions actually, and what you touched on in the presentation. But you talked about these large companies trying to transition, specifically oil and gas companies trying to transition into offshore wind, for example. Do you think these large companies are well placed to make that transition and win in the game of these emerging new industries? Or do you think smaller, more focused companies that don't have this kind of waning or fluctuating interest that you were talking about, that are just going to focus on that industry, will ultimately win out in this kind of race?
Yeah, that's a good question. So, yeah, you could, there are positives and negatives. So perhaps the positives, like if you think about, for instance, Aker Solutions going to offshore wind power, they are a major large company, massive knowledge on all kinds of maritime or floating technologies and engineering, strong engineering departments and so on. So they have like a, they have plenty of, they are large organizations, they have a large kind of, they're big, they know their, some of the their customers are like Equinor, it's, they know them from oil and gas, and they have, they know their financiers, and so they can, it's perhaps easier for them to get financing for their projects when they have their, in comparison if it would be like a smaller company, then of course it's more difficult to get resources to develop such kind of new technologies. But then again, it depends on the company. I'm not commenting on Aker Solutions here, but more than that. But of course, larger companies may also have this kind of certain kind of path dependence on what they have been doing, and perhaps it's made of, they might be focused on the earlier technologies still. Perhaps they have the mindset is the kind of is what is makes sense in the older technology may not be optimal in the new technology, and maybe there may be some kind of various kinds of path dependence there as well. So while the smaller companies may be able to think fresh, think from a kind of try to do more optimized solutions, and there are both positives and negatives there. So, and we of course don't yet know what is going to happen in, for instance, offshore wind power, which if it will be Aker offshore wind's solution that will win the game in floating wind power, or if it's something else that is perhaps more optimized for any given conditions and so on. So I can't really say if there are positives and negatives.
Very good. So I think that is the end of this session, but I'll make one comment, because in just 1 week, there will be the official opening of what's called Oslo Science City, Norway's first innovation district, which is right around this. The Oslo Science Park will be sort of at the heart of this. I think Mette will be part of this opening down in the City Hall in Oslo. And of course, the main idea behind this innovation district is to get this innovation system kind of, with research, with business, with investors and so on. And I think any advice that you have in terms of getting this to work properly, we will be very happy to hear. I think we'll end the session here, so let's thank the speakers again. We have some small gifts, some energy storage.
Wow, awesome.
And some ecological chocolate.
Great, thank you.
More storage.
Thank you.
I'm not sure if you can put CO2 on it, but you can try. So, I think we need 20 minutes break, stretch your legs and so on. I hope you'll be back after the break. There's some coffee, some refreshments and so on outside. There will be more carbon capture, storage and utilization after the break, and then we have a great program going on further into the day. But please enjoy coffee and short break. So I think we'll start up again. So welcome to the second session here. We are going to dig further into carbon capture, storage, and utilization with two separate sessions here. The first one will be a dual session where we have Rikke Brun here from the Department of Geosciences. She has a PhD from the University of Copenhagen, many years of experience from the oil and gas industry, and she's doing kind of a green shift herself now, moving into CCS instead, and very personally enthusiastic about this, I think. So we're looking forward to hear from you, Rikke. You are part of this FME Center on carbon capture and storage called NCCS, Norwegian CCS Center. Also part of that center, we have Katrin Banet. She's Associate Professor at the Scandinavian Institute of Maritime Law. She's digitally with us today because she was not completely well. So we hope that will work fine with Katrin then on Zoom. Maybe a little bit of challenge with the questions and so on, but we'll see. Hopefully that will be okay. And Rikke is then sporty here and will be the physical presence of this talk. So I can just briefly add that we are streaming this because we have a few people who said that they didn't want to or couldn't come due to the current situation with COVID. So it is being streamed as well, but we didn't want to broadcast that too loud because it's really nice to actually meet here physically and talk to people and so on. So that is the main thing of this forum. So I think I'll just leave the floor to you, Rikke. So please go ahead.
Thank you very much. We've very conveniently started with the conclusion slide. So I might just go back. No? Oh, no.
Sorry about that.
That's all right. No problem. It makes it easier for me, of course, not a problem. But if you wanted to hear the story, then I think we'll start from the beginning. So thank you for your introduction. This is the beginning, yeah? Yeah, it does. All right. Yeah, hi everyone. I'm here to talk about carbon capture and storage, or CCS in short. And I've called the talk Challenges and Opportunities and added that this is from a UiO perspective because I'm gonna say most of the talk will focus on work that is going on here. So I'm going to do a little bit of a step back compared to Jim Stian's talk earlier on to just sort of what is CCS for those of you who might not be so familiar with it. So this picture here, is there a pointer? Yeah. So this here is a Mickey Mouse sketch borrowed from the GEOS, a geological survey of Denmark and Greenland, who's got a sort of a popular science magazine called Geovitten. And I have marked a 1, 2, and 3, which is the carbon capture and storage. So in the principle, it really is quite simple here. One is that we capture the CO2 from where it is emitted at industrial sites. This is typically processes that involve some sort of combustion. So it could be waste incineration, as you heard earlier on. It could be any sort of energy production, like electricity production, which typically is from burning fossil fuels, not so much here in Norway, but in most other places in the world. But there are also some industries that emit carbon dioxide without actually involving fossil fuels. For example, cement production, which is quite a significant share of global CO2 emissions. So that it's a magnitude of different industries. But then the two is once we've captured, once Aker carbon capture has been on the scene, we need to compress the carbon dioxide, which is a gas form when it's emitted, into a liquid, and this is by adding pressure. So it's a high temperature, high pressure phase where we can transport it as a fluid. It makes it take a lot less space and easier to work with in large quanta. So as transportation, it's either it's a pipeline solution, or as we would do it here in Norway as part of Langskip, it's a ship transportation solution. So typically a sort of an LNG type of ship. taking it to a repository. And then 3, the storage part is underground, so we actually pump the CO2 down in Norway under the seabed at a depth and at a place where we've got the right geological conditions for a storage site, where the CO2 is going to be captured underground and stay down there, because we want it to be permanently locked away from the atmosphere. Incidentally, these kind of underground structures are very similar to what we've been extracting oil and gas from for many decades. So we have got a lot of knowledge about how these type of repositories work in Norway and globally, but particularly here in Norway. I think we'll come back to that. So these are, in principle, this is fairly simple and fairly uncontroversial. And as Stian also said, we've actually done it here since 1996, where the Sleipner CO2 repository was taken into use and has been injecting about 1 megaton per year. So that is the first one, is why. The next one is, of course, why do we want to do it? This is also just taking a complete step back, and most of you have seen these kind of curves over here, maybe rather a number of time. This is taken from the US Global Change Research Program, they modified it from an earlier paper, and shows the connection between global average temperature and CO2 concentration in the atmosphere. And as most of you know, CO2 is a natural part of the atmosphere, so it's not poisonous, and we breathe it every day, but it does work as a heat shield in the atmosphere. So there is a certain connection between temperature and concentration of CO2 in the atmosphere. So the graph here shows the average global temperature since more or less pre-industrial times, and then till now, with an average of sort of an average pre-industrial. And as you can see, the blue ones are the years where the global temperature was lower than this average, and then the red ones, the years where it has been above. And as you can see, the above are counting for more and more years as we come closer to our time. And then linked to this, the graph of CO2 concentration, you can see this started rising already at the sort of industrial revolution time, but it's really been accelerated since World War II. And of course, what does it mean, this rising CO2 connection in the atmosphere, which, by the way, is very largely a product of our emissions of particularly fossil fuels for industrial use and for electricity and heat. Well, the thing is, as you know, that it triggers quite rapid changes to temperature, which triggers rapid changes to ecosystems globally. And in that itself, I mean, that's not a new thing. And me as a geologist, we know that this is taking place all the time because fluctuations are natural. But the speed that this is happening means that ultimately we are impacting on their own livability, so to speak, both for ourselves and pretty much for everyone else on the planet. And there's some person with a poetic license has illustrated some of the key type of implications that these kind of changes can have. So all this focus on CO2 as a particular important greenhouse gas is largely accepted that this is a product of our activities. And it's also lately accepted that CCS as capture is necessary to reach our target from the Paris Agreement of limiting the temperature rise to 1.5 degrees. This was also recently reaffirmed by people in the Glasgow summit very recently. So if we look at the CCS capacity, and Jim Stian touched upon it earlier, so he spoiled this figure here, but I think this is quite a nice illustration of what capacity there is for actually capturing and storing CCS at the moment, both globally and in Norway. So this figure here is taken from a report made by NTNU and SINTEF very recently, and they are sourcing their data from IEA Net Zero by 50 roadmap. And these 3 dots here shows the present capacity globally for CCS injection into geological formation and then storing it away of 40 megatons, which I think he said it was about 20 different projects worldwide. So this is the current capacity, and given that our roadmap of capturing everything, so lowering our emissions to 0 by 50, of course both requires that we actually cut down on fossil fuels, that we replace part of this by hydrogen and many other things, and particularly also, I mean, turn our attention to sectors that cannot easily be decarbonified, like cement industry, for example. So the difference in size between what present capacity we have and what we need to have in 2030, which was Jens Stian's figures, and what we need to have by 2050, there's quite an enormous difference. Just as a comparison, Langsheep or the Northern Lights repository, when it comes into use in 2024, the initial capacity will be about 1.5 megaton per year, and they think that they can probably scale up to about 5 megaton per year when fully operational in the cluster. So these things here, they are very small numbers by comparison to what the need is going to be just in 10 years and in 30 years. So we need hundreds of Langsheep or Northern Lights projects in Norway and in the North Sea region. This figure here is made from numbers that the Norwegian Petroleum Directorate has made. They have, of course, done a big scan they've worked with this for a long time, actually, to do a basic mapping of the total storage capacity in Norway for CO2. And their number here is that they think that the total storage capacity on the Norwegian continental shelf is about 80 gigatons of CO2. This number here is equivalent to 10 years of global storage by 2050. And it's equivalent to about 1,000 years of the present day emissions in Norway. So it's quite a significant capacity or possibility that we have here. So I think that we should see this as an opportunity, basically. That's my personal view, and I think that the carbon capture and the politicians being willing to engage in setting Longship in the sea thinks the same thing. So CCS should be thought of as a business opportunity for Norway. This figure here is from the same NTNU and SINTEF report, but they've done a screening of opportunities in the North Sea region just. So looking into renewable industries such as wind, and looking into hydrogen, both blue and green and all the other colors of hydrogen, and looking into CO2 storage. So 40,000 jobs in the North Sea region, that's quite a significant industry. I think that we've got some, here in Norway, I think we've got some competitive advantages for positioning ourselves from a business development point of view to capture or to grab a part of this business. We've got it both because we're very centrally located in the North Sea, which gives us access to a very large market in the EU and the Scandinavian countries. We've got a industrial capacity because we have we've got a big oil industry, and I think they are part of it. They've got a lot of know-how. We've got a supplier industry that are brilliant at marine operations, and they are applicable also for offshore wind, for example. And we've got the know-how, and that know-how is built up through decades of fruitful collaboration between industry and academia. So I think this is quite a unique position, really, for us. Not to bang our own drum too much, I think that UiO is doing a really good job here, and I think that we're really at the forefront of the research part. So partly through UiO Energy here, there's a lot of there's a spectrum of different CCS-related research activities going on here. So there's energy law, which Catherine Burnett is going to talk about in a minute, and there is people who work with capturing technologies, and there's quite a lot of focus on working with CO2 storage aspects, and I will touch upon those a little later. So that's really, it's quite a wide spectrum. A lot of the activities that are going on are focused around NCCS, which is a very large research collaboration, a research center. It's hosted by SINTEF, and it's including the important academia institutions that are working with CCS, so it's NTNU and ourselves, and then there's a large number of industry collaborators, so this is a really big collaboration, and it's taking into account the whole spectrum of everything from capture technologies to transportation, energy systems, and storage. So I think this is a really integrated focus. It's been running for 5 years now, and it's got another 3 to go. So we're sort of in the midway in this, and there's a couple of PhD students that are here that are going to present their pitches later on that are connected to this center. So I think this center is really coming not from Norway. For me, this is the showing the best of Norwegian research academia collaboration, and I think this is anything that Norway does really well and has done really well for a long time. So so I'm quite enthusiastic about this particular center. I'm going to leave the word to Catherine. She's got a couple of slides on energy law. So I'm wondering if you can...
Thank you, Rika. And if you can move... Yeah, that's fine. Thank you very much. Yes, indeed, we are undertaking research at the University of Oslo on CCS in different ways. And what I'm going to talk about is the legal research. I will start by drawing the picture of the legal issues and the legal instruments we are dealing with when we talk about CCS and we work with CCS projects. And I'm going to do that in 3 parts. You see the international part, the European and EEA part, and the Norwegian part. If we start by international law, we do have quite an extensive list of applicable instruments, starting by the UN Framework Convention on Climate Change. And the convention is important because it sets obligations in terms of emissions reduction, but as well obligations for the state parties to undertake mitigation measures that will include CCS in addition to adaptation elements. So CCS is one of the mitigation options that the state parties can undertake in order to meet their obligation, particularly objectives set in Article 2 to the convention. And CCS also helps fulfilling parties' obligations in terms of improvement of sinks and reservoirs. That's also where CO2 storage comes into the picture. Under the Paris Agreement, which falls under the UNFCCC regime, parties must submit a national leader-to-mine contribution that describes mitigation measures that can include the use of CCS, and that's what Norway did. The UNFCCC regime also defines emissions accounting rules for reduction achieved through notably the CCS. So that framework convention sets as well the rule for the accounting of the captured emissions. And that's very important as well to get recognition from the efforts of implementing CCS technologies. In relation to the UNFCCC regime, the Intergovernmental Panel on Climate Change, the IPCC, has several times insisted on the key contribution that CCS technologies can make in terms of target compliance. And you see the graph on the right, which was a follower work from the International Energy Agency after the release of the 2018 IPCC special report on global warming of 1.5 degrees. And that stresses as well, that report, the importance of carbon dioxide removal and negative emissions in all the different illustrative pathways that they identify in the IPCC report. And that confirmed the role of CCS, the crucial role of CCS that was already identified in previous reports, notably in 2005 reports from the IPCC. That report as well stressed a new sense of urgency for the implementation of climate measures and emissions reduction measures, and that reinforced the role of CCS in all those different scenarios. So therefore, it's not only limited as it was at the beginning to the power sector, but it extended to other sectors where it is more difficult to reduce emission, the so-called hard to abate sectors. The European Commission also responded to that call from the IPCC when they released their long-term 2050 climate strategy, a Clean Planet for All, where it explicitly recognized the role of CCS, and it was followed up in the Fit for 55 package. So that's the really important convention around CCS for providing the target, the obligation as a starting point for putting a compliance strategy in place that will include CCS. Then you have other convention, and I will go more quick on that. You have, of course, the UN Convention on the Law of the Sea, since we are primarily talking in Norway about offshore storage of CO2. And that's primarily part 12 to the convention that will be relevant. The convention does not allow or prohibit activities at sea, but it defines certain principles that the parties are bound upon, including environmental protection principles. And because of the similarities between waste dumping activities at sea and CO2 storage, there was as well discussions as to the legality of the CO2 cross-boundary transport and storage activities under international framework. And that's how the London Convention and its London Protocol, as well as the OSPAR Convention, came into the picture and had to be amended to clarify the legal treatment of the permanent storage of CO2 and cross-boundary transport of CO2 for permanent storage. And that has been partly solved in the way that you have an amendment allowing for such cross-boundary transport to the Article 6 to the London Protocol. And it has been subject to temporary implementation based on a bilateral agreement between the parties that want to transport and store the CO2 underground between themselves. But still, the main ratification of the amendment to the protocol is run in parallel. So you have important international ratification processes that are still needed. Also, we have a temporary solution for enabling it. And that's a very important background when you think about the Longship project that also relies on the cross-boundary transport of CO2. Other important elements are related to environmental impact assessment rules in a cross-boundary context, that's ESPO Convention, or more practically the international and European standards that can be used as part of the project. When we look at the European level, the key instrument is the directive from 2009 on the geological storage of CO2. And this is really the main piece of legislation, although we have many other legislation that also are relevant, but this one defines the regime around the environmentally safe geological storage of CO2. in relation to climate change policy. And that directive has 3 elements. It's a permitting regime for the storage of CO2. There are obligations during the operation phase and third-party access to transport facilities. And finally, obligations around the closure, post-closure obligations, and transfer of responsibility for storage sites to the state. So this is a very uncommon framework that is set in the directive. It's focusing on storage, and that means as well that for further implementing CCS project, the member states will need to adopt supplementary legislation, as Norway did, because the directive has been incorporated into the EEA agreement by a decision in 2012, and it entered into force in 2013, and it has been transposed into Norwegian legislation in 2014. So far, the directive has not been amended. It has been assessed as fit for purpose and allowing sufficient flexibility for the member state, and is a bit as the Pandora box. You don't want to open it except if you really need to. And that's been the case with the CCS directive. So this is the main instrument. There is no plan for revising it. But other instruments around it have been amended to reflect the specificities of the CCS project. For example, the EU ETS directive or the MMR regulation related to the measurement and accounting of the emissions. When we look at the national legislation in Norway, we do have almost complete legislation, which is primarily based on the storage legislation, regulation on storage, which defines the different steps for permitting the storage operations, in addition to petroleum regulations and pollution regulations. Recently, we have also 2 white papers from the government, and primarily the Longship white paper, which really sets the strategy around CCS in Norway, which also was completed by the energy white paper from this summer, but most of the elements are in the Longship white paper. Can you move to the next slide, please? So what are we doing when we're talking about CCS legal research at the University of Oslo? Because indeed, you may wonder why lawyers are spending their time on when we look at CCS, and why is CCS legal research important? Well, the first reason is that we do have the technology in place. So Rika talked about the geology, and she's coming back to that. We do have technology, but we see as well that technology is sometimes used throughout a value chain with a set of different technologies indeed. And as I mentioned, it has been extended from only more emission abatement solution for power generation to other type of emission reduction applications in industrial processes, but as well in relation to low carbon hydrogen production. So therefore, the spread of the use of CCS technologies are also developed further. And the fact that we are looking at a set of technologies, a set of actors, means that we need to look at the value chain from capture, transport, and storage. And that's what we are doing as well when we are undertaking legal research. We're looking at the interaction, we're looking at the different obligations along that value chain. And they're also in connection with how the projects are developing. At the beginning, there were more point-to-point CCS projects, where now we are looking more at CCS clusters with even more integration of the value chains, interaction between that. So the second element of scoping and scaling when we look at legal research is that we need to look at different types of instruments at different levels. When we are undertaking legal research, we are primarily interested in the rule of law, and I mean identifying and analyzing the applicable rules as they exist in conventions, legislations, contracts, even soft law. but as well how the legal rules can be improved. And we spent quite a lot of time trying to figure out how we can improve the regimes, how they can be developed to enable not only CCS, but as well to achieve certain objectives in terms of environmental protection and investment protection. So you have many considerations to take care of. That means that we also need to look at both the objectives behind CCS deployment as well as compliance strategy and the role of law in that process. To take a few examples of the type of research we are doing, I put a list here. This is just a short titles of works that have been already done or are ongoing. Of course, we have been looking at, and we continue looking at, the international framework that is applicable to CCS, that enable it, and as well that restrict its application. Another important question that has been raised almost since the beginning is the long-term liability for storage under international framework, but as well under European and national legislation. And they are that also applies along the value chain. Think that there could be a leakage from CO2, who is responsible for it, and who will bear the responsibility for it. But as well, at the end of the chain, when you store the CO2, there are mechanisms for the transfer of long-term liability to the state. We are also looking at the transport phase, and at the beginning, they were mostly talking about pipeline transport of CO2, while if you look at the Longship, you have as well the integration of shipping of CO2, and that's something which is also favored in other CCS clusters in other sea basins. So how do you organize the shipping of CO2? What if there is a leakage along the process, and who is responsible for that? CCS also can enable negative emissions. How can you regulate and recognize the negative emissions achieved? This is something which is still ongoing. And the European Commission has said that they will come forward with some proposals in terms of carbon CO2 reduction certificate scheme. And that's something which is probably coming in the new package in December, but that's something that we will look at closely. In the same connection, the coverage of CCS under the EU ETS is something that some PhD candidates have been working on, and I still continue to work on. That's a very important incentive in developing the CCS projects. And that relates to financing. You need financing from the private sector. What about the taxonomy regulation on sustainable finance? Yes, CCS is recognized. But what about the state financial support? That's an issue of state aid regime. So those are two elements that we're also looking at. How are they recognized? How much can a state or an investor can spend on it? Public procurement rules, reuse of installations in the context of decommissioning, and how the CO2 transport regime can be developed further. That's some examples of the research topic we are looking at the Faculty of Law. Thank you. Back to you, Rika.
Thanks, Katrin. Okay, so I'm going to continue and talk a little bit about what we do at the Geoscience Department with regards to storage. And I've got a couple of examples here, and most of them are relating to NCCS. So the first one here is looking into the Longship or Northern Lights area, and this map here. Oh, sorry, that's quite a long way ahead. Wrong button. So this map here is a map that shows the location of the Northern Lights site, which is the repository for Longship. So Bergen is in here, and the gas plant is here, and then there's a pipeline going out into the offshore area here, and the colors out here, the red blobs here are oil and gas fields. So you might know about the Troll field, which is one of the biggest gas fields in Norway. So that's really situated right outside Bergen. One of the things that you might want to notice in this map, apart from the blobs here, there's a lot. The black ones are wells that are drilled. They're mainly oil and gas exploration wells. And then there is a single well which is drilled in connection to Northern Lights, which is going to be the future first injector. So that's located down here, and we'll come back to that in a minute. The other things that you might want to notice on this map here is these black lines here, and some of them have been highlighted in red. These are major faults where there are planes of offset of the layers underground, and that's really quite important for understand the storage in this area here. So we do two things that are the key things that within NCCS. One is to look at the quantification. Where are the storage? Well, we have 2 minutes. Okay, then I'm going to skip a lot of slides. All right, so 2 examples here. Quantification, looking into where are the storage, the traps that you can store in, where you have a big structure that can hold back the CO2, where you have a reservoir, a porous media that can hold the CO2, and where you have a good lid that is impermeable, so the CO2, which is buoyant, so it weighs less than the water in the pores, otherwise it escapes up and comes back up at seabed, which is what we don't want to happen. So this is a paper by Jonathan Osman, who's a PhD at NCCS, and he's almost finished. This is from a paper that he had accepted in APT very recently, and the map here shows this is a interpretation of a seismic section that goes roughly from the injector, which is this red line here, and then across the troll field and up in this direction here. So what you see here, the yellow, are the major aquifers, so the porous media. These are sandstone layers. This, by the way, is a scale of depth, so this is a kilometer, 2 kilometers under the seabed. So this is quite a compressed picture. So you got 2 sets of major storage units, and the gray things here are the lids, so impermeable shale formations that would stop the CO2 from going up. And then all these black lines here, they are faults, and some of them are, this red fault here is this one up here, so these are major faults, and as you can see, they bend the layers and create structurations. And this is very important for this area here. So these 2 maps down here are surface maps of the interpreted top of this first formation and the second one. So this is the deeper one, and this is the upper one, and this here is the one where CO2 will be first injected as part of the Northern Lights project. The yellow blobs here are the actual closures, so the size of the trap. So this is a way of quantifying traps, mapping, and then seeing how would these traps look like. One thing you want to notice down here is that the site of injector is not inside one of these yellow blobs. If we take the next one here, that's quite an important thing. So this is the same map as you saw before. This here is a close-up of the lower storage unit that you saw before. This is the work of Nora Holton, who's here today, and she's going to tell us much more about it in her pitch a little later on. But essentially, this here is again a surface map of this lower unit, and all the lines here are faults. And one of the key things when you look at faults and storage is to try and see how do the faults behave, because there's 2 things with faults. This is a Mickey Mouse of the 2 things that faults do. Well, they offset the layers, and then that means that you can juxtapose different lithologies across the fault. So you can juxtapose a permeable with an impermeable formation across the fault. And in that case, the CO2 won't migrate through it. But if you have a sand on sand, well, it could just go through. And if the fault offset is big enough, you could juxtapose different sands against each other. The second thing that can happen is that when the fault, as in the movement of the fault, the lithologies are smeared along the fault plane. So if you have clay lithologies and it's smeared along the fault, it actually works up a clay layer along the fault itself, which works as a membrane. And this is important because if that is the case, then it means that the fault is actually impermeable, so then it works as a seal in itself. So these 2 scenarios here are if some of the faults are sealing, if there is juxtaposition, so that you have sand on sand or clay on clay. This is a map of how the faults behave. So when the CO2 is injected down here, it moves up dip, which is up in this direction towards the north. But this fault here, which is very important here, there is actually sand on sand, which means the lower sand is juxtaposed against the upper sand. And if there is no further stopping the CO2, it will go straight into the Troll reservoir and end up in the Troll field. If there is clay smear along these faults here, and this is a measure of the amount of clay smear, so then these major faults that have a lot of offsets have actually worked up a clay smear that could be enough to stop CO2, in which case the CO2 won't go through the fault, it will run up along the fault. This is kind of important to know when you want to set up a monitoring program for where to look for where the CO2 moves. And this is important because we are liable for showing that we know where the CO2 is, because we have a monitoring responsibility going ahead. Since there is a lot of bad timing, I'm going to skip the next. This one will be presented. This is Sean Evans' PhD, will be presented later on today, looking into further storage quantification. There's also even further projects going on ahead. We are, of course, looking in places where we can make a difference, because the key thing is that the emitters are where they are, because they're factories that are built and then retrofitted with capture facilities. Transportation can be costs can be minimized by minimizing the transportation distance. And storage you can find in many places. So we're looking into places where there are shorter distances and synergies with existing things, as for example down in the very southernmost part of the North Sea, where the green sand project is basically literally just across the border in Denmark. So I just want to round up with summarizing that going back and hammering, I think this CCS is an opportunity for Norway as an industry. We've got a large storage capacity, we've got competitive advantages, we've got central location, we know what to do it, we've got the industrial capacity. This know-how is largely developed as a fruitful collaboration between industry and academia. This is a unique type of collaboration, I think, in Norway. I think that there is further research needed, both to actually work up further sites. The geology varies quite a bit, so just from a subsurface point of view, there's differences. So to quantify and de-risk the storage, and to improve the technology, all this is to bring down costs. And then, of course, there, as Katrine mentioned, there is things that are still obstacles, not so much on the technical side, but there are, for example, some legal issues that stops us from importing CO2 from Germany, or things like that. So there is further research that needs to be done in order to really open up an European market and create a large business for this. So thank you.
Thank you. So, sorry for stressing you a little bit. We
I'm
don't want to go too
stressed.
much over time, but I think we can do one or two questions from the audience. And you can also see Katrin. Thank you very much for joining us online, Katrin.
Yeah, hello. My name is Asbjørn Torvanger. I'm from the Cicero Center for International Climate Research. I know this is beyond your topic or discipline, but this is about the workplaces that we can generate by developing carbon capture and storage. Of course, we need visions. We need, in terms of the green transition, in terms of climate challenge. But we also need some realism. So I noted that you mentioned that CCS, and I assume that is both on the capture side, transportation side, and the storage side under the North Sea bed, could create 40,000 workplaces. To me, that is a surprisingly very high number, because we are talking about capital-intensive activities, both in capture, transportation, and storage. So I really suggest that we should do some quality checks on the number. Thanks.
I'll bring that on to Sintef.
Yeah,
Yeah.
Sintef, do you want to come from that? Do you believe in the numbers?
Yeah, I'm citing numbers from a report, and I must admit that even though I've read the report, I have very little concrete insight in how the numbers are actually generated. Of course, I merely take a notice that it seems that there are a general consensus in many places that this could be a big industry.
I think a lot of people feel that it's quite an optimistic number, at least. So I agree that
Possibly.
it
And
could-
it's not for Norway, it's I guess it's for the whole North Sea region. So this is also looking at you'd be competing with the UK and Denmark and Netherlands and so on and so forth.
Yeah. Okay. Final question.
Yeah,
Well-
just not knowing the report, so I'm not going to say about that. But it could be also throughout the value chain, right? I mean, the actual putting that is capital intensive for sure, but developing all these technologies like we earlier heard. So there is all kinds of suppliers needed throughout the value chain. So that is, of course, where the Norwegian companies also have an opportunity.
I don't know how many people are employed in the oil industry today, for example, in Norway. There must be someone knows that. But if you think about how much it takes to run a field, an oil field today, with everything it takes from drilling operations to, which is labor intensive, and to the, as you go along to the daily OPEX, sort of a daily day monitoring and adjusting. It takes quite a lot of people, and these kind of things you'd want to, of course, in an oil field, you want to optimize production, so you're continuously looking at where the oil is flowing from and to, but you would need to do something similar, just again, from my storage perspective, in a CO2 reservoir, because you have a need to continuously monitor where the CO2 is and where it goes. So I think that just on the storage side, that there is definitely, it's not something that just runs itself once you knock the steel into the ground and started the pumps.
Okay, I think we have to move on. So thank you again, Rikke. A bit of chocolate and some energy storage for you as well. We can at least put some carbon-based stuff in it. And thank you, Katrin. Unfortunately, I won't be able to give you any chocolate right here now, but thanks for joining us. So I'll close you off. There, and then moving on. In general, at these energy forums, we like to invite a couple of international researchers, but we didn't dare do that this time. But fortunately, just as I was sort of assembling the program, I got an email from Sami Khan at Simon Fraser University doing a European tour. And he said, is it possible to come to the University of Oslo and give a talk? And I said, yes, perfect. We have the occasion here. So very happy to have you here, Sami. And looking forward to hear your presentation here. You are also doing interdisciplinary work here at Interfaces. You have a PhD from MIT in mechanical engineering and are now assistant professor at the School of Sustainable Energy Engineering at Simon Fraser University. So I'll just leave the floor to you, Simon. Go ahead.
Great. Thank you so much, Fabian. Thank you for this opportunity. As Fabian mentioned, really happy to be here. Was locked up in Canada for a year with COVID's lockdown, so so really happy to come this way and have the opportunity to come to Norway. So my presentation title is a bit of a mouthful, but I promise you I will explain this in detail. But as Fabian mentioned, my main interest in my research group is in interfacial science, and specifically with applications to sustainable energy systems. So my group is called Engineer Interfaces for Sustainable Energy, and we are in beautiful Vancouver in Canada. As Fabian mentioned, I've had the great opportunity to work in academia, the private sector, and public sector in Canada. So I very much agree with the theme of the talks this morning about interdisciplinarity and working between different sectors. My background's in chemical engineering. I did my PhD in mechanical engineering. But I also have a master's in technology and policy, so I still keep an interest in the bigger picture studies as well, and that's a theme that permeates in my research group as well. So speaking about interfaces, where exactly do these interfaces come in sustainable energy systems? So as we're all familiar, the sustainable energy landscape continues to grow with technologies like solar cells, as well as wind, offshore wind technologies, and geothermal systems coming. Now, broadly, if you were to talk about the challenges in these systems, you could have two buckets. You could have a performance challenges that are there for performance, which is how fast are you generating energy, or also how selective are you to certain products that these energy systems are generating, but also challenges with longevity, so corrosion and scale formation, and then reducing the maintenance cycles that would be required for these energy systems. So a lot of these challenges occur at interfaces. So broadly, you can think of an interface as a boundary between two media. So most interestingly, boundaries are between fluids and solids. So you could think of the surface of water as one interface, the interface between a bubble and a liquid as an interface. So at these interfaces, very interesting interactions happen, which are physical as well as chemical reactions. And many times these can cause bottlenecks to performance and longevity in these systems. So this is why we're very interested in our group to engineer these interactions using a toolbox of material science, which includes both surface chemistry as well as surface texturing. So now to give one specific examples, in solar energy systems, which keep coming up, if these are left out for a long time, dust starts to accumulate on these cells. Now in Canada, especially in the north, you would appreciate here as well, ice and frost formation is a major challenge. Now when these start to form on the surface of solar panels, they can inhibit how much light goes into the panel. So this now brings up a multidisciplinary challenge. If you made a surface that is able to resist and stop the dust from sticking, then it may impact the transparency of the light that goes into the solar panel. So these are the kinds of interactions we're interested in studying, which brings in this interdisciplinarity. So similarly, also I'll be talking about CO2 capture and conversion systems as a major focus in my group. So in terms of scientific domains, we are interested in interfacial phenomena and electrochemistry, which are interfacial topics, but then using the knowledge that we gain from these two fields to drive the material science toolbox, which, as I mentioned, can be broadly categorized into coatings and surface chemistry, as well as methods to texture these surfaces. So in terms of the fundamental science, we can bring it down also to wetting, which is hydrophilicity and hydrophobicity. So broadly, surfaces around us can be either hydrophilic or hydrophobic, depending on the contact angle of water on the surface. So on one end, hydrophilic surfaces have a contact angle of less than 90, hydrophobic surfaces greater than 90. And there are examples of hydrophobicity all around us. Actually, I think there was a photo in the brochure for this forum where there was droplets of water on a leaf. So leaves around us tend to be hydrophobic, especially lotus leaves. They're very good at shedding water and keeping themselves dry. Same with the duck. There's a saying that said, like water off the back of a duck. That's because these feathers of the duck are hydrophobic and they're able to keep themselves dry. Now, that what I described was hydrophobicity, which means the contact angle is greater than 90 degrees. But if you texture the surface, and by texturing, if you add micro and nano texture on the surface, then you can amplify the hydrophobicity and you can make the surface super hydrophobic. So in that case, the contact angle of water is greater than 150 degrees. And this is also what the lotus leaf does very well. So if you were to look at the surface of the lotus leaf under a microscope, you would see that there's a combination of these micro nano textures as well as a waxy surface. So this is how it's able to minimize the contact between the water and the solid. And that's how these water droplets now bounce off super hydrophobic surfaces. So this is kind of a prelude to what I'll be talking about, where these surfaces have applications in sustainable energy systems. But you can already see that by using this toolbox of material science, we're able to alter many of these interfacial interactions. So I'll talk about two examples of enhancing the longevity and performance using interfacial engineering. So this was a project that I'd done in my graduate studies to enhance the longevity of condenser systems, which are now being ubiquitously used in geothermal systems where there's a fluid that comes in and then there's heat exchange that's happening. So many challenges occur here because geofluids contain a lot of salts, and the moment they hit an interface where they're going through pipes, there are interesting processes that can happen like scale formation or corrosion. So inhibiting these with robust hydrophobic coatings is a major need, and this is a topic that I'd explored in my graduate studies. So hydrophobic coatings are great for inhibiting these interactions because they minimize the contact between the liquid and the solid. So if you can think of this liquid being a very corrosive electrolyte, then if the area of contact is minimized with a hydrophobic coating, then that's great. But a lot of hydrophobic coatings around us are organic in nature. So a good example is Teflon, so non-stick coating that is applied to cookware. And these coatings are not very robust when it comes to high temperature. So if you can see in this video here, this is a fluorosilane coating, which is organic. Initially, it is showing dropwise condensation, but over time, you can see that it converts into a film condensation. So this is steam that is condensing on the surface. Initially, again, it's hydrophobic, but over time, it's degrading, it becomes hydrophilic. Now, this is a challenge because when you're condensing the steam, you want to maximize the heat transfer coefficient, which means that the resistance to heat transfer should be minimized. So when this kind of film starts to form, the heat transfer performance goes down. So it is essential to quickly shed away this liquid. And there are different ways of doing this. You can apply energy, you can blow away the liquid. But again, we're focusing on the material science toolbox here. So hydrophobic coatings that are robust with temperature are very important. So this is why we studied these ceramics, which are called rare earth oxides. So these are the oxides of the lanthanide series, which have a very peculiar inherent hydrophobicity. So they're able to resist interaction with water. And what we showed is that this thin film of cerium oxide, which is a rare earth oxide, it shows dropwise condensation at accelerated temperature and pressure conditions. But unlike the other video that I showed, even after 100 hours, it was able to show dropwise condensation as well. So you can think of these ceramics as having applications in systems where there's high temperature and pressure, where organic coatings may not be as optimal. So I would refer you to these papers and publications for additional details. I was not able to present due to time, but again, showing how using the materials available to us, we're able to engineer these interactions. So what I showed here was a thin film of cerium oxide that was deposited on a silicon wafer. Now, silicon is very good for a scientific study because it's extremely smooth and you're able to study surface chemistry very well on cerium. But to show that this also works on an industrially relevant material, we also applied a coating to titanium. And we similarly saw that there was dropwise condensation, even the same as cerium, with over 100 hours of dropwise condensation. So going back to the sustainable energy landscape, these hydrophobic coatings can have applications in heat exchangers for geothermal systems, but wherever there is a need for protective coatings. But one interest in our group is, again, solar panels. As I mentioned, the surface of solar panels. If these coatings are applied, then could we make them transparent, but also have them be low surface energy so that they're able to resist interaction with dust and ice as well. So this is where the interdisciplinarity comes in, because as you can appreciate, there's a phase change happening along with surface chemistry and material science. So this is the kind of research that our group is interested in. Okay, so just very quickly moving on to another toolbox we have. So you can think of solid coatings, as I mentioned, which can be applied to surfaces. But these coatings have some challenges, and one major challenge is these so-called pinning sites. So you can think of pinning sites as a region on which water droplet would stick. If you're driving and it's raining outside, you'll see that water droplets, rain droplets sometimes stick to the panel of glass, which you might find peculiar because you would assume that glass windows and glass surfaces are very smooth, but they're still able to arrest droplets of water. That's because if you were to look at these under the microscope, there are many such sites on which drops get arrested. So because of that, even though a surface may be hydrophobic, it may not be ideal to shed the water. So the water may not be able to go away very easily. So that's why instead of solid coatings, we can look at liquid coatings. So by liquid coatings, I mean a thin layer of a hydrophobic liquid, or a liquid that does not like interaction with water, that is very stably held within textures on a surface by capillary forces. Now this is something which nature does very well. So this is a pitcher plant, and if you were to look at this again in the microscope, you would see that there's a textured surface along with a thin layer of oil that is impregnated within the textures. So when an insect goes on top of the texture, it just falls inside, right? So that's kind of an example of a very slippery surface. So these surfaces are called lubricant impregnated surfaces, and on them, as I showed in this video, water droplets are able to shed away. So rather than not just being hydrophobic, it's also good for a slippery application. So in the interest of time, I won't present on a previous study I had done here, which is enhancing corrosion protection using these surfaces. But I'll show a video because it will be more visual if I show it pictorially. So this is the associate publication. But the main message here is that solid coatings have issues with pinning sites, but also there can be defects in solid coatings. So you might have noticed this if you have a non-stick cookware and if you accidentally touched it with a fork or a spoon, and then as soon as there's a crack, then that's where food starts to stick. That's because there's now a defect in the coating, so now liquid can now interact with the underlying surface. So this is a hydrogel here, which as soon as you put it in water, it swells to many times its original size. And then if you were to apply a coating of Teflon, you would think that Teflon is fairly hydrophobic, so it would resist the interaction with water. But if the Teflon coating has even small pinhole sites, then water starts to permeate even within the Teflon, and then as soon as it touches the hydrogel, it starts to swell up. But this is where now adding this liquid layer that I mentioned is able to provide uniform protection. So in the case of this liquid coating that is applied to the hydrogel, there is no influx of the water. And I promise you that video is running. It looks like it's not, but even at that same time scale, we saw that there was no expansion of the hydrogel. So using this philosophy, we studied corrosion protection, and we found that there's a 3 times order of magnitude enhancement in corrosion protection by using these surfaces, and I refer you to that publication for additional details. Okay, great. So in the final part of my talk, now I'll go to the performance bucket, and as we've discussed about carbon capture and storage extensively in this forum, I'll talk about how these surfaces can be used to enhance conversion, capture and conversion of CO2 as well. So as we know, capturing CO2 is a pressing technological challenge, probably one of the most important technological challenges of our times. So there's a growing need to capture CO2 directly from exhaust streams, but also directly from air as well, because the concentrations right now of CO2 in the air are simply too high. So there's an urgent need to sequester this, but we are facing a big technological challenge, which is the dilute concentration of CO2 in the atmosphere. It is a drop in a pond kind of scenario where these very small dilute concentrations are causing such magnifying effects on our planet. So how do we capture the CO2 efficiently is a major technological challenge. And I can represent this by showing this video of CO2 bubbles being bubbled into a lime water solution. So this is an experiment you may have done in high school chemistry. You can see that it takes a lot of time before the solution turns milky. And this is to show that these bubbles only have so much time that they spend in the system. And a lot of bubbles have to be bubbled before the solution is able to react. So we have mass transfer challenges here when it comes to interaction between gases and liquids. And this is where using innovative approaches is important. So as an example, I can like if I gave you a beaker of water and I asked you to evaporate this as soon as possible, if you just left the beaker of water out there for many days, you would see that it would take a lot of time before it evaporates. That's because this is the interface where the evaporation is happening. So in order to hasten this evaporation, you would have to put in energy. So you would have to boil this water. So in that case now, instead of a few days, it would just be a few minutes. But you could also use materials instead of using energy. So if you were to use paper towels and then distribute that volume of the water into individual paper towel sheets, then the mass transfer with paper towels would be enhanced significantly. So you could have many of these sheets of paper towels. If you were to look at the paper towel in the microscope, you would have these kind of features. Now these features are what causes the water to wick into the paper towels. So very interestingly, you can use, again, material science to drive the same mass transfer process rather than energy, and then cause the hastening of this evaporation. So similarly, we design paper towels to capture and absorb CO2 bubbles. So on the left here, you can see that there are surfaces all around us where bubbles don't stick. So these are hydrophilic surfaces, but the reverse of that means that they're gas phobic. So the bubbles are now not interacting. So here on that surface, water is preferentially wetting, but the bubble is bouncing off. So we made this micro nano engineered surface which instead captures the bubble very quickly. So this is again the time scale of 100 milliseconds. So the bubble now comes and gets captured similar to a droplet getting captured in a paper towel. Now these surfaces are superhydrophobic surfaces. So as I mentioned earlier, a superhydrophobic surface resists impact with a water droplet. But the reverse of that is that they actually like gas. So if they hate water, they like gas. And nature does this very well. So the diving bell spider is very intelligent. I think I might have a video. It is able to take a bubble of air along with it when it goes underwater. So underwater, there are a lot of mates that it wants to impress. So bigger the size of the bubble, the more it's able to get mates. But also it's able to use that bubble to breathe underwater. And it's doing that because on the back of the tail, there are these nano micro textured surfaces that are coated with a hydrophobic material. So by that, it's able to capture these bubbles and take it underwater. So similarly, we decided to design these for CO2 capture. So if they're able to capture CO2 bubbles, then by holding the CO2 gas in place, you can enhance the mass transfer between the CO2 and the electrolyte. So in the interest of time, I'll just show again some color videos to show that they're enhancing the local concentration. So this is a color indicator where you can think of blue being less CO2 in the solution and green being more. So in the case of conventional bubbling, when you're bubbling CO2 in the liquid and hoping that it would dissolve very quickly, there's a lot of convection and then the bubbles only have so much residence time. So the entire solution appears blue, which means that there's only so much concentration of CO2 that would be present in the solution. But instead, by bubbling the CO2 on that trap, which, as I said, is akin to a paper towel, then we find that this local concentration in the liquid close to that trap is enhanced. And that's shown by the color here. So while the rest of the solution appears blue, in a very thin liquid region close to that trap, it appears green, which means that more CO2 is dissolving because, again, it is held very close to the trap. So we validated this with pH measurements as well, and I refer you to this publication. And I'll just move on here. So what I showed here was the first part, which is capturing. But then the next one is how do we use this, and could we utilize this to convert? So what we tried was if we put a catalyst in that region very close to this trap where there's a higher concentration of CO2, we hypothesized that there would be more conversion of CO2, which would occur electrocatalytically, but then also more selectivity to CO2 conversion as well. So this is why we studied electrochemical reduction of CO2. And again, in the interest of time, I won't go into details. But the basic philosophy of this method is if you dissolve CO2 in an electrolyte, and then if you use a catalyst like copper, then if you can electrochemically reduce the CO2 into many attractive products. So these products can range from ethylene, which can be used as a fuel, but also it could be used as a monomer for the polymer industry. Or you could use, or you could have liquid products like methanol as well. But you can appreciate that one challenge here is that the electrochemical conversion is happening in an aqueous solution. So in addition to this electrochemical reaction, there is coevolution of hydrogen as well. Now, this is not a bad thing because hydrogen is great, but you want the process to be very selective to CO2 conversion. So what we found is by using, so actually in the past, so these are some papers, we found that there are many advances in catalysts, but a lot of these have constraints with hydrogen evolution as well, in addition to other products as well. So what we found is by using this kind of trapping approach, we're able to enhance the conversion of CO2, but then also selectivity of conversion, which I can show in this slide here. So we found that in this work, by doing the electrocatalytic conversion close to the trap, the hydrogen efficiency is reduced. We generate more attractive products of CO2 conversion and also increase the reaction rate. Okay, great. So again, to summarize, these gas capturing surfaces are an embodiment of my initial point, which I mentioned as interfacial engineering. And then these can be used to capture CO2, but then also they have applications in enhancing the longevity as well. Okay, so I'll conclude by talking about the program I'm in. So as I mentioned, I'm from Canada, and our program is new. It's called the School of Sustainable Energy Engineering, and it is growing. So we have 40 to 50 undergraduate students now, and our graduate student body is growing as well. We have a brand new building, so it's been closed due to COVID, but now slowly we're able to go in, which is great. So these are my graduate students. I'm very privileged to have started my program with 4 amazing graduate students from around the world. And as we've discussed today, collaboration with industry is also very important. So in Canada, we have a program through MyTax, which permits collaboration with industry. So we have some ongoing collaborations with a company that's working in the solar field, a company that's working in the biomass energy field, and again, looking at interfacial challenges there. But we also have collaborations with the National Research Council in Canada, as well as the granting agencies for funding there. Now, in terms of collaboration potentially with University of Oslo, we have a program in Canada, as I mentioned, which is called MyTax. This gives opportunities for Canadian graduate students to come and do internships abroad, and then likewise for PhD students and master's students here to come to Canada for a quick 3 to 4 month internship, maximum about 6 months. So my students, Gahi and Clara, will be going to University of Kansas through this program, and this would be an excellent opportunity for our universities also to collaborate in future. My lab is starting to get populated with equipment, which is awesome. So we're going to have equipment that is catered to thin film deposition, as well as surface science and electrochemistry. We also have a very state-of-the-art materials lab at SFU, which permits micro nanofabrication as well as thin film deposition. Yeah, so this is the main summary from my talk. So overall, in a 1-sentence summary, material science can be harnessed to engineer interfacial interactions, but we are specifically interested in CO2 capture and conversion. And yeah, so I was in while I was in Norway. I don't know if you read in the news, but Vancouver had some very severe floods, and it hits really hard when natural disasters come close to you. So this is a street right outside my home. Luckily, my building was not flooded, but a lot of my friends' buildings were flooded, and unquestionably, it's due to climate change. Our debate should not be on what caused this. It should rather be on how do we mitigate this. So yeah, I'm really happy that I had the opportunity to come to Norway. This was in Tromsø yesterday. We were able to see the northern lights. I'm very happy. I checked off 1 tick mark. So yeah, looking forward to many opportunities to collaborate, and thanks again, Fabian, for the opportunity.
Thank you.
And this is my email and website, so feel free to contact me.
And thank you a lot for covering a lot of interesting material science in a very nice visual way. We're slightly after time here, but we have set aside 1 hour for lunch, so I think we have time for 1 or 2 questions here from the audience. Anyone? I see some possibilities for collaboration, and make sure that you talk to some people here later today, and maybe also get to see some of the facilities. So yeah, Uni.
A very interesting talk, thank you. I was wondering, when you have these sheets where you can concentrate CO2, are those part of the catalyst? And do they influence the catalyst activity also in some way?
That's a great question. So these were not part of the catalyst. They were kept close to the catalyst. And the reason being, as we discussed, when there's hydrophobic materials added to the catalyst, you have surface activity getting impacted. There's also conductivity. So the first step was to show, could it work if it's close to the catalyst? But then now we're very interested in integrating the catalyst as well on the surfaces.
But was this, or are there inorganic materials, or yeah?
So the coating itself is a hydrophobic organic coating on the textured surface. The catalyst was copper, so that's the standard that's used for CO2 conversion.
Yeah. Okay. Thanks.
Good. I don't see any further. Yeah, there's one final question, and then we'll break for lunch.
Sorry.
Are they scalable to the industry level?
Yeah, that's a great question. And there's 2 ways of looking at it. One is that because it's a surface property, you could have as thin as possible a coating. So technically, you could have a 110 material decimated into very thin coatings applied everywhere, and that should be fine, even if it's like a few nanometers thick. Yeah, that's a major challenge. A lot of these coatings are fluorinated, and they're not good for the environment. So an active area that we're looking at is non-fluorinated coatings, which there are not many of right now, but if they are made, then we are very interested in using materials that are earth abundant and readily available. So rare earth oxides, interestingly, are not rare. They're available in the Earth's crust, so cerium oxide is a good alternative.
Good. So I think we'll end there. So thank you again, Sami. Some chocolate for you.
Awesome.
Also some energy storage.
Yes,
I guess I have to check this in with the luggage.
Yeah,
when moving
because I
on.
can carry it on the flight. So thank you.
So let's give him a hand. So it's time for some lunch. It will be right outside here, and then we'll start up again at 1 o'clock with Statkraft as next presenter. So there's no reason to go away. Enjoy lunch, enjoy company, find some people that you haven't met before and discuss a bit. That's part of the reason why we want to gather physically here. And I'll see you back at 1 o'clock. Thank you. Okay, so it's 1 o'clock. Let's get started again for the third session here of the UiO Energy Forum 2021. Hope you had a good lunch, that you had some nice discussions with people that you may not have met before. That is certainly part of what we like to do with these events. We discussed a lot. We had industry, and there was a lot of carbon capture and storage and some utilization before lunch. Now we'll move more to the energy system and I guess to electricity and so on. And we are very happy to have Martin Westermark from Statkraft. Statkraft is a key player in Norway when it comes to the electricity system and the production of renewable energy. And you also have this yearly scenarios and reports trying to predict what will happen in the coming years. So we are, of course, very much looking forward to get your take on what this looks like, because we know a lot of things are going on in Norway and elsewhere. Martin has a system engineering background from Uppsala University, and you said you've been working in Statkraft for about 8 years now. You are an energy analyst. You work in the strategy department, and you have been the project leader for the latest Statkraft report.
Yes,
so you
that's
know
true.
Everything about this report. So please tell us more, Martin.
Yes, I know all the errors that was left in the final publication as well. So yes, thank you for having me. Does the mic work? Yeah, good. Yes, so I work in Statkraft in the strategy department, where we try to have kind of a bird's eye view on the energy system on a global perspective. So as you understand, it's a broad topic that I will try to go through our perspective and how we see positive development going forward, but challenging. Challenging, as I said. Yes.
Let's just try starting it again.
Okay, maybe I just go for the errors and have a bit more.
Let's just try switching it on and off.
Yay.
There. Sorry about that.
No worries. Okay, so backdrop, and I'm sure I don't need to convince any climate skeptics in this room. But there is, of course, urgency in this situation. We had about 50 degrees measured in June in Canada this year. There was a lot of fires, again. A lot of participation in China, in Germany, and elsewhere. And we can also see that, of course, a slower thing, but that the sea level is rising. 20 centimeters doesn't sound much, but it is already causing troubles. And this is now today when the global warming is about 1 degree. So we need to do something, and we need to do something fast. This graph is actually quite unique. It looks very simple. It's just something that grows and grows and grows. What's unique with this graph is that it actually grows in 2020 as well. When we look at a lot of different developments, in almost all energy-related sectors, like oil use, total energy demand, etc., we see the COVID dip. But actually, in wind and solar growth, it's a record again. And you see that at least a tend to exponential growth. And exponential growth is, of course, a good thing when you have limited time. One reason why this is happening so fast is, of course, the enormous cost reduction that we have seen just the latest 10 years. So solar has fallen from, let's say, an average around 350 euros per megawatt, or dollars per megawatt hours, to down to 50 on a normal solar project today. For offshore wind, the fall is not as large, but still large, and as well for onshore wind. So renewable energy is getting a lot cheaper. And more countries are also committed to net zero. We have seen ambitions from both the US, from European Union, from China, that say that they will try and aim for net zero in 2050 and 2060. You can, of course, be say that it's too late and too little, and do you really commit to anything when you say that you should do something in 2050? However, I'm a strong believer in that the targets is actually influencing the way you think and act forward. So I'm not so pessimistic about these targets. I think they are relevant, but they need, of course, to be followed by actions. And it's, of course, different between different countries, how thorough you do the work. I mean, we can see in EU that you also have put quite strong 2030 targets together with a lot of money into it, whereas other countries have a less clear pathway towards the net zero targets. But it is important for the industry and for everyone else that these targets are set. And this creates a strong dynamic. It's much easier for politicians to set high targets, EU CO2 emission targets, when the electricity means to do so is cheaper. And when politicians set targets, it's easier for us as a utility or others to actually put the money into projects, etc. And that drives down cost. So this is kind of the fundamental driver in our low emission scenario, a very important and strong driver. So it's a cooperation and collaboration between politicians and the industry that together drives down, create a good circle and drives down costs. And of course, CO2 emissions. So that's kind of the backdrop for our low emission scenario. Now I will say some words about how we see that future. One thing that we strongly believe in, and I mean we're not the only one, is that power and electricity is one of the main things to decarbonize. So to decarbonize, we need more power. And in our low emission scenario, the power demand is doubling from today to 2050. And that growth is coming from solar and wind, almost alone. And that's even, so in 2050, we have about 2/3 of the global energy, the global power demand covered from wind and solar. If we add hydropower and nuclear, we can say that we have more than 80% emission-free power production in 2050. This is, of course, a power market that is very different from the one today. So the power market needs to be able to handle the large variation in wind inflow and wind and irradiation. We believe that the best ways to do this is international collaboration. It is very important that we not as a country go alone, but that this is something that we need to collaborate with interconnections, with systems that works together. So that's one part of the solution. The other part of the solution, that the demand that is growing and is coming, is to a large extent a flexible demand. EV cars can be charged flexibly. The hydrogen production can be relatively flexible. So that is one kind of key to create and to handle so much intermittency in the system. And there will be a need for a lot of other technical solutions. So this won't be easy, but it is absolutely technically achievable in our view. To the far right here, you see a rotating stabilizer that we are building in the UK to get a better grid stabilization during times with limited inertia in the grid in UK. So when the CCGTs and gas engines isn't running, there needs to be something, and this is one of the solutions. So with that, I want to say that, and this is not, of course, the only one, there will be a lot of need for grid enforcement and technical solutions to challenging problems, but it will be possible. And this clean power is used to decarbonize other sectors. So we see around 50% increase in industry demand, which is a lot. But percent-wise, of course, it's the transport sectors that go through the kind of the real revolution here, where we see that the personal transport, at least, will be fully electrified to 2050, more or less. You can, of course, always find a niche where it isn't suitable for electricity, where you maybe need to get hydrogen or biofuels, but I mean, the main part of everything will go on electricity. Also some shorter distances, ferries, etc., have the opportunity to go electrical. And then they have the building sector, and there we have around a double in power demand to 2050. But that actually hides something, because we think that heat pumps is important here. So even if we're doubling the power demand going into the sector, you get some free energy from the surroundings with heat pumps. So where does this lead us? Well, our low emission scenario, where we take this kind of positive spiral, as we talked about in the beginning, into account, that goes to around a 2-degree pathway. So you see here we have the low emission scenario, and we have EPPC's scenarios in gray in behind, and kind of their sample space. But we are quite a bit from a 1.5 degrees. So if we really want to limit the global warming as much as possible, there needs to be something more. There needs to be kind of a step change in both target and ambitions and policy to go there. And it is challenging. It's more and more challenging. The more carbon you're taking out from the system, the more harder it is to take the last part, of course. But as we see it, one of the solutions is clean hydrogen, which I've called the last chapter in our low emissions report this year, fueling the race to net zero. So when you have electrified a lot, there are sectors left which need something else. And there is, of course, opportunities. We have talked about this during the morning. That's one thing, and we believe it will be needed. We also believe hydrogen. And we're starting to see, to some extent at least, the same spiral here going. We have more and more countries and that is setting hydrogen strategies, trying to get this industry rolling by themselves. We also see that the cost of electrolyzers is falling, and that together with the cost fall in wind and solar is, of course, creating a doubling effect. So on the left-hand side, you see our projections on what will the cost of green hydrogen cost in the future. And we say that the blue hydrogen will also be part of this. So we, at least as a company, see a mix of a blue and green hydrogen going forward, depending on how good gas resources countries has, where the industry lies, etc., etc. And what will we use this hydrogen for? Well, we don't think too much about bringing the hydrogen back to the power sector. It is a large efficiency loss if you first generate power and then splitting hydrogen, CO2, when splitting water molecules to get hydrogen and then back again to power. These losses are large, and you really need that only maybe kind of in the Dunkelflaute, as they call it in Germany, kind of a cold winter week. Buildings, we also think that electricity is a better solution than hydrogen to heat, comfort heating. But then there are two sectors that is really demanding to decarbonize with power, and that is the transport sector, and not personal transport. We can drive electrical cars, but shipping is hard, aviation is hard. And then we have the industry sector. Like ammonia, etc., is impossible to electrify to decarbonize by electrification. They will need hydrogen as an input fuel, as a feedstock. And how will this green hydrogen then be created? So we have looked at the different opportunities to create green hydrogen from electricity. And what we see is that there are mainly two options in Europe that is relevant. One is to have some kind of seasonal storage. So you are able to create the hydrogen during the summer where the sun is shining, and then have a steady demand, so you can have a large utilization on your factories. And that's one solution. The other solution in Europe is to have hydrogen production in countries where there actually is some solar during the winter, like southern Italy, and then exporting through pipelines, converting natural gas pipelines to hydrogen pipelines. That's also a viable solution. Probably cheaper storage cost, but higher transport cost. More expensive is to try to rely on only a short-term storage in Germany. And the reason for this is mainly that there will be, in the future, as we see it at least, with the falling cost of PVs, that there will be a large spread between summer and winter prices. So the power will be cheap in summer and expensive in winter. And if you can't store it, hydrogen, during the whole season, it will get more expensive. There have also been talks, I know, that you should try to ship hydrogen from Chile to Europe, or from South Africa or somewhere else, which has summer when we have winter. It sounds like an attractive solution, but when we look at the conversion cost, because it's hard to transport hydrogen, so when you look at conversion cost to ammonia and then back to hydrogen again, we see that it gets expensive and quite large losses as well. As an analyst, I'm also, of course, interested in how is the dynamics here between, and the interplay between the hydrogen production and the power production. And it is complex, which is, of course, fun when you're an analyst and trying to understand the world, but it's a bit hard to go in all of the details. But three main things that we see is shown on this slide. So the most simple one is, of course, when you have hydrogen production, you get a higher power demand. And that is simple and well. What we also see, and is quite interesting, I think, is that we also see a relationship between, okay, what's the optimal size of hydrogen storage and how much intermittency production do we have in a country. So in a country with limited hydropower and a lot of wind and solar, there makes sense to build larger hydrogen storage. And in countries with a lot of hydropower, like Norway, we see that the optimal size of hydrogen storage are smaller, so it plays a less important role in the flexibility, given that we have so much hydropower here in Norway. We also see that there is a relationship between how much hydrogen you need to power and other flexible assets you have in the country. So in a country where you have limited hydropower or other peak power plants, we see that the hydrogen peakers can play a good role for making sure that the light doesn't go out, but they are needed in less extent in other countries, like Norway again. So we should be very happy with our hydropower here. So this is the last slide as a summary. We believe, and this is our low emission scenario, but we believe in it quite firm, and we think that the world gets cleaner and more efficient today, or in 2050 than today. But we need to do something to get here, and here is a telling figure that we need to install 2 times as much solar and wind capacity each year compared to what we did the record year 2020. And that is only to reach a 2-degree target. So if we really want to get to 1.5, it is a shift, as I said in the beginning. It is a significant shift in ambition and pace. And green hydrogen is fueling the race to net zero, but we need quite quick ramp up here as well. So, next.
So in this session, we won't have a discussion at the end, so we'll just take the questions after each presenter here. So it's open for questions. Yes?
Yeah, thanks for a very interesting presentation. I have 2 questions, because all these plans depend on that we are able to scale up green energy production immensely. All this electrification, the green transition and so on. And I really see a lot of challenges there, because we are still dependent on fossil fuels in Europe. We are phasing out in some countries nuclear power. So my question is actually, where can all this green energy come from? I'm not talking about Norway, I'm talking about the European picture. Do we need more nuclear power or what? And also, talking about wind power, we know that this is not immensely popular in many places, and it's very land use demanding. So, and the second part of that question is, we are still dependent on fossil fuels in Europe, in the power sector, in terms of coal and gas. When will we be completely out of the fossil fuels in the power sector in Europe? Thanks.
Thanks for good questions. As I said, this won't be easy. It's not the kind of walk in the park to get to this scenario, and I totally agree. There is a challenge to ramp up, and it is a challenge with getting land use and so on. However, I think this is still the most realistic scenario to decarbonize Europe. I hope that we don't close down too many nuclear plants. I'm a kind of engineer, and as an engineer, I'm always positive to nuclear. I think it's a fantastic technology. However, I have a hard time to see it scaling up and play kind of a really important role in the future. And this is mainly due to the speed. I mean, if we look at this development, yeah, this is 10 years. I mean, Olkiluoto 3 was starting to build in 2005. So that says something about how, at least how I see nuclear. It takes too long to build. And at the same time, we see a dramatic change and shift in the green energy production. I mean, we have, of course, limitation in how fast you can build up wind and solar in our scenario, in our modeling. And we see the larger challenging with especially onshore wind. Solar should be able to it's not the area constraints there. It's rather the getting use of the power during the winter, for example, and that type of challenging with solar.
Yes, thank you. So one thing that has worried me a little bit, I mean, you talk about, let's say, one of the requirements for this, for Europe to be reliant on wind and solar is that we share energy among countries, right? But as we're seeing currently, we see countries limiting export capacity, specifically SVK, for instance. We now also see how Statnett is doing the same. And I'm a bit worried, when we do not have enough wind, what do countries do? Are these kind of semi-nationalistic ideas where you protect your own grid first? Is that something you see as a risk going forward?
Yes, of course. I mean, as I say, we need international collaboration to get this through. And I mean, if Swedes and Norwegian can't collaborate, who can then do that? I mean, we should have both the kind of institutions, etc. So I hope that the fuss between SVK and Statnett is going over relatively quickly. But of course, I mean, it is in a world, and in a nationalistic world, we want to decarbonize in this way at least. That's for sure.
I think we can do at least one more question, if there's anyone.
So what prospects do you see in terms of building integrated solar panels? Is that something that you see as a promising technology, that all kinds of buildings have their own solar production?
Yes, absolutely. I mean, that's one of the reasons why we don't see so many area constraints for solar. It is that you can build it both in relation to agriculture, so you kind of co-locate agriculture and solar, but also integrated in buildings. So it is an important technology. And then, of course, it's not the only solution, because you only have sun during the day. And that is the challenge for solar, but it's not kind of the area or the costs.
And if I can just pick up, you mentioned hydrogen here as part of the solution, but also that it's very expensive to transport this of large distances as hydrogen or as ammonia.
Yeah.
So what you're sort of seeing then is, I guess the conclusion is that you have to have more kind of local production of hydrogen. You should produce it where you need to use it, or is that something that you try to pick up in the scenarios that you are working on?
Yes, so what we see is that it's at least expensive to transport by car or fuel, and it's expensive to transport by ship. So the opportunity is to transport in pipes, and that's not too bad. That's possible, which makes it possible, at least in kind of the long run, to convert the gas grid, parts of the gas grid to a hydrogen grid. We see already that they are trying to do that in the Netherlands and kind of North Germany, creating a hydrogen suitable grid. So I think kind of local in a sense Europe, but not a global market in transporting hydrogen back and forth. Maybe indirectly through ammonia, and that's not when you need the ammonia as the end product. It can be suitable for a kind of global trade, but not if you need the hydrogen.
So a final question from me. You're part of the strategy team here.
Yeah.
But you also know that Statkraft is really one, I guess, the largest producer of renewable energy in Europe, right?
Yes.
So how do you interact with the rest of Statkraft? So what you point towards the future here, they pick up and then use that as information for their investments and so on, or?
Yes, so what we do is, of course, I mean, more detailed work on countries, etc. So we interact with Statkraft, other parts of Statkraft, I would say on a daily basis, both up through the corporate management and back to let the information flow go that way, but also a direct discussion about where to invest, what market conditions do we need, how is the regulatory framework around things. So.
Okay, very good. So thank you again, Martin. I know that you have to run off, but here's some ecological chocolate and
Thank
also
you.
some energy storage where you can store some of your electricity as heat for a while at least. So thanks again. That was really, really nice. I think there were questions here, and we'll pick up some of these things, I think, in the next two talks, where we first touch upon renewable energy and the intermittency, the uncertainty in the production here of solar and wind. And then we'll also discuss the move from fossil to renewables in the final part of this session. So we have dual presentation here. So I see Marianne here, so I guess Marianne will start. Marianne Seiringer is associate professor at the Department for Technology Systems out at Kjeller. And she will be followed by Fred Espen Bent, who is a professor at the Department of Mathematics. And they are both involved in a project that we actually fund, which is one of the what we call thematic research groups, which is a good example of an interdisciplinary project. We have 3 of these that are running now, and all 3 will present, 2 of them in this session and the final one in the next session. So I'll just give the floor to you, Marianne.
Thank you.
Let us know more. What are you working on?
Yeah, Martin, actually, this is taken from Statkraft's website, so it's a project in Norway, and I think I start actually quite very much in line with the previous speaker. So you all know 2021 has really been a year of weather extremes. You have seen record high temperatures in the south of Europe with forest fires, and then also leading to electricity blackouts in some areas because of the combination of forest fires and very large demands for cooling in the south. And actually there was a study in the US recently that looked at this can be the most deadly weather event when you have a deadly climate event, the combination of very high heat periods combined with infrastructure failures due to weather extremes. And this is taken from the last IPCC report, the assessment report 6. You can see globally, you can see everywhere around the world, the globe is warming. And what is really important to know, so we want to keep within 2-degree warming, preferably 1.5 degree. And this is because between 1.5 degree and 2 degrees, really most of these most sensitive ecosystems in the polar regions, permafrost, swamps, coral reefs, there are those tipping points. And at 2-degree warming, many of these will cease to exist. So these are important targets to keep in mind. And as the previous speaker said already, we need to transform our energy system because it accounts for 70% of all greenhouse gas emissions. And we can do that by reducing demand as well as electrification with wind and solar energy. And this is because we know the costs of really dropped dramatically. So we can decide to wait for some technologies to come up in the future. In 2050, maybe BECCS, so biomass with CCS, is going to be available commercially and cost competitive. So if that's happened, it's great. We can maybe reduce warming more, but I think now we have to really bet on the technologies that are currently commercially available. And we develop computer models also as part of this project. We use an energy system model that very much focuses on the power sector and looks at, we use lots of weather data as an input, and then I guess it's quite similar to most of this energy system model, with all this weather input and lots of equations on how plants work. We find the least cost solutions for Europe. And even, I think, this is just taken now from the last, just after Glasgow, the meeting, there was a study that looked at what will actually happen if those promises, and some of them are actually already put into law, but only like the minority of them. What if these promises and commitments that are made until 2050 are going to be actually implemented and realized? Then we still end up in a world that is up to 2.7 degree warmer. So between different studies, say between 1.3 degrees and 2.7 degree warmer. And this would then be if we achieve a net zero carbon economy in Europe by the 2050s. So that will reduce the climate risks, but not eliminate them. So they will be still there. So we have to actually plan for a world that is much warmer than today. When transforming this energy system, I think there's three main uncertainties. So one is socio-political, and we have another project that deals with that, looking into actually, I think this is one of the big barriers. One of you touched already into the question, is how do we actually transform and how do we get the people on board? You can see a march by TNT against wind power, for example. Then another uncertainty is we have seen this dramatic cost decreases for PV, but also for wind. What will happen about other technologies? As I said, this, for example, biomass CCS, negative emission technologies. Are they actually going to be commercially available, and when? And are we going to use them, include them in our models? Or I think better to just look at how we can reach our climate targets with technologies that are currently available and actually cost competitive. And then the third uncertainty, which Spartus is really focusing on, is around this weather and climate uncertainty. And you know there's wind and solar energy. I'm happy that the previous speaker really showed how big of a role they will play in reaching a net zero energy system. So they are variable, spatially, temporally, but also interannual variables. And sometimes we forget that when we model that actually 1 year, you can't just use 1 year of weather from the past and then model based on that. Because here you can see 30 years of capacity factors, and you can see on the top for PV, on the bottom for wind for the UK, and you can see there's huge variations depending on the year you're looking at. So you can have a very windy year and then another year that is less windy. So you need to plan for this variability in the weather when you're modeling how do we get to a net zero carbon energy system. And we really focus in this project on the weather variability. And for that, we use climate data. So we can use this weather data that is actually modeled weather data, but it's the advantage is it's available on a uniform grid around the globe, so 30-kilometer resolution, and we have the hourly data from 1950 to present. So on this 30-kilometer grid, we can actually look at how do we design a highly wind and solar-based energy system that can also withstand the weather variability. And some kind of some results that we did there. This is for Europe. You can see where the model installs wind and solar energy, and the box plot represent these different weather years. So you can see there are some patterns that are quite consistent. So the model likes to, and Fred is going to talk more about this spatially distributing wind technologies. So it likes to take advantage that the wind blows differently in different places. So you can actually take advantage of the weather moving across Europe. So you can see, for example, it places wind in Denmark, Finland, Italy, Norway, Lithuania. So it really places around around the country, and solar, it really likes to place that in the south. But there are some outliers depending on the weather year you're looking. So that shows kind of really that it's important to look at the weather variability across years. And just before I give over to Fred, so this is from the last assessment report. You can see here into this assessment report, there's lots of climate models that go into it. And here it shows except for some regions up here in the north, all climate models agree on temperature increases. You can see more the temperature will increase more in Europe than it will in the south of the world, and more on land than on the sea. So all the models agree on that. But what they don't agree on is for example, how wind will change. You can see here those lined areas. This is where the models have low agreement. So in some models, you can see minus 10% wind. Other models can have plus 10% of wind. So actually, if you and also with wind comes extreme events. So extreme events for the power sector could, for example, strong winds that destroy transmission lines, so infrastructure damages, and that will lead to blackouts, or also problems on generation. So as the previous speaker said, this Dunkelflaute, when you might in the future have more of these events with strong winds, and then again a few weeks with very low winds. So actually we need to not only account for the weather variability of the past, but also explore how the weather might change in the future. So yeah, the project is around designing future net zero energy systems that can withstand weather and climate variability. And with that, I'll lead to you first.
Okay, is the microphone on? Yes. Okay, so I'm the next one following Marianne. Fred Espen Bent is my name, and the project that Marianne talked about is called SPATUS, and Spatial Temporal Uncertainty in Energy Systems. So the acronym is SPATUS, and it's funded by UiO Energy. We're very happy for that. I'm also part of another project that Marianne is leading, Empower, which is a convergence group that also is somehow related to what we are talking about here and what we want to explore in our research. So it's about climate and weather data to assess model uncertainty and future predictions, as Marianne has already told you. And it's about trying to find optimal installation of renewable power plants in order to meet emission targets and demand. So just to give you a little bit of a taster of what we are doing, I'm going to present one paper that we recently worked out, not me and Marianne, but with two colleagues from Sweden. It's about modeling solar irradiation, and this is a trial to depict what is happening. You have the sun up here sending power, essentially, irradiation down to the solar panels. I'm sorry for the very bad drawing here. And in between, there might be some clouds that interrupts this irradiation. And if you look at the blue curve here, you see the daily variations. So this is the peak hour. It's around 12 o'clock in Hamburg, in Germany. So it's the daily variation of irradiation in Hamburg, middle of the city, from 2010 until up to almost today, 2020. And the red curve you see here is somehow a seasonal mean that is extracted from what you can derive from the clear blue sky conditions. So we fitted first a seasonal mean, and we tried then to model the blue variations around the seasonal mean. And the goal was, of course, to try to say something about what is the variation in PV production if you would have a solar power plant at the site of Hamburg. So the power production from PV is more or less proportional to the irradiation, which is I, but it's also proportional in a negative sense with respect to temperature deviations from some mean level. 25 here. But this part we don't worry about now. We are focusing on the irradiation part. And what we found was a rather simple stochastic model for the daily peak. What you see here is, this is the red curve, the S, that's the seasonal mean. Let's call it the seasonal mean. And then you have some random variations in time in this X factor. And the X factor had a 2-day memory effect. So there is a 2-day lagged memory effect in how the sun irradiation in Hamburg is. And this we also found in other locations in Germany, so it's not only Hamburg. So it's a 2-day memory effect, and this is typically in statistics modeled by an AR2, autoregressive of order 2 model. So you see it mathematically here. So this is essentially a linear regression against yesterday and 2 days ago irradiation. In addition, you have some noise, and this noise factor we could separate in between summer and winter, and basically in between no clouds and cloud conditions. So it was a kind of not surprising, but still we could explain that pretty well. So the green curve that you see here is our stochastic model, and the bars is the empirical noise that you can observe here in the winter time and here in the summer time. And they all add up to such a histogram, if you like, where you have a bimodal feature distinguishing essentially what you can expect of some summer irradiation variation between summer and winter. Okay, so what can we do with such a model? I'm going to make a little toy example, and this is related to the intermittency of solar power. As we all know, we don't get solar power at the time we necessarily need it. And the question is, could we reduce production variability by simply distributing the power plants in space? And the answer is, of course, yes, we can, and yes, we should. But how could we do this? And I make a little toy example, and I'm not considering interconnections, I'm not considering variation in demand, I'm only trying to balance as much as possible the production simply by placing plants at different locations. And this is about the spatial uncertainty, and the toy example I'm making is that we have actually 3 cities available. We had more in our study, but we had a model for solar production in Hamburg, in Berlin, and in Munich. And Munich is most south, and the data indicates that the capacity in Munich is better. The capacity factor, how much you can get on average as a production, is better in Munich than in Berlin, which is second best, and Hamburg is somehow worst, so to say. So maybe we should place all our power plants, PV plants in Munich, where it is better, or should we maybe spread them out? And if you look at the figures and the numbers that I'm using here in order to make this toy example are actually taken from the actual data. So what we know, if we take Hamburg as starting point, we know that the mean capacity factor in Berlin is 3% higher, so you get on average 3% more solar power if you install a power plant in Berlin rather than in Hamburg. But also the uncertainty is 1% higher than Hamburg. If you look at Munich, you have 19% higher mean production. So it's quite a lot compared with Hamburg, but you also have a higher uncertainty, 8%, which is a lot higher, a lot of more variations in the solar irradiation. The blue numbers here are the correlations, statistical correlations. So Hamburg and Berlin, they're rather close. They have a correlation of about 0.4, which means they are positively correlated. Sun in Hamburg means sun in Berlin, at least sometimes. Between Hamburg and Munich, there is almost no correlation, so they are almost independent. And Berlin, Munich, you have 0.16, a weaker correlation. And what you find is that actually the installed capacity that reduces variability should spread out like this. So you should have 36% in Hamburg, 34 in Munich, actually more in Hamburg than in Munich,
and 30% in Berlin. That's the optimal allocation that minimizes the variability. So this you gain without any batteries or anything. You minimize the variability simply by spreading out the power plants like this. And the gain here is 25% reduction compared with the strategy where you put all your production in Munich. This is of course a toy example, but it gives you an indication of how much we could balance by simply spreading out. Now, what should we do? Should we spread out as much as possible, or should we maybe concentrate a little bit? So this toy example indicated that we should have something in Hamburg and something in Munich and also something in Berlin. But maybe we should focus more on what happens in the south and kind of distribute there. Well, it turns out that if you look at, well, we focused on Germany, so this is not a universal thing, but if you focus on the correlation, which is the main factor here in how you should spread out, then the correlation decays with distance quite clearly. So the farther away the cities are or the locations are, the less they are correlated, but they are in general positively correlated. So the dream situation would somehow be to have negative correlation here. But you have positive correlation. But what we find is that reduction in variability increases with distance. So you should spread out as much as possible. So that's the other thing we can learn from this toy example, that one shouldn't distribute concentrated in the southern part, but maybe distribute as far as possible in the available locations. Okay, so there's just some references, and this was a little teaser or maybe some insight into what we are working on. And we are having data and a lot of things available with capacity factors and spatial distribution and time uncertainty, and we are trying to kind of optimize and see what we can do with these things. So thanks a lot.
Thank you. And if we get Marianne up here as well, it's open for questions. Yes, one there and one in the back.
So I have a question for you, Fred. So of course it's good to spread out to have a more even production or stabilized production, but we also know that it's not about having a stabilized production, but meeting the demand. And also, as you touched upon, is that transporting the energy also has some cost and loss. So how does this kind of add up all together? You know?
No, in the toy example, the condition was that you meet the average demand. So I called demand just one, but of course you scale it to what you have. So it's conditioned on that you meet average demand. But demand is also variable, so that's not accounted for here. No. And transportation costs through cables, of course, maybe you find an optimal allocation where you actually don't have any connecting cables. So that is also something you should and need to take into account. But we haven't done that, so and I didn't make any toy example for that. No.
Then those questions
Yeah.
there?
Yeah.
Go ahead.
Hi. If I look at the histograms that you showed between the variation between summer and winter, correct me if I'm wrong, but is the irradiation higher in the winter? That means that the power production should be higher in the winter?
No, these histograms are not telling you that. It's telling you the probability distribution in the summer and winter. So although it looks here like you have a lot, this is the variability. Yeah, it's the variability. So it's how often you have a certain variation around the mean, so to say.
Okay, thank you.
Yeah. Okay, further questions? Time for one or two more. Can I ask, just out of curiosity, you had this 2-day model. If you were doing this for Bergen, for example, would that be just a 0-day model with nothing? No connection, or what do you think?
Looked at Bergen, no. No, I think it will be highly variable actually, because it's if you have been to Bergen, and probably have been there more than me, then every time I've been to Bergen, there has been sun. Yes. It has also been rain. Yes.
Can I also ask, have you mentioned or showed numbers here just for solar, but have you looked at the solar and wind together?
No.
Because I guess there's,
yeah.
How do you think the correlation will be there? If you, for example, are in the same area?
This is a very, actually I don't have the figures now in the head, but we have looked at these things, but it's not written up, but it has been looked at, where we had wind and solar and capacity factors for a lot of regions around Europe, and trying to reduce variability by spreading out the production, so to say. But yeah, maybe Marianne has more to say.
You tested it in a course, so if you just have these 4 technologies and 2 technologies and 2 different locations, so you can actually see that it will always get cheaper if you add another location, and if you add PV, you will need less capacity, just because there's some diversification you can reach with PV more in the summer and wind more in the winter. Well, yeah, and often wind more actually during the night, and sun during the day.
Okay, very good. Thank you again. And you will also get some gifts. So, I'll do this one first. Chocolate. And the thermos. And for you as well, Marianne.
Thank you very much.
So, thank you again. And as you mentioned, you also have a project Empower, which is one of these convergence environments. And I think you'll get to present that in the next UiO Energy Forum next year. Then we'll be excited to hear what's... Yes, it's linked to Maya in the last session as well. And then, final presentation in this session. That's Brynja Lia, who also has a thematic research group. But I think what he'll present here is something slightly different. He is a historian and a professor of Middle East Studies at the Department of Cultural Studies and Oriental Languages here at the University of Oslo. And he has been studying or development interest in renewable energy and the development here in the Middle East, in Northern Africa, and also looking at Norway, I think. So we'll say a little bit about this, how the green shift is happening, both in Norway and in the Gulf. So I'll just leave the floor to you, Brynja. Go ahead.
Hello, hello, hello. So can you all hear me? Well, thank you. I'm really honored to be here. I'm coordinating a research project on the green shift and climate change discourse, where we're comparing Norway and select countries in the Gulf. So what I'm going to present are just some tentative results, because we're not fully manned yet, but we have started. This obviously is part of understanding the green shift as also a result of the human factor. This is not only about technology; it's also about human beings talking about this and having different perceptions about the viability and where people's preferences really count. But obviously, I guess you might want to know why do we actually compare Norway with Gulf autocracies? I mean, what's the point of such a comparison? And let me just say why I think that might be fruitful. Obviously, these are very different countries. Political system are very different. The demography also is different, although the Gulf monarchies are generally also small countries like Norway. And the level of oil dependency is also very different. And I think the prioritization of climate change in the political discourse is also much less in the Gulf than in Norway. But still, when we start digging into this material, it's actually striking to see the kind of similarities we find in the discourse on climate change in the region and here. So obviously both regions face the challenge of a post-oil future. We've been talking about searching for the nye olje and the new oil in Norway. That's has become a classic. Everything is the new oil, apparently. But that's also much more a pressing issue in the Gulf. And more interestingly, so far we've seen that both Norway and we've started with the United Arab Emirates as a case study. And we see that both these two countries have this self-perception, this self-image of being a green leader, despite being so reliant on oil and oil export. And more so, actually, that both have this discourse, this public discourse, that a continued oil and gas production is a vital part of the green shift. They're sort of framing it. We need to not only continue production, but even develop new sources, oil sources, and that is part of being able to finance and the green shift and so on. So both countries are, in a sense, engaging in extensive greenwashing. I'm not sure whether our politicians would agree to that, but I think it's fair to say at least that there is some greenwashing going on. Because Norwegian oil production is the cleanest one in the world. We've heard that a number of times. And for the United Arab Emirates, we're also pushing this sustainability thing in everything they're doing, despite even having such being so reliant on oil export. And I guess this is more like it's speculative on this part at this stage. I think both countries, both regions actually also invest heavily in green energy production without necessarily making huge profits. When you talk to people in the oil industry now, you get a sense that they're making lots of money on oil, but the green thing they're doing is still not so profitable. That's the image that's the sense I get from my conversations. And both countries are Norway and also the United Arab Emirates, so the Qatar, Bahrain, Kuwait also, and Saudi Arabia, are wealthy countries, and they also have the sense that climate change are putting extra responsibility on them in terms of sharing wealth and paying for for the green shift and have a responsibility there towards the sort of global social issue, justice issues. Okay, since I only have tentative findings so far, I'm gonna talk more generally about the green shift in the Middle East and the green shift discourses that we see based on the secondary literature, just to give you a sense of the challenges out there. Okay, so why is it that the climate change is such a pressing issue in the region, even though the sense you get when studying public discourse is not that people prioritize this as high as we do back in Norway. As you can see from this press article, the Middle East is highly vulnerable to climate change. We have extreme temperatures. It's actually common to claim that, and I think that's right, that it's twice as high temperature increases in the region than elsewhere in the world. We have water shortages, the certification issue. We have rising sea levels and so forth. And in addition, many countries in the region also suffer from power outages, which have become more and more frequent. So it's not only that global temperatures are rising and creating almost uninhabitable conditions in some regions, but that the power supply is also weak. So in terms of the Gulf states, they suffer from some of the same issues as we do back home, namely having very high greenhouse emissions per capita in these countries. And that is not, even if we discount emissions by the oil they export. But they're sort of in a double bind because their regimes are so highly dependent on financially on fossil fuel export, and we usually refer to these regimes as rentier states, in the sense that they're able to keep autocratic forms of government because they pay their citizens to be loyal, in a sense. There is a very low still renewable energy production in the region. I think the figure 5 used to be correct a few years ago. I think it's higher now, but the potential for solar energy and for wind energy is enormous. So it's a really big divide between the potential there and the way it's being exploited. So the public discourse on climate change is rapidly shifting, but up to for a few years ago, until a few years ago, it used to be like it was treated as a non-domestic issue, in the sense that these were sorted under international news. You know, this was something that other peoples were caring about, but not so relevant for internal politics. And when they talked about climate change, they usually tended to shift towards local environmental issues and talk about cleaning up the beaches and stuff that wasn't really related to climate change. But more recently, climate change has also become a more serious issue in domestic dialogue and domestic debates. We also see that there's a prioritization of adaptation over mitigation, quite typical. As for regional cooperation, obviously in electricity production, for example, that would be very useful and fruitful. But regional cooperation in general in the Arab world and the Middle East is weak. We don't have an EU for the Middle East. The region has been ravaged by war, internal conflicts, turmoil, revolutions, and so on, and that makes so regional institutions in general are weak. There's also low transparency regarding these issues, but things as we see it over the past few years are changing a bit regarding the cooperation. For example, very recently, Israel and Jordan started a deal with changing desalinated water from Israel and exporting green energy production, solar energy, back to Israel. Just one example that is sort of a rare light of in an otherwise dark picture. Okay, so why is it that we see a boost or at least an increase in solar energy in the Middle East? I think we talked about 2015 as sort of when there was really a shift in the focus on solar energy. When lots of countries started launching their own solar production programs. And now, over the past few years, there has been almost like a competition between different countries who have the largest solar power production facility. Here on this picture, we have pictures from the famous Ouarzazate solar power plant in Morocco, where they combine both the concentrated solar power production and also the PV production. But the reason for this isn't necessarily a concern about climate change. It's about the rising domestic consumption. So by producing renewable energy from solar and wind and so on, they can free up resources so that they can export more oil. In case of Morocco, they don't produce oil in a significant manner, but they are deeply dependent on imports. So this is important in that sense. So energy security is important for some countries like Morocco and Jordan and so on, while others like Oman, like Saudi Arabia and so on, are using this to free up resources for export. And for countries like the United Arab Emirates, it's very much about branding, to show off that we're really doing something in terms of renewable energy. But obviously, we are talking about autocracies to a large extent, or very limited democracies, and in these type of countries, energy transition in general, all kinds of transition, but also energy transition is a complicated affair. There are lots of technical hurdles, like we talked. One of the previous speakers talked about variable energy or in variable power or intermittency. That's an issue, storage and so on. But it's also about upfront costs that need to be financed. For the Gulf countries, that's not such a big issue, but for other countries in the region, it is. Lots of legal and bureaucratic challenges. State monopolies are really strong in this region. So to basically have something as like feed-in tariffs, for example, is a complicated issue when the state run most of the electricity utilities. So there's also the issue of community acceptance and social acceptance for various types of renewable energy projects. You might think that in autocracies that's not a big issue, but actually it is. So we have this term NIMBYism, you know, not in my backyard issues, and we've seen so the yellow vest phenomenon from France isn't limited to Europe. We've seen tendencies in that direction in the Middle East as well. And there's also a discourse about green colonialism, like resistance to Western extractivism. And I'm not sure how extensive that literature is and that discourse is yet, but we do see quite vocal activists promoting that narrative about the Middle East, especially about North Africa. One thing that is striking, a striking development over the past few years is this green hydrogen rush. This is not my choice of words, but we've seen that in the region. I put a question mark there because I'm not sure how much substance there is in this yet. But one country like the Saudi Arabia, for example, has launched something they call the biggest green hydrogen initiative or facility in the world in its new city in Neom. That's under development in Saudi Arabia. So, but this is just part of a series of initiatives from Saudi Arabia about, launching very big ambitions, but that those ambitions doesn't necessarily come. Actually, my daughter is calling me, so I have to just send her a message. Sorry about that. Okay. Okay. So that's one issue. The green hydrogen thing is obviously, as former previous speakers talked about, it's interesting and necessary for a number of reasons, for industry, long distance trucking, aviation, and shipping. And you would think that this would be very profitable for the Gulf countries to actually focus on, to produce green hydrogen, because of the potential they have in that regard. Obviously, that would solve the intermittency problem to a certain extent, but obviously it has a lot of technical disadvantages and might not be as cost effective as other solutions. So in the region, there is a perception that Europe and the rest of the world need energy, massive green energy to fully decarbonize, and that would provide an opening for countries like Saudi Arabia, who would like to export this sometime in the future. So the question is this? Are we talking about? We see lots of green ambitions in these areas, but when it comes to profitability of many of these projects, it's so low that it still is a question whether this will be profitable and be able to replace oil as a revenue generator. We still see that the electricity mix in the MENA region is mostly dirty, less than 10% for the whole region, and much less for the Gulf countries. But it has risen though recently. I think in Egypt it has gone up quite a lot. They built a huge park there in Upper Egypt in the Benban power plant. So the power plant is one of the largest in the world. But the problem in the region, and also especially in the Gulf, is that energy consumption is rising sharply, and with if the current increase continue, the Gulf countries will have, or the Saudi Arabia alone will be forced to import oil for generating electricity. That won't in 2038, I think it is. But that won't obviously not happen. It can't happen. But it says something about the enormity of internal consumption of oil and gas for electricity generation and so on. So and a final issue is also that the idea about the Middle East being a green energy exporter is still a distant one because of the rising domestic consumption, and I think it's also an issue about the Middle East remaining only a producer of raw material, and that is an issue that I think is a problem in the local debate. Okay, I'm just gonna skip through this more quickly because I'm running out of time. But yes. Yes, let me just focus on the political obstacles. I think that that's a topic that's being repeated time and again in the region, that we have so many internal wars and crises and turmoil that we don't have energy and time to focus on the green shift. That's quite typical in many countries. I know, the war in Yemen, for example, is a very serious issue for the Gulf monarchies. Also, their conflict with Iran, although that is lower, getting lower now. But all those together creates pushes basically the green debate further down the list of priorities. But we have seen over the past few years that the countries in the region are prioritizing the building of huge solar energy projects. There is a competition now between different countries in terms of who is building the largest ones. And they're also using this energy project for visibility, for symbolic purposes, like the solar cooling system for the soccer World Cup in 2022 is just one of many examples. They have extremely high ambitions, but there is a gap between the announced project and the implementation. So a final issue I'd just like to raise before I end is the issue of rentier state that I mentioned earlier, because we would think that a transition to more distributed renewable energy production, which is harder to control by the state, would sort of make it easier for these countries to, or for the opposition groups in these countries to push for demands for political reform, because we see whenever there's an economic crisis in these countries, the system opens up, it liberalizes, because it needs public support. And whenever oil prices are going up, the opposition is being cracked down upon. So is renewable energy sort of a response to the democracy deficit in the region? There's a discussion in the literature about that, and I think also in the public discourse, I hypothesize that that's something we will obviously find in the political discourse, that perhaps renewable energy in one way or another will make the rentier states in the region less stable. Okay, just a few words about the project. We're not fully manned yet. We're going to hire hopefully the last postdoc. We're 2 postdocs. There are 2 postdocs on the project, but the aim of the project is to basically look at how government and societies in these 2 regions are responding to the prospect for a green shift. So we're using discourse analysis as a method, both quantitatively and qualitatively. Many different types of sources, media, government reports, interviews, and so on. And the countries we're selecting, initially we started with Kuwait and Qatar, but now we're considering or studying the United Arab Emirates. It depends on the last one who's going to be employed now, where the focus will be. So yeah, that's it. Thank you. Thank you for your attention.
Thank you. Thank you so much for taking us to another region of the world and sort of the larger perspective here. So we can do a few questions. I can start just by asking myself, you sort of hinted at this, because you say that there's the risk that there will be kind of raw material producing the hydrogen. So there's not much discussion then, I take, about using this energy, using the hydrogen to produce same materials, produce fertilizers. There should be a lot of options that could be done, and that would be easier to transport than hydrogen. As we heard from Statkraft, it doesn't necessarily make sense to transport hydrogen or ammonia or these chemicals, this energy carries a long way.
Yes, but I think the monarchies in the Gulf see that they need to export something to generate revenues to make up for the downfall or the decrease in oil profits over the long term. So I think that's definitely something they're looking into to find ways of exporting energy. There was a huge project more than 10 years back about the Desertec project about exporting renewable energy through electric cables across the Mediterranean, and that idea is still there. The Desertec idea is still. There are new generations of that project coming up, and so there's a lot of dialogue between Europe and the GCC countries on cooperation on clean energy and including clean energy export. So I think this is very much on the agenda.
Yeah. So there's a question up there.
Yes, thank you for a very interesting presentation. I'm wondering a little bit now, this was the focus on the Middle East, as I can understand, but if we look at the south of the Sahara, for instance, in South Africa, I was listening to an interview with a regulator in South Africa, and you mentioned this green colonialism, and what was interesting in that discussion is that those were the type of words that would frequently come up from this regulator. And do you think there is a lack of understanding, let's say from European companies who want to sell, let's say, as this South African was saying, European solutions for European problems? Do you think that is something we should be more aware of? Yeah.
Yes, I think we just need to know more about that debate and the prevailing perceptions. But I think some of that criticism or skepticism is part of the elite wishing to retain privileges and so on, because a closer energy cooperation with Europe would demand a liberalization of the energy sector, which will then decrease the monopolies, and then the revenues generated from these that goes to the elite will then diminish. So some of it is elite concerns about losing power and privileges, but I think because the elite is, some of the elite groups are pushing that agenda. You see it very clearly in Algeria, and the guy I refer to here, Hamza Hamadouchi, he's an Algerian, but he's I'm not saying he's talking on behalf of the elite in Algeria, but it's also a typical leftist criticism of the Desertec project and similar project of energy compression. And I think it has to do with the way that some of these energy projects are being implemented on the ground, like the Varzazat plant, for example, in huge plant consumes a lot of water, and there were concerns in the local communities that they didn't get any employment because some of these facilities are very high tech and they don't demand much local labor. So it's like the benefit for the local communities might be very, very small over the long term. So finding ways to make this a local initiative and local ownership, I think, is very, very important.
Very good. Thank you again, and thank all the speakers from this session. You'll get some chocolate and thermos as well. And I can just say that in the next session, we will touch upon the green colonialism in South America. So we'll follow up on that.
Thank you.
Yeah. So we'll do another 20-minute break. We'll start up again at 14:40. There should be coffee and something to chew on, I think, outside. So stretch your legs, and you're welcome back here in 20 minutes.
Det spørsmålet for deg.
Ja, det er et godt spørsmål. Det er et godt spørsmål.
Det spørs om svaret er godt nok. Ja. Har jeg 20 minutter til å snakke?
Cirka.
Ja. Jeg skal prøve å være flink.
Ikke bruk mer enn 20 minutter.
Nei.
Et eller to spørsmål sånn kjapt også, for det får litt alle til på slutten. Så vi har jo 8 minutter til sammen. Okay, so I think we're mostly back. So welcome back to the last kind of, well, I shouldn't say scientific, but it's kind of ordinary session here. We'll focus on sustainable transitions with a question mark behind it. So we'll again get different perspectives here. We'll start off from catalysis with Professor Une Ulsby. She's at the chemistry department and also at the Center for Material Science and Nanotechnology. She has a lot of experience with working with industry, working at Sintef, and is now, she has a lot of interesting projects here as well at the University of Oslo, and was awarded the ERC Synergy Grant, and it doesn't get much better than that, does it, Une?
No, that's true. Now I don't remember which...
I think it's on. If it doesn't blink, it should be okay.
Can you hear me? No? Hvilken var det du klikker på?
There.
Okay. Hello? Do you hear me now? Yes.
Good.
Yes.
Floor is yours, Une.
Thank you. Thank you. Yes, and thank you for the invitation to come here and talk. So I'm representing the materials scientists today. And the starting point, I like to quantify things. I'm an engineer. So I was wondering, will Norway be able to do this transition, and what will it take? And we have two energy challenges in Norway currently. One is that we are among the heaviest consumers in the world, so we have to decrease our consumption. But that is not something that I will talk about today. That's something for each of us to think of. And then we have the reliability we have on the income from oil and gas export. So we need these alternative income sources. So that's the green shift. And then if we go back to basics, so how much energy will it take to replace fossil sources in Norwegian industry? Will we have enough energy, and could we make it last longer? And of course we could if we do some material science development. So let's look at the energy consumption that we have in Norway. This is a total consumption in 2020, 212 terawatt hours, and 151 terawatt hour are renewables. So for industry and mining, we have two parts here, the energy, which is 74 terawatt hour, and the raw materials. And if we now look at this, the energy need that we have in industry, that is typically for heating, for compression, for separation of products, etc. And if we look now at the energy balance here, we see that already it's quite green. Almost 53 terawatt hour out of the 74 is renewable, and only 21.4 terawatt hour is fossil energy. So this is what we need to replace in order to just electrify the Norwegian industry. That's not so bad. If we then look at the raw materials use, that means that's the chemicals that we use as reducing agents for metal industry, or carbon source in polymers, petrols, in ammonia production for a hydrogen source. And that is higher. And we see that among them, we see that the coal that typically goes to metal production, that's only 0.6 terawatt hours, so that's not so much. So then it's the oil that is the main part here, and then some natural gas. This goes mainly to fertilizer production and some polymers. The oil goes typically to the oil refineries, and it's making both polymer and monomers for industry, and then for consumer products, but also to fuels. So what we need to do when we think of these raw materials for fuels, for consumer products, it's all of these products that we see here. I mean, it's the fuel, but it's also clothes, it's paints, it's cosmetics, it's medicines. All those carbon-containing products are made mainly from oil, some from gas, and then a little of it from biomass. So what we need to do in this green shift that we are having is to replace that with recirculation or recycling of these products, either directly or more indirectly by making them or burning them into CO2 and water, and then recycle the CO2 and water. So that's the far end of this transition that we need. So if we now assume that we go all the way to CO2 and water, so what will it cost us? If we look here, this is the typical product ranges from a refinery, so 15% to consumer goods and 85% to liquid fuels, mainly for transport purposes. And then this is what goes into the production, and this is the consumption of the fuel itself during transport. We could, when it comes to transport, we could replace the liquid fuels with batteries. And that is true, at least for personal small vehicles. But we have one problem with the batteries, and that is the energy density. If we look at the density of petrol, it's 13 kilowatt hours per kilogram. And then we see for the lithium-ion batteries that are state-of-the-art, or that were state-of-the-art in 2005, we see it's 2 orders of magnitude less. And also, when we look at lithium-ion batteries in 2020, we see that it has increased the density a little bit, but nothing that really makes a difference. And when discussing with my colleague, Alexei Koposov, who is the battery expert at UiO, presently in Grenoble to do experiments, that's why he is not here today, he also tells me that this is mature technology, the lithium-ion batteries. So battery research now is more about replacing lithium with sodium, for instance, as they are working on, making electrolytes that are more durable, and also having more sustainable production of the battery itself. So this means that when we think about long-haul transport by ships, by plane, or by big trucks, we need something else. So we need either to use hydrogen directly, or we need liquid fuels. Just to say, I'm not sure now, but I think that in the first version of the Tesla car, the battery pack was 700 kilograms. Now it's probably much more. So it's out of question to have something like that in planes, for instance. So we need to either make hydrogen, or make hydrogen and then convert it to liquid fuels, ammonia or petrol. If we then go back to the consumer goods, then we know that here we need to do exactly that. First make hydrogen, then make the product out of the hydrogen and CO2. And then, so much of this was already part of the Statkraft presentation today, of course. But there is one thing that I can add to the picture, and that is the energy loss that is associated with the conversion of water and CO2 to hydrogen, chemicals, and fuels. And typically, if you look at water electrolysis, we have this typical electrolyzers from Nel, for instance. When you go to their sales page and you see how much energy you need to make so and so much hydrogen, and you can, at least as a chemist, I can find numbers. What is the energy content of that hydrogen? And what I see then is that there is about 40% energy loss for this water electrolysis. Then the good thing about these electrolyzers is that you can operate them on and off, depending on the accessibility of energy. So that's easy. But if you have a stable energy source, then you can use high temperature inverse fuel cells. And then those can be up to 75% energy efficient. So that means that you have this range of energy loss that is available. If you convert in an ordinary process natural gas to fuels and chemicals, this is something we have worked on for years, then we see that if you have simple processes, only going from one product or one raw material to the final product in one go, then you lose about 20% of the energy in general. If you need to go in several steps, having several reactors that operate at different conditions, so that you need to compress the gas between them, for instance, heat up, cool down, then you lose a lot more. So then you are normally losing 40% of the energy or more. So if we then should have a new process for recycling of CO2 and water, we just have to combine these numbers, and we see that we potentially have between 40 and 64% energy loss. So that means that we need surplus energy. And we heard from Statkraft that we will need about 50% more energy in industry. Potentially we will need more. So if we now look at the energy that we need, we had for fully electric energy supply for heating and so forth. We had these 74 terawatt hours. And then if with these raw materials, of course I have to make some assumptions there, but I just I assume that we have 15% going to recycle the polymers, and then the rest recycle to petrol or ammonia, and 50-50 between this and hydrogen. And then this is a range of energy input you need to have to get this output. And then we have the total green energy need here. If we compare these numbers to, and I'm sorry I don't have the source here, but this is from Norges Vassdrags- og Energiverk. They had a report where they predicted the net or the expected new electricity production capacity from hydro, wind, and solar in 2040. And they took into account that there is some opposition to some of the solar and wind power plants. And some of them are onshore and offshore, and so there is a range here, as we can see. And if you now compare this, and now I have taken out some and did some magic with my numbers, so I can we can discuss that later. What I did, I subtracted what was not needed anymore. But if we now look at this extra capacity plus the net export that we have today, and we look at the numbers here, we see that the maximum one, 59.5, is not so far from the 67. But we see from the lower end here up to the highest end, there is a big deficit. And of course here I assumed, the similar product distribution in the new energy. But we see that we need continued technology development, both in the production of electricity, but also in the processes that we use, where we use that electricity to fill that gap. So if we first go to the production of electricity, we see that while the battery capacity has not increased a lot since 2005, we see that the silicon solar cells from 2005 to 2020, the energy efficiency of commercial cells increased from 10% to 22%. So this is a lot. Not only the prices went down, but the productivity or efficiency is also much better. These are our numbers and information I got from Kristin Bergum, who works here at the University of Oslo. And what they are working on now are tandem cells. That means that you have a silicon wafer on top here that has a high band gap, and then some of the energy that is not used or is transferred over in this less energy intensive region, they are then going through another lower band gap solar cell. And then you can actually use much more of the energy. And they foresee that they will have a 50%, can have a 50% increase in efficiency here. And that can close much of the gap between the most favorable process side and the most favorable production side. Also, of course, on the other side, and since I'm a catalysis chemist, I have to talk about catalysis. We are working to, this is from a EU project that I'm heading, where we are trying to combine two processes in one reactor. First, we have a process for going from CO2 to methanol, and then a process for going from methanol to hydrocarbons. This one is typically operated in industry, the methanol production at 100 bar pressure and 250 degrees, and this one at 2-3 bars of pressure and 400 degrees. So there's a big gap here. And we're trying to develop a process where everything goes in one reactor, and we are targeting propane for the time being as a fuel. So the target that we had for this project was that we needed at least 30% conversion of CO2, and we should have at least 60% selectivity. So among the products, 60% should be propane. When we started, there was a 17% selectivity in literature. After year 1, we were able to have 5% conversion and 20% selectivity. And then after year 2, we had 40% conversion and 50% selectivity. So we have still some gap to close here, but it looks quite promising. So how could we get there so fast? And I think that is also one point here, not to brag about what we are doing, but in fact, the reason why we can succeed so fast is that well, I say the catalyst is the heart of the process, and we have worked on catalyst technologies and fundamental studies for me, 30 years. And the first 20 years, I worked with natural gas conversion. So all that expertise built up from the oil and gas technology can be directly applied in this new era where we're going to develop the green processes. So just this is a little snapshot from the reactor. This is the filling of the reactor through a normal microscope. This is a scanning electron microscope. So we see that we're at micron size here. We see the crystals. And then this is a drawn image, but it's based on a transmission electron microscopy picture. And here you see that the catalyst that we used has small pores. And they are so small that you can direct what they are molecular sieves, so that you can direct what molecules are entering into the pores and which one will be have favorable reactions in the pores. And this is how we can steer the selectivity of the process to the desired product. Now we also have ongoing project now where we are introducing metals into these pores, and this we do to replicate an enzyme. This is a copper site bound to 4 nitrogen in a PMMO enzyme, and this enzyme, the good thing about enzyme is that they are so specific. You feed in one product or one raw material and you get one product and nothing else. And what we want to find out is if we could be able to replicate this selectivity in a synthesized catalyst. So we could use this in industry, because then we would gain much more than by working with the ordinary processes. So we see here that these are silica aluminates that we have worked with before, these zeolites. Now we work with some metal organic frameworks that are also the same kind of crystalline open structures, where you have, but that are built up of inorganic cornerstones, and then you have organic linkers between them. And that means that you could actually, we are working now on synthesizing sites where you have copper bound to nitrogen. The nitrogen is blue. And so that it looks similar to what it does in the enzyme. And then, of course, in the enzyme, you have a lot of other, well, we have a lot of things around it. So it is a much more complex mechanism than what you can find in the synthesized catalyst. But this is what our goal is, to be able to replicate the full enzyme. Have I used my time now? Okay. Yes. I just wanted to say something about, because I always like to tell this also to my students, because this is the birth of Norwegian industry. Birkeland and Eide, when Eide bought the waterfall at Rjukan, and Birkeland was able to make a short circuit that they turned into a standing what do you call it? Lysbue. That would create nitrous oxide from air. And this they needed to do at very high temperature, and the reason they wanted to do it was that the world needed fertilizer. At the same time, there were two Germans, Haber and Bosch, and they were working on a catalytic process. So you see Haber here in the lab with the catalytic test reactor. And this process, the catalytic process, because the catalyst is changing the pathway, so it can operate at much more favorable conditions. We see that by adding the catalyst here, they decrease the energy need of the process by an order of magnitude. And then later on, they decided that maybe this is not fitting so well to the shift today, but it's illustrating that here they stopped using electrolyzers to make hydrogen and started using fossil fuels instead. And then they decreased again the energy use, and then there's optimization after that. But this accounts for 1% of today's global energy consumption, this process. So it says how immensely important these processes are. But there is just one thing I want to say, at the end here. And that is that this fertilizer production process, the reason why I'm bringing it up was that it was developed in response to another global crisis. And that the first solution, the one of Birkeland and Eide, it was sufficient to solve the immediate problem, the immediate crisis, but it wasn't a very good solution. So the better solution were found later. And I just compare this to the first generations of electrical cars, and then to Tesla, that was the most sold car in 2015. So with that, I just want to thank you for your attention, and I think I have my conclusion here, that if we combine existing expertise with these new challenges, we can actually bridge the gap, the energy gap. Thank you.
So I think we can do one question, and then we'll have a discussion or chat at the end of this session with all speakers. But if there's a quick question directly to me, that's possible. I heard here that you're saying that the catalysis people and the solar cell people are much better at improvements than the battery people, right?
No, I do not want to be cited on that.
That was my words, not
yours.
Yeah, I don't see any questions. Then I think we'll do the questions at the end, so you can start thinking about further questions to Unni, and then we'll move on to the next speaker here, if I can even get... Huh. Interesting. Yeah. Mouse pointer gone missing. Yeah, so that is Alexander Dunlap from the Center for Development and the Environment. Whoops. Yeah, that should be ready. Alexander is a postdoctoral fellow at SUM. Working within energy and extractive perspectives. I think you'll give us some more food for thought here related to the green shift. You're perhaps a bit more skeptical towards the green shift, I think.
Yes, I am.
Even though you're a postdoc, you are very highly cited. So we are excited to
Yep. I've been, so yeah, maybe a little bit of context. I come from a very opposite direction. I have a PhD in social anthropology, so I think a lot of what this will be to do is to really try to go after these Latourian black boxes and kind of rip them apart. But let me give a little more context for this, and a lot of what's in here is going to be based on I was recently a contributor to the report that green mining is a myth for the European Environmental Bureau and Friends of the Earth Europe. So some of this will be coming from that. But I just want to stress that since 2014, I've been working on energy infrastructure and also mines. And this means living with the people in resistance, really trying to understand why people are picking up arms or making blockades against these things. Really listening. I mean, I still remember this woman talking about the last day she saw her dad before police shot and killed him and prevent him from going into the hospital for trying to prevent copper mines. So please know that this is coming from a place that is actually rather involved and upfront to really understand where these numbers and these things come from. And I kind of want to drag you into this today. And this is working, yeah? All the technology. This isn't, though. We can do it the old-fashioned way. So I'll be giving you a piece of kind of a lecture that generally looks at energy infrastructure in 5 phases: raw material extraction, land contracting, ecological, economic, and cultural impacts, energy use, and decommissioning. But today we'll just be looking at some of the raw material aspects. Yeah, and so here's a monograph I did for my fieldwork looking with wind energy development. If you want to look at some of the levels of violence and kind of armed conflict that kind of go on with kind of these infrastructure projects. But really, so when we're looking at these numbers and we talk about these things, you know, what is green exactly, you know? So, okay, I guess I'll look at it this way. But ultimately, there's roughly 8 kind of standard types of wind turbines. And they're going to have a slightly different material impact than each, but they're all going to have roughly the same kind of impact. And you can look into kind of the averages of the amount of concrete that they need. Here, I'd like to actually be able to look at these things more specifically on here since I don't prepare for anything. But these things, they need an enormous amount of concrete. You know, these are between 17 and 14 meters deep, and they're between 16 and 20 meters wide. A lot of this all depends on the geography of where you build these things, for how much concrete reinforced steel that you'll need, which are going to need a lot of steel. They need tons of steel per megawatt, they say, between 107 to 132 tons of steel. So this is enormous. The aluminum, the numbers are kind of mind-boggling. You know, roughly you need 5 tons per megawatt of copper, and it goes on into different rare earth minerals and all of these different things like this. And I think one of the lines that I stressed that I'm skipping over in this is that I'm someone who's stressing that, you know, the term renewable energy is completely inaccurate if we're looking at the impacts of these things on different habitats and different ecosystems. And we're forgetting that in all of these processes, how dependent they are on hydrocarbon extraction for different fuels, diesel, and things like this, or choke coal in the case of kind of steel manufacturing and processing. And so for me, it's really important that we break down this, I call it the fossil fuel versus renewable energy dichotomy, that's rather polarizing and also big in kind of the Norwegian debates. That in the end, if we actually go down the supply webs, if you have an iceberg in front of you, if you go down the supply webs, you'll see that it's very much fossil fuels and so-called renewables or low-carbon technologies are rather deeply interconnected and have far more extensive and destructive kind of supply and energy. The energy that they use is far more than we're able even to calculate, which we'll get into. Okay, it's not working since I started pressing on it. Still isn't. What is... there it goes. So again, to kind of humanize these numbers a bit more, which again, I'm still in this level of abstraction based on different kind, you know, for me a big issue is, you know, what is this data? Where does it come from? How is it measured? And how is it being put into these models? But you can look roughly that, you know, for aluminum, 1 ton requires 4 tons of bauxite ore, which then generates a certain amount of waste, and it has an entire leaching and processing kind of, you have to leach it out and use all sorts of different chemicals, which I'm very interested to talk to chemists about more, in terms of actually the production processes that go into these chemicals that are toxifying environments. Copper, for 1 ton of copper, you need 110 tons of waste ore, and this is all coming from the London Mining Network. But these numbers tend to, I've triangulated them with other reports, and they seem, these averages, again, and they're approximations. I imagine it's actually much worse than this. But rare earth elements, 1 ton, and there's different rare earth elements, obviously, but 1 ton generates 1.4 tons of radioactive waste. It requires 6 million liters of, creates 6 million liters of waste gas with hydraulic acid, and 200,000 tons of liters of acid-containing sewage. So these are highly toxic processes, and thanks to China sacrificing its environment, at least for the EU, 97% of all rare earth minerals come from China, according to the recent kind of critical raw materials document in their appendix. Iron ore, 1 ton waste, I mean, it goes on, and it's rather extensive, and there's more minerals than this. So for me to even keep track and to see this and the amount of weights has been rather challenging, and to really understand what goes into this. And I guess there's 2 ways this can be done. You can actually go through the companies that would want to disclose these things, which they have little bit of an interest to disclose, or the ways that I've kind of tried to do before is that you go to the mines and then try to follow them up to just try to even understand what mines are leading to what smelting facilities are they outsourced to, which have what type of labor conditions, and what type of energy requirements, and so on and so forth. It's a rather complex webs. Oh, at least it's happening there. Again, where do these come from? It's mostly sourced in the global south, but as we know, and Norway's been on the head of the game for what they've been trying to do for mining in Sami territory with the copper mines. There's this kind of push towards a more internal colonization. So right now the push for the critical raw material frontier in the EU, they're really pushing, they're going after Spain, Portugal, and really doing everything they can to kind of prevent their kind of mineral insecurities, even by what they're planning, it looks very far off, as they admit in the documents. But so a lot of the times when we're talking about low carbon infrastructures or green, we're talking about really just exporting different extractions, different uses of fossil fuels and things like this, even if there's a turn to try to start dumping these type of waste in the fjords in the north, for example. Can't remember the name of the mine. Oh, it's doing it again. It worked on mine. Yeah. Do I just have to turn this on? Will this help it? What's the best way? Because if I click on this, it makes that not work.
I think this is part of the problem. Let's see. Like this.
But I can keep talking. but all of these things are very highly connected. There's such an inseparability between all of these processes, it's very hard to deny them or to divide them, and also really complicates this renewable energy versus fossil fuels. And it also kind of raises issue with the way that we're not actually talking about the levels of consumption, the types of urbanization, and really what a lot of this is about is really trying to put reflection into consumption patterns. Here we go. I just press this one. Ooh la la, it's working. Okay, but I mean, here's some graphs of some supply chains. Here's some silly kind of ghetto graph that I made to kind of talk about the renewable energy extraction nexus, to really stress how hydrocarbons and different types of hydrocarbons are used in every process of kind of manufacturing and production. And obviously the idea, the utopian idea, is that there's the giant problem that there is no attempt at actually creating balance or stability. There is constant growth always, constant consumption, constant needs for different annual profit measures. So this means that there's always going to be a need to constantly extract. And so until there's this, the big criticism of transition is that it's really addition or transaction, and that it's not transformation. And I mean, the reality of it is they're more socio-technical transitions more than any real kind of energy transition based on kind of large-scale consumption patterns, which I'm sure we'll talk about more. But again, this is just to stress how much fossil fuels are part of these supply chains. So here are the popular scenarios for kind of transition and for understanding the kind of the need for extraction. And it's widely known that obviously low carbon infrastructures are highly more mineral intensive than the existing kind of fossil fuel or thermal power ones, but at the same time, I don't think any of this accounting is being done in any accurate way and understanding the origins and how much energy, construction, and materials is even going into original kind of thermal plants or different kind of coal production. So that there's a lot to unpack and to try to figure out there. But so here's kind of the World Bank is saying, based on kind of low carbon infrastructure, things that, aluminum, indium, and silver are going to go up 300% by 2050. Copper, lead, iron ore, more than 200%. However, if you look at the European Commission's data, wind, solar, and infrastructure demand for lithium, dysprosium, cobalt, neodymium, and nickel is going to go up 600% in 2030. And this is all on 2018 levels, which are rather high. And it's going to go up 1,500% in 2050. And so EU demand and that's just for wind, that's just for wind and solar. But so when we started accounting for demand for electric vehicles, lithium they're saying is going to go up by 1,800%, cobalt by 500%, and the demand is going to go up even more by 2050 with 600%, and lithium by 1,500%. And I think what's fun about some of these older calculations is that Norway itself has actually already outdone earlier estimations for demand for electric vehicles. So these, as I'll get into, these are all extremely conservative estimates for understanding ecological damage and toxification, but even by kind of the own standards of actually demand and consumption. But also, fun facts, this does not include the kind of the amounts of ore needed to leach or extract minerals. So it doesn't really include the energy that goes into actually kind of getting these minerals. It does not include, and especially for specialty minerals, and then there's declining ore rates and a lot of different kind of factors like this, but this does not include e-bikes, e-scooters, or distributional electrical infrastructure like power lines and transformers, where I've been working in environmental conflicts in Southern Europe on these things. So this isn't even accounted for. All those scooters that we see running around because people don't want to walk or ride their bikes anymore are kind of directly related to kind of to the rare earth mineral production that's mostly coming out of China. And so this is, again, another rather sad step that we're not riding bikes or walking or using different kind of trains or public transportation, instead individualizing these things, which looks kind of fun, but has severe ecological costs. And yeah, this does not include digitalization. And if I don't know how much you are familiar with the digitalization, the bureaucracy of digitalization at UiO, it's a bit of a nightmare. It doesn't help my teaching. It doesn't do a lot of good things for me. In addition to all the smart cities, the European Commission admits that everything in the periodical table is used in the different sensors for smart cities, but there is no data on this, or to my knowledge, or at least from the European Commission, there is a lack of data or no data on this in terms of, so this isn't included in these numbers, more or less. Unexpected increases in demand, I already mentioned that, and so there's the issue of ore grade and technological advancements, which I think everyone here is very familiar with. But for me, I'm rather discontent with these numbers. These numbers have zero to no texture of actually what is really going on to secure these minerals. And this isn't talking about the landscape degradation and destruction of actually opening these mines, whether it's when you're doing open pit copper mines that are putting different kind of minerals in the air and different toxins, or the dams that are systematically breaking. I have a list of all the big mining dams that have broken. They break all the time. They break just like pipelines leak oil at this point, as I think we're kind of well aware from, I hope, from watching the kind of the pipeline construction in the United States. And so yeah, and this is destroying ecosystems. There's a lot of talk about corporate science from Stuart Kirsch, who did a lot with mining in New Papua. This doesn't get into the human rights violations and the application of counterinsurgency techniques to kind of break local resistance in the areas, whether it's blockades, but also and this is really brutal stuff, and whether it's dropping rocks on people from helicopters or tear gas, lighting their houses on fire, black bag raids, and also kind of using the threat or use of rape as a tactic to break resistance in these areas. I've had a lot of really kind of gross conversations with paramilitaries actually who work for mining companies in their different departments. Asunto Internos, or internal affairs that specializes in counterintelligence to kind of break and negotiate with leaders and break resistance in towns, but also to prevent and work against other mining companies who are trying to do concession grabs, which I found to be rather interesting. And not to mention the racism that kind of goes over, that is kind of wedded through all of this, and also just the kind of the levels of economic inequality that are being exacerbated. So behind these numbers, behind these things, I just want to stress there's like really not nice stuff that kind of pretty much kind of haunts me to this day. But to try to wrap this up, kind of ways forward is I'm kind of calling for, there's an introduction, the conclusion for a book coming out on energy democracies. I'm really trying to stress that, I'm calling for an insurrection in energy research to really change the way that we look and how we're approaching research. And so this means really looking at supply webs and how they need to be unraveled. They truly need to be unraveled in terms of, again, what is the data that is, what is the data that's being plugged in there? How is it actually measured? How complete is this? How many assumptions are being made in terms of what this data is that we're buying off of these weird private sector websites or getting in these different ways? And then also really questioning these models and the assumptions in the models that are going on. Yeah, and so going after the supply labs, really looking at the kind of data collection, and again, this really, the insurrection part of this is really ending epistemic violence or discrimination against other methods of knowledge and knowing. And kind of the go-to example I use is that when we even talk about health, and Norway is particularly stronger at this than other countries I've lived in terms of, only acknowledging quantitative approaches, really ignoring other sciences. For example, Chinese medicine that has been around forever that is based on the concept of qi and understanding that the bodies are made of energy, which has a completely different, it's going to have different consequences in analyzing and assessing the impacts of energy infrastructure. And I come from this going door-to-door interviews with, and also having it widely known in these areas with wind turbines and a lot of infrastructure about how there's lots of different cancers, lots of different problems. Obviously, it can be related to a lot of different things like diet, but there really needs to be an opening up, and as they say in medical anthropology, advocating medical pluralism or really mixing different sciences and approaches to really understand the costs that are the kind of the ecological but also social costs for these kind of types of mines and kind of infrastructural development. And this means changing the language. For me, it's very difficult if you're at these mines or these things like this to see these things as clean, green, renewable, or even as a park or as a farm, especially with the different kind of enclosure and privatization of the winds or of solar, of different things like this. And we're getting there. But and for degrowth now, and so I think this means really taking seriously the abundant literature coming out of the degrowth school, which isn't about economic collapse or anything like this, but really coming up with strategies to kind of address this issue of consumption and actually improving the lives of people, as opposed to having some type of economic meltdown and collapse, which has been kind of one of the strongest arguments for decoupling. And then finally, just really actually looking right now in energy research, there's a lot of weight just throwing behind democracy, and to really actually critically to look, and this isn't advocacy for dictatorship, it's quite the opposite, but to really get more innovative in terms of the forms of organization that we do, in terms of how we're in universities or elsewhere to try to address this issue of kind of socio-ecological degradation. And with that, I'm done, and thank you. Yeah.
Thank you very much for that cold shower.
In Norway, I think cold swims are appreciated here.
If there's a quick question, we can do that. Otherwise, we'll just save the questions till the end here. I don't see any hands, so I think then we'll just move on. And this will, of course, partly cover what you said, the missing digitalization, I think. Maya will cover part of that. Let me just be sure I'll clean this as well. So our last speaker of this session is Maya van der Velde from the Department of Informatics. She's working on technology and society, and she's also the head of our final thematic research group called Circular Energy, which is about recycling and repair and digital devices and furniture, I see.
Yes, I like show and tell.
So I think I'll just start this. Yeah, you can use the clicker. That should preferably work now. So, floor is yours, Maya.
Thank you. Can you hear me? Okay. Well, first of all, thank you for inviting me. My first UiO Energy Forum, and it will not be my last. Yeah, so my name is Maya van der Velde. I lead the Regenerative Technologies Research Group, and I'm also heading the Sustainability Lab. And today I will talk a bit about our new thematic research group called Circular Energy for Sustainable Circular Economy. We do both qualitative and quantitative research in our group. But today I will mainly talk about repair as a kind of energy conservation strategy, and I only have qualitative data for you because that's the kind of research I do. We also were able to hire a postdoc, Tigist, who is also here with us, and she will do the more quantitative life cycle assessments of the kind of energy and climate gains when we repair our digital devices instead of chucking them. So this is our team. We are mixed, so an interdisciplinary group from people from the Department of Informatics and the Department of Private Law. And we also have partners, the Science Library of the University of Oslo and Climate House of Klimahuset. They are both participating also by providing us with room and organization of events to also do kind of public dissemination of our research. And actually do also repair activities with people. So we started in May, so we are very new, but we already were very active, and UiO Energy also funded 3 master students this summer, so I will also talk about that project today, because there we actually have data now. We are starting our work with life cycle assessment of digital technologies, and we had last week, I think, a very successful Fixing for Future symposium where we had more than 20 researchers based in the Nordic countries talking about all kinds of aspects of repair. So legal aspects, design aspects, business models for repair, etc. And tomorrow we start with a new group of master students who will actually design a kind of more tangible or visual presentation of energy use in what we call these days net zero buildings, because the problem with kind of net zero language is that you make actually all the energy, but also all the risks and impacts of producing that energy invisible. So we want to make that visible, and whatever that's going to be, I don't know yet, because that's also the task of these master students. So we have a project that's called Circular Energy for Sustainable Circular Economy, but my presentation today, as you can see, I changed sustainable to regenerative. And that has to do with the fact that also the name of my research group changed to regenerative, because the term sustainable and sustainability, and we talked about, we do a lot of sustainable design in our group, has become almost sometimes meaningless, because we can use it now for everything that makes things a little bit better. But a bit better is not good enough. So we are looking we take this whole system perspective, and we look at how actually ecosystems survive, or how our bodies survive. They do that by repairing, by restoring, and rebalancing. So then our question was like, can we also have technologies, digital technologies that are regenerative? We don't know yet. It's also part of this project to figure out if that works and how. I will not talk about the urgency of why we need to think differently. We already heard other presentations. We have to produce less, consume less, and we have to repair the atmosphere. But back then to the circular economy. This is one of these central concepts we work with, because it's also a very central concept in Norwegian policy. So these are some popular representations of what is a circular economy. And this is then the current state of the circular economy. I didn't put a land on it or a sector, or it's just some general notes. What you can see here is that we have a lot of attention there's a lot of impact still in the extraction industry, which also Alexander already talked about. When it comes then to recycling as a kind of solution to this problem, we see that we have targets for recycling, we have the EU Waste Directive for recycling. But if you, for example, look at mobile phones, you all have a mobile phone, how big a part of the mobile phone will be recycled if it actually enters a top-class e-waste recycling plant? At the moment, about 17 out of the 62 materials are recycled, and the rest of the materials are used for fuel for the process. So there's an immense loss of materials and energy. For textiles, we heard last week that only 1% of the textiles that we throw away get recycled and put back in a kind of circular energy. A circular economy, sorry. And then when you look at repair, there are no targets for repair. When you look at the University of Oslo, all its service contracts with digital technologies say they last for 3 years. If you're a consumer in Norway, you have the law guarantees that you have 5-year warranty on your products. But the university has signed away this kind of regulation. Then things are happening on the EU level. We have now the Eco-Design Directive that has identified 10 products for which we now have a kind of right to repair. But the digital technology we use the most, at least here at the University of Oslo, mobile phones and laptops, they are not part of the EU directive. And that is the result of intense lobbying by the tech industry, big tech industry. So, what we do in the project, what we call then first a sustainable circular economy, we realize we have to slow down the circularity of this economy. So we decided to focus then in our project on repair. And we see then repair of our digital product as a way to conserve energy, because the longer we keep our technologies, we don't need to invest energy in a new product, and we don't have to invest materials in a new product. So and that's what you see here. So that's where we are at the moment. We're focusing on energy conservation by product lifetime extension. We are looking with the law faculty into looking at these kind of service contracts. So we take then also here the University of Oslo as our main case. What kind of tenders are written, what kind of procurement contracts are signed, and how can we extend the service contracts on digital technologies. And then also we would really like to propose some targets for repair to the University of Oslo. And why this is necessary, so these are just 2 examples. This is not based on repair, because if you, for example, would put a new battery in your smartphone, and you also have to calculate the CO2 or the energy that went into producing that battery. But this is the kind of research we are trying to do, but then including repair. And you see here, for example, if you extend the lifetime of all smartphones in the EU by 1 year or 3 year or 5 years, you will get this incredible effect in terms of energy conservation and less, of course, greenhouse gas emissions and loss of materials. The same is true for laptops. So I want now to jump back to this notion of a regenerative circular economy. And here, of course, I'm very inspired by the economist Kate Raworth. I hope most of you are familiar with her, so I don't have to explain the whole donut concept. But it's based on the planetary boundary frameworks, and a big part also overlaps with the Sustainable Development Goals. So which forms the social foundation of this donut. So based on her work, we can say that the regenerative circular economy is a just and distributive economy, sustaining a good life for all people and planet. So what then does repair? How can we look at repair from this perspective? So I've been doing repair research for quite some while now. I use ethnography as my research method. I've been doing research in Ghana, in Accra, around this place called Agbobloshi, which some of you are familiar with maybe through a documentary called Soppelsmuggleren, which of course I have a very different perspective on what I saw there than NRK. I was guest researcher at your old place, social anthropology at the Vrije Universiteit.
That place is a bunker.
And there I was for 6 months a repairer in a repair cafe, just to see what it actually is to be a repairer. And this summer then, and this is what I talk a little bit more about, we had our own repair and conserve team with 3 master students, and we went around in Oslo and looked at what we call independent repair. We wanted to know what role does independent repair play in this transition to a regenerative circular economy. So we had a master student from law, and one from social anthropology, and one from human geography. We realized that we had to get on our bikes and we had to go around because many of those independent repairers are not registered as a repair shop. So we divided the city up and we had to limit our reach into 6 sections, and then we went on our e-bikes going around in Oslo. And then the summer students started to visit all these shops and asked for interview. They were able to do 27 interviews. What was very striking is the really wide variety of backgrounds in these of these repairers. And at the moment I'm now doing thematic analysis of these interviews, and I can already say there are kind of 8 main themes are popping up. But here are then 2 pictures. We also took pictures. This is on the left. Refix is, I think, the smallest repair shop in Oslo. It's not wider than this door. The repairer in the shop, he doesn't own the shop. He is a refugee from Syria. He lost his house and his IT business during the siege on Homs. He made it to Europe in a one of those small boats, ended up at Lesbos, where this big refugee camp is. And he now lives outside Oslo and was able to be reunited with his wife and 2 daughters. And on the right, you see the largest business interviewed. They repair witwaren or white goods. And the owner, it's a kind of social entrepreneur, so the owner has contact with NAF and accepts people from NAF, and then he trains these people to become repairer, and they get a real certificate, and hopefully they will join the independent repair community. And the owner says that he's doing this because he wants to give back to Norwegian society for the way they accepted his father years ago as a refugee. Now, very quickly, this is what the students thought about the project. They had their own presentation here with UiO Energy. And this is, I know it's not really readable, but in a way you have 27 interviews, and I'm now coding them. And these are the 8 main themes that are coming up. For now, I just want to look at the role of the independent repair sector for a circular economy, because that was in a way the. And what you see here is we interviewed people repairing mobility batteries, Jetlik, a new startup in Oslo. And they have created this kind of local circular economy. So they work together with a local e-bike company, but they also work together with this huge European-wide e-scooter company. And they use the batteries to repair other batteries, but also now to, as you can see here, if I can here, they're actually one of those bodies that you also had on your slides, the little electric car. They actually now used batteries made from these mobility batteries to create an little electric car that has a wider reach. So the second example is and this is where I brought in also, here it is, my screen. This is an example of how there are many independent repairers who repair mobile phones, and they really talk about the problem of having access to Apple spare parts. And whatever you heard in the news, that's not going to change, okay? So just to get that clear. So what they say, they created also a local circular economy, because when your screen breaks, it's just the glass that's broken. Apple has no copyright or anything on this glass. So if it's your screen and the repairer puts a new glass on it, is it still your screen? Not according to the Supreme Court in Norway, because they've decided that using this kind of screens are in a way copyright violation, because the Apple logos are on the inside of the screen. And so it resulted in one of the independent repairers being got in a court case with Apple. But at the same time, you can still buy them, and you still have this local economy of refurbished iPhone screens. So I don't know how many minutes I've left. Oh, 1 or 2. It's just, I want to say that when we talk about the circular economy, we always talk about flows of resources, and we try to create a circularity in these resource flows. But it's much more, repair is much more than an instrumental phase in a circular economy. And that's also why I brought this. We have lots of broken chairs at my department, and we throw away a lot of wood, packaging wood from whatever kind of equipment we buy. And this is what you get when you put these two together. And we call that transformative repair. Or this is a kind of categorization of forms of repair, and we call that reconfiguration. So reconstruction is really like what we do in these repair shops, trying to put things back in their old shape and function. Using actually refurbished screens, we move in a kind of remediation, we transform things too. So it still has the function of the mobile phone, but there's something different with the materials. And I have to, I guess, to be quick now. So what I'm doing also now is trying to map what I see in these interviews on this kind of understanding of repair. And what I want to show is that when we talk about repair as an energy conservation method, we have to look more than just plain product repair. Because when we repair, like in a repair cafe, we also repair social relations. We repair our relationship with our products, but we also at the same time help to repair our planet. And as you saw also here, it was a way of giving back to society and dealing with loss. So this is about my repair research in Amsterdam, my repair research in Ghana. I will not show you all the plans we have for our project, because I see that everyone wants to stop me, so thank you.
Thank you very much, Maya. And then I would like to get Unni and Alexander and Maya all up here. And we'll see if there's some questions in the audience, or if people are still have some energy.
Maya's so cool.
Yeah?
Yeah, Unni, if you stand by the microphone there, then it should be okay. The other two have microphones on. So, open for questions. Yeah.
Good afternoon, everyone. My name is Shelly Bogra. I am representing the Impact Department from Norwegian Institute of Air Research. Lovely presentations. Especially I'm working in the materials, recycling of materials management, basically, for the the low carbon transition and the digital transformation that is expected to happen in Europe and elsewhere. My first question is for Alexander. So you talked about the extraction cost, the whole damages that these extraction of materials would have. What kind of lowering of impact do you see from the recycling of these materials that are currently already invested in these technologies, which would be discarded, like from wind turbines, battery systems, and everything? Do you see any lowering of impact in that sense, and possibly the social impacts also, considering the degrowth thing you talked about? And my second question is to Maya. How do you address the value-added proposition in your, these repairing processes in the context of like whether these can be a feasible solution at the local level? I mean, how do you quantify that value added? That would be my question to you. Thank you.
So just
Yep.
Yep.
Yeah, I kind of just gutted a presentation that I have that's for a course. There's usually, from the World Bank, the rates of recycling. Some of it's better, some of it's worse than what's showing on there. But it's not enough. It's horrible, and especially, there's a lot of people, I think some of the people here today, or at some point here today, who are working on trying to improve a lot of these things, but in terms of recycling lithium-ion batteries, it's negative 1%. And there's different ways of accounting in terms of what's being used and what isn't, but again, in the extraction, if you want to talk about high-tension power lines, which are a big thing that's not even included in the data, so a lot of that metal is actually already tied up in existing infrastructures, but the long story short is that the recycling, while there's a lot of efforts to improve it, is horribly low. I don't see too much positive. Again, my general line is that there's no, if we're not going to talk about the growth imperative, if we're not going to talk about challenging shareholder value and maximizing it constantly at every annual accounting period, then there's little point in talking about any transition, because if it's going to constantly grow, recycling won't be enough, even though I think it's an important outlet. And currently there's just not enough, it's not developed as an industry well enough, and it has a way to go. And a fun fact is they saw on the covers of Bloomberg, for the composites for the different wind turbines, they're just putting in landfills in the US and Europe. So it's rather negative, and I don't know exactly what you're asking about degrowth, but I think recycling and a lot of what was shown about repair is so important, and it's criminal what the Norwegian court has done and what Apple is doing, and really there has to be a push to stop these things and to push for repair and to use these things. And with the example of what you're showing with the different office chairs and these woods, you can make, and if you get recycled carburetors, you can make do-it-yourself wind turbines, and then you got to steal batteries and get things like this or acquire them. But there's so many possibilities. I just want to stress, despite the negativity and the cold shower, how many possibilities there are, but they're so far from being exercised well enough, even though I think Maya was a great example of some of the things that are being done.
So about, I can't really see you because of the light, I'm sorry, but I know it's this, but your question was about, in a way, making it visible in terms of data, and also about scaling up. Now, in terms of making things visible in data, so we are planning, but this was on my slides, I had to click through, actually to make a very nice, accessible report to the University of Oslo showing the gains of repairing their digital technologies. And expressing that really with hard data. So this is also what TICAST is going to do. We're doing our own life cycle assessments, and seeing what do we gain by putting a new battery in a laptop, of replacing a screen, or repairing the thousands of routers, where we call them here in the University of Oslo. And so in a way, and we want to present this data, which then of course can be used by other organizations and universities, and hopefully it has a kind of effect. Now, scaling up about repair is I think, very difficult. As you can see, the lobby at the EU in Brussels against the right to repair is incredible, and at the same time, of course, Apple see things coming, and so that's why they announced last week, okay, we're going to give out spare parts for the repair, but you know, only from the iPhone 12 and up. So who has an iPhone 12 and who's going to buy one? Because if you buy an iPhone 12, you in a way, you know, you're doing the opposite of what actually needs to be done. You have to keep the mobile phone you have now for as long as possible. So it's, and as long as Apple also knows making phones that you can actually easily open, what's the use of having an Apple original mobile battery? So when it comes to scaling up, it's really, we have to get this through changes in regulation. We have to set targets. You know, targets and regulation at the moment I have the most confidence in, because repair in itself is becoming this kind of cool thing. You know, everyone is in repair, but not repair without changing our mindset of what is our relationship with our products. It just stays a gimmick, you know. So it's I know it's not really a full answer, but I think talked enough.
So can I just ask you in terms of, you know, we're talking about making new materials and so on. How much do you sort of consider all the issues related to this? Or if you wanted to comment on something else, go ahead.
Yeah, I was actually planning to ask a question to Maya.
Go ahead.
Because, yeah, and I didn't really hear your question, so we can take that later. But I think that we all want to recycle, we all want to repair, but it's so difficult to find those repair shops. And now you say that many of them are not even registered. Do you know why?
Yeah, well, I can tell you, I live around the corner from Greenland, and all these repair shops, because I talked to them also, and they are registered as import-export businesses, because they often have a owner who has good relations with often the country where they came from or their parents came from, and so they are very much into import-export. But actually what they're doing there is also repairing. So that's why we need to go around. So we made this repair map, as you can see on I think also Natuurvernverbundet is working with the repair map. Spieren, they are working with the repair map. So things are happening. I think Oslo municipality should also make a repair map, make it easy for people to. And of course we should have a repair cafe at the University of Oslo. We had one, or they have one at the Vrije Universiteit in Amsterdam, a green office, and well, we'll see how that works. But maybe we can make it work here, okay?
I hope so.
Yeah,
I truly hope so.
Yeah, but yeah.
Next year, we'll have it.
Okay.
I think so. Yeah, we're working on it.
Yeah. So then we can go just here to campus and.
But that means that if I go to your website, I can find the map. Or
yes, it's on the Sustainability Lab website.
Yeah.
So, yeah, question there.
Yeah, so I have a question to you and to you both actually. So I come from Germany, and right now gas prices are very high because it's cold in Germany, and they use gas for heating. And my idea, naive thought was that if we replace that fossil energy for heating with wind and solar, then we are a step towards net zero. But now I doubt, when after your talk, whether that's actually correct. And then also in relation to you said you're gonna use metals in these catalysts. Are these then also problematic in terms of the extraction? Yeah.
You can start, perhaps?
Yeah, I mean, I've actually worked on the Hambach coal mine in Germany and detailed the repressive strategies of RWE. But I mean, and besides that coal mine uses wind power, or I think one of the neighboring, besides them using solar panels and environmental offsets to kind of justify more coal mining, which is expanding, and there's people protesting right now down there. The problem is that there's increased consumption, and that there is no substitution really going on in terms of energy use and growth, and it needs to stop. There has to be a stopping of an addition of coal is being on top of wind, on top of solar, and then there's the issue that there's not much wind and solar and the overall energy consumption. And then the issues I'm bringing up is that you need tons of choke coal to actually do the smelting for the metal. And then you have examples, I mean, Norway's been trying to do it for a while, but you still need some of this coal. Sweden's pushing their green aluminum right now, and they're trying to make wind turbines that have 300, I think is a 300 wind factory or wind park that's based out of timber, out of wood and not metal. So there's efforts to do this, and they're trying to digitalize mining and have those giant dump trucks and make them digital and do the production processes and all these, but then those need more mining and more of these things and more production. So no, I mean, for me, I don't see it. I want to be convinced, but I fail to be convinced. And I mean, the idea is that you obviously build enough low carbon infrastructures or lower carbon infrastructures where they can kind of power themselves and go in circle and find some balance. But there's kind of a gaping hole of needing to consume more constantly and acquire more raw materials and to get more profits and to kind of ultimately do the entire purpose of most companies. So it's from this perspective that I'm negative, and I do not see. I see that there needs to be some new legal mandates that are actually celebrating repair and actually really trying to figure out what really needs to be. And yeah, sorry, the reason why I'm stalling is because
the concrete example of the Germans heating with gas, do you think they just keep heating with gas, or do you think the wind is still somewhat better than gas then, or?
I mean, so here's the my line for current negotiations in real politics. So the renewable energy dichotomy that everyone's talking about of versus fossil fuels or the oil industry. So like the Green New Deal and all these things are saying, oh, we will destroy the hydrocarbon sector, but we'll cover the world with wind turbines, solar powers, and electric vehicles. I think that there needs to be a more kind of intelligent conversation between actually making sure that the hydrocarbon industries are actually just putting their kind of energy into these kind of technologies, and then there needs to be a stop at just constantly producing and consuming more energy. And really, the wind and the solar has just become a new frontier of accumulation and actually enclosing different kind of common resources. And for the more kind of specific example is, I'm an advocate of energy autonomy, of actually figuring out kind of localized circumstances, of actually how to actually power things individually as a neighborhood or as a block, how you can actually use recycled carburetors to kind of use the resources that already exist and to actually literally take back your power so you know how much you're really consuming and what you're really doing. But we're far way off from that. We've been rather dependent, addicted, and kind of lazy. We've become house cats in terms of how we actually relate to energy. And I think could be a fun struggle to actually try to undo. But again, we're at a point where it's being made illegal to repair cell phones and have different parts and things like this. So things are not looking good.
So I think time is running out, but last question there,
Yes.
This was my question as well in terms of, how much do you think about where the metals and the materials that you're building, where does it come from? Of course, it doesn't matter at the lab scale, but if you really want to scale up and change the world.
Yes, and that is of course an issue. So what is there are programs with trying to replace like noble metals that there's little of with more abundant metals. So we now work with copper. We think we can do the same with iron. And it's a matter of understanding the process first, and then seeing what are the properties you need of the site that is actually active for the reaction, and then you can build it with other elements afterwards. So yeah, that's clearly in part of the picture. Yes.
Final question. Yeah.
Okay. Yes. So. After hearing your talk, Alexander, what I think, from my optics, what this is a symptom of, is that we are gravitating toward energy, let's say energy resources, where the energy efficiency drops. So historically, we've gone from, let's say, you talk about this energy, what's it called? Yes, so historically we've used energy resources with a low yield. So if you put in 1 joule of work, you get out maybe 2 or 3 joules of energy from that. And then we found oil, and that has maybe 1 joule in, and we get 60 joules out, okay? And now we're instead going in the opposite direction. We're going back again, and we're now looking at wind and solar, where we put 1 joule in, and we get maybe 10 or 12 joules out again. And the natural result of that is that you need more minerals. So what is then your opinion on nuclear energy, for instance? So because that is
in 20 seconds.
No, I can do this simply. I mean, part of my problem with the kind of rare earth minerals is that they generate nuclear waste. It generates thorium. It generates really kind of gross stuff. I mean, in terms of the maintenance of nuclear facilities, in terms of the realities of mining uranium, I mean, the United States has a particularly, but this is older, has a particularly crazy history of mixing nuclear development with a genocidal program against Native North Americans, which then built bombs and different things like this. But I don't see nuclear as being viable for the infrastructures, the costs, and all. But really, again, there's always this forgetting of how they're actually mining uranium, and I imagine that there's been kind of new progress on this and also getting rid of nuclear waste. But I am going in the other direction of how we can consume less and really actually question the lifestyles that we have and actually how happy we really are. And there's plenty of statistics of depression, suicide, pharmaceuticals, and things like this that I think there is need for a social transformation in terms of actually coming to terms with how we're living. So I'm going the other direction than nuclear. But I can understand the appeal.
I would like to comment that, but
if it's very short, then we will continue afterwards, because I think we have to round off this session now. So give a big hand to the 3 presenters here.
Yeah.
I think we've been given a lot of food for thought here and things that we can keep discussing. And we'll have a break now, but this is not the end of it, because at 4:15, the student pitching will start here. That will be fun, I guarantee you. And after that, you'll even get some more food. But thanks to the speakers. Here you go. to do this and put their research on the line here. They have a maximum of 5 minutes, and after 5 minutes I will stop them. Then it's the next student. You, the audience, decide. So you have a Mentimeter, which will put up at the end of this, and then you vote and decide which one, who gets the prize. And the prize is Interrail tickets. So it's a nice prize. We did this 2 years ago, and the winner then has still not been able to go on the train trip. So it's actually a very cheap way to make a nice prize, but hopefully it's possible to do it next year. We hope so. Things must improve, I guess. So then I hope we have everyone inside then. Then I think we'll just start and do this as smoothly as possible. So I'll just briefly introduce you with name, and then you just get going. So first one out is Magnus from Department of Geosciences. Go ahead, Magnus.
Thank you. So I'm a PhD candidate with the Norwegian CCS Research Center. So I'll try to show one example how we use experimental rock mechanics to help determine some safe operational guidelines during CO2 injection. So we've seen the background for CCS in Norway by Rikke earlier today. We know the importance of the cap rock above these reservoirs in preventing the buoyant upward migration of CO2. There are several mechanical changes happening when we inject CO2. Here we'll focus on the pore pressure change. So an increased pore pressure could give stress changes that could promote fracturing or reactivating faults already present in the rock. So these could all provide some possible leakage way for CO2. So we need to determine some operational limits in terms of how much pore pressure we can tolerate. So in my PhD, I'm looking at the mechanics of a typical North Sea cap rock. We have several meters of this Straupner shale in the laboratory, so we can do mechanical testing. It's been sampled from 2.5 kilometers depth. So when we open this in the lab, we see that it's a combination of intact and fractured material. So we need to determine the strength of both intact and fractured material. So experimentally, we do this on the fractured material in the shear box. So we can test a fractured sample, apply some normal load, and then measure the resistance to shear. For the intact part, we use the triaxial test device. We insert a small cylindrical rock sample and then expose it to a horizontal and vertical stress that's relevant for the field case, and then we measure the strength. So quickly, some typical results we get. These are from the shear box testing on fractured material. So we have the blue curves showing the normal stress, so that's acting perpendicular to the direction of the fracture plane. And then we have the black curves, which are the recorded shear stresses we measure during shear mobilization. For the intact rock, we get these results from triaxial testing. So we see that the strength goes up with consolidation stress. Here to the left, we have vertical samples. They have an axis that's perpendicular to the horizontal layering in the rock. And to the right, we have the same for horizontal samples. So if we take these results one step further, we can get friction and cohesion from these plots of shear stress versus normal stress. So those are both very important strength parameters. So here we have the red curve indicating the intact strength and the green curve indicating the fractured rock strength. These circles are more circles representing the in situ stress state, so the stress in the field at depth. If we increase the pore pressure, we can imagine pushing this stress state to the left. So this new stress state, if it intercepts with the failure line, we can imagine that failure will occur. So back to our results, we see that we are far away from the strength of the intact material in terms of our in situ stress at the location. But the green and blue curves are closer to the in situ stress. We could say that the likelihood of inducing fracturing of already pre-existing faults are more likely than fracturing the intact material. We can also quantify this pore pressure change that is needed to push the stress state into a critical state. So having said that, we're not here discussing what happens if we remobilize a pre-existing fracture plane. So this is one simple example showing how we can use experimental rock mechanics in a CCS context. there are several factors that add complexity to this study. We have the orientation of the fault. That's very important. Important in terms of or how it relates to the in situ principal stress directions. We have anisotropy of the material, so different properties in different directions. We can have quite complex stress path with a fully coupled total stress pore pressure relationship. And then, of course, we have some uncertainties related to the experiment, some bias that we also need to consider. So with that, I thank the NCCS and its partners for funding and you for still staying here. Thanks.
Thank you, Magnus. Great. So we're off to a good start. I can take that. I'll wash it. And then you can take off the microphone. And then the next one can get ready.
So
that should be Yngve, right?
Yeah.
So
already now, I just want to warn you that it's going to be a change in topic from this to social sciences and feminism. So hopefully that's okay. So my name is Yngve Bråten, and I'm going to present to you my master thesis in human geography at the University of Oslo. And I'm going to start my presentation by introducing to you 4 words. So pay close attention: climate change, urban green transformations, disability, and post-structural feminism. And my objective is that by the end of this presentation, you'll see the important connections between these terms and words, and that you've had learned something new, although it's quite late. So starting with climate change, we know that climate change is posing severe risks towards societies and ecosystems all over the world. And we know that we need to take urgent climate action to combat climate change. But how do we do this? So today we see that there's an increasing number of cities around the world that are designing and implementing so-called urban green transformations. And these transformations are there to help the cities reduce their greenhouse gas emissions, but also to make the cities themselves more climate robust and climate resilient. But the question is, how can we ensure that these urban green transformations are socially just? And how can we ensure that these urban green transformations do not reproduce or produce social inequalities? So that's the topic that I'm investigating in my thesis. And I'm bringing this topic with me to Oslo and into Oslo's climate strategy, which has a very ambitious overarching goal of reducing Oslo's direct greenhouse gas emissions by 95% by 2030. So this is an ambitious green transformation. But the question is it socially just? And this is what I wanted to figure out. So what I did is that I looked at whether or not Oslo's green transformation is inclusive towards the everyday lived opportunities and challenges of disabled people. So to limit the scope of my study, what I did is that I looked at 2 climate interventions. The first one is car-free city life, and the second one is use of public transportation. And I talked with people that are blind or using wheelchairs, and I talked with them about their experiences with Oslo's green transformation. And this is where post-structural feminist theories come into play, and I'm sure that all of you are familiar with post-structural feminist theories. If not, I'm going to spare you the details, but I used this theory to investigate the extent to which Oslo's green transformation is producing or reinforcing disabling barriers. And these are, as you can see, circumstances and conditions that are preventing disabled people from being part of societies, essentially. I was looking at 2 barriers, social barriers, which are discriminatory attitudes and practices towards people with disabilities. And I looked at physical barriers that are barriers in the built environment, for instance, gaps, ramps, etc. And more than analyzing whether or not Oslo's green transformation is producing these barriers, I wanted to know what are the consequences then of these barriers in the lives of my informants. I don't have time to talk about these barriers in great detail, but what I can say is, yes, Oslo is producing and reinforcing disabling barriers in its green transformation. Excuse me. Some examples are found at the bus stop, on the bus, in relation to parking spaces, in relation to the removal of parking spaces, in relation to changing driving patterns, and in relation to the use of taxis. A lot of disabling barriers. What then are the consequences? A lot of my informants state that they don't have the same access to Oslo city center as before. Some of them don't have access at all. And this is quite dramatic. Other people state that it's so time and energy consuming to use public transportation that they've stopped using public transportation totally. As one of my informants said, I've broken up with the bus. I don't have the time, I don't have the energy. It's not for me, I'm excluded. Another person said that not only is it practical challenging to use public transportation, but it triggers strong emotional responses. He said, I get anxiety every time I'm on the way to the bus. And this is because he don't know whether or not he has access to the bus or not. Will he be left behind or not? It's really stressful. And quite ironically, a lot of my informants state that we are forced into polluting modes of traveling because we don't have access to climate-friendly transportation, which is ironic given the ambition to Oslo and its green transformation. So what? Hopefully by now, after 4 minutes, you see the important connection between climate change, green transformations, disability, and post-structural feminism. And I want to end by saying that, of course, we need ambitious green transformation, no question about it. But if you ask me, they need to be socially just and socially inclusive. Thank you very much.
And on time. And if you're here for the tapas, people can ask about the post-structural feminism there. Then next one is Nora. You have the clicker here.
Tack.
And I'll give you the slides as well. So you can see we have a good mix. That's actually us. There.
Yeah. Thank you. So I'm Nora Holden, and I'm a quite new PhD candidate at the Department of Geosciences. So we're back to talking about geology. So I'll be talking about storing CO2 in a field that we call Aurora. And I'm also part of this NCCS, or Norwegian CCS Research Center. So CCS is not a new technology in Norway. We've actually been capturing and storing CO2 for 25 years in two fields that we call Sleipner and Snøhvit. In two new and recent reports by IPCC and IEA, they state that CCS is a technology that we need to meet our climate targets. And therefore, Norway is now planning the first full-chain, open-sourced and cross-boundary CCS operations in just a few years. And the plan is to store CO2 in Breivik, transport it to Øygarden, and down into the North Sea and the subsurface in geological formations. And that's why geology is important when it comes to CCS. So in this figure, you see Aurora, which is the current target for CO2 injection, and it's in this blue outline in the figure. It's located just south of the Troll fields, which some of you might have heard of, and west of Bergen. And in the middle of Aurora, you see this well 3157, which will be used as a CO2 injector. In addition, you have these long black lines in the figure, and these are faults or fractures that offset the storage complex or the storage of CO2. So the PhD project aim is then to assess how these faults will influence migration of CO2. And the way we do this is to use seismic data to visualize the faults and interpret them, and then assess whether the faults create either barriers to fluid migration or allow it to migrate across them. And we use two methods that we call juxtaposition assessment or membrane seal assessment. And then we can use our results to discuss likely migration routes of injected CO2. So this is what the storage for CO2 looks like in seismic. To the left here, you have a seismic cross-section. The top represents the seabed, and then you have the storage approximately 2.5 kilometers below the seabed. So from the figure, we see that it's dipping towards the south, and therefore, because CO2 is buoyant, we would expect it to migrate northward and encounter the faults to the north. In these figures to the right here, you see the storage seen from above. And in this figure here, which is mostly gray, these black lines represent these faults or fractures. So we want to know how they will influence migration of CO2. So just to jump into some of our takeaway messages or conclusions, Aurora is faulted, and these faults will likely influence migration of CO2. You can see a more detailed explanation to which faults will influence migration in the two figures to the right. You also have these structural traps that will trap CO2, and it will contribute to the overall storage capacity of Aurora. So while we think that faults can have an overall positive contribution to storage in Aurora, there are still always uncertainties when you work with seismic data, and therefore monitoring is an important aspect of CCS, or storing CO2 in Aurora. So finally, just to mention some upcoming projects. 1 minute left. Yeah, thank you. We want to have a closer look at faults than what we can see in the seismic. So we're traveling to Utah next autumn to look at outcrops that provide analogs to faults that we see in seismic in the North Sea. And because faults are actually complex zones of deformed rock that can be really challenging to see in seismic data, we want to see if we can apply new machine learning techniques to help us interpret these complex geometries in the faults. So that's it for my short presentation. Thank you, and thank you to the NCCS partners.
So then the next one is Johanne. I'll start that and this one.
Thank you.
It's yours.
Right, so my name is Johanna, and I will be presenting my master's thesis that I'm currently working on. By complexity of climate change in this title, I'm referring to the challenges of finding possible solutions to the climate crisis. Because the social reality of the climate change problems is very different depending on where in the world you are. And my master project is a research project on the municipality where I grew up, which is Aurskog-Høland. And through semi-structured interviews, I will ask about their perceptions, feelings, thoughts, and behavior in relation to the climate change issue. And with this thesis, I hope to contribute to finding ways of facilitating transitions to more sustainable society that everyone can get behind. To do this, it is necessary to understand the different social contexts that people live in, and this is something that I will focus on in my project. And so I ask, how are perceptions of the climate crisis influenced by social context? This model is from Karen O'Brien, and she calls it the 3 spheres of transformation. And it illustrates a way to separate different aspects of society into the practical, political, and personal sphere. And the practical is more concrete and has to do with actions and technical solutions. And going out to the personal sphere, it's more abstract and has to do with people's beliefs and values. And these 3 spheres are interrelated. So the personal sphere influences the political, which then again influences the practical. And changes in either sphere can cause changes in the others. Another way to separate the different aspects of society is by dividing it into micro, meso, and macro level structures. And the macro level structures are more about the individual and social relationships, while the macro is at the larger structural level. And in my research question, what are people's perceptions of the climate crisis in Aurskog-Høland? This mostly, first relates to the personal sphere, as it is about people's beliefs, but it still has to do with the other spheres, and the other spheres also influence the answers of my informants. And the same with micro It's at the macro level, but it still is influenced by the meso and macro level as well. And so this picture, I think, is a good illustration of this way of thinking. It's from Bjørklangen, which is the municipality center. And to the right in the picture, you see a red farmhouse. This represents the old agricultural culture in Aurskog-Høland. And to the left in the picture, you see the newer housing estates that are more densely populated, and this is a centralization process that is going on in the municipality. And this process can be related to climate change because this centralization process is actually creating even longer distances for people living in other places in Aurskog-Høland and making them even more car dependent. And additionally, my informants that I've in my interviews so far have talked about the fact that they think that this centralization process and also the most of the typical climate change mitigation measures are sort of outside of their control and come more from the regional and national level of government. And then I have another example. I don't know if I have time for the whole thing, but it is about how our ability to contribute to change within different social roles is very different for different people. So some might find it easier to contribute in their work or in their social relationships, some in the sharing of ideas with others, some in relation to transportation, some in consumption, and some in political activity. So I hope that by getting a deep understanding of the social reality of this group, that this can contribute to finding doable solutions for achieving transitions in specific contexts.
Okay, so next one is let's see. Masi?
Yes,
that's right. So I'll give just
thank you.
one.
Yes.
And you can just go ahead. It's yours.
Okay. Hi everybody, my name is Masi. I'm at the Department of Physics at the University of Oslo, and I would like to talk about my PhD topic, which is synergy of liquid hydrogen and superconductivity. Nowadays, especially in Norway, we have heard a lot about hydrogen as a sustainable energy, and it becomes more and more famous. But what is the reason? So first of all, water is the only byproduct of hydrogen consumption. So it means that the hydrogen is the carbon-free source of energy. And also the excess of electricity can be saved in form of hydrogen rather in batteries. And also we can find the source of hydrogen almost in every country. And it's not exclusive for only few countries like fossil fuels. And hydrogen has the highest specific energy density in terms of energy per mass. But in contrast, it has a very low volumetric energy density in terms of energy per volume. So to compensate this problem, it is possible to provide hydrogen in liquid form. So liquid hydrogen has higher energy density in terms of energy per volume. It is about 800 times more than hydrogen in gas form in normal condition. It also occupies less volume, which is quite good for distribution. And at the end, liquid hydrogen has a very low boiling point, which allows us to synergize it with superconductivity. But what is superconductivity? Well, the electrical resistivity of some material could reach zero at very low temperature. It means that we can pass electricity among these superconductors with almost 100 efficiency. This phenomena is called superconductivity, and it has a wide range of applications, but I only addressed two of them: distribution of electricity and transportation. Hopefully, the critical temperature of some these superconductors is above the boiling temperature of liquid hydrogen. So it means that we can use them at the same time. But how? How can we combine them, and how can they be used at the same time? So maybe the pipeline is the simplest example. Imagine we made a pipeline with superconductors, so the liquid hydrogen can pass inside this pipeline. So at the same time, this liquid hydrogen could cool the pipeline. So the electricity can pass through this pipeline without any resistivity. So first, the liquid hydrogen can pass inside, and second, the electricity can pass through the pipeline. But is it all? Definitely not. We can still take advantage from this simple pipeline. Actually, this pipeline in superconducting situation, it could create high magnetic field, which is enough to levitate a heavy train. So it means that this pipeline could be used as a railway for a magnetic levitation train. And by eliminating the friction between the train and railway, we can save considerable amount of energy.
1 minute left.
Yes. But this is a simple pipeline. What if it is expanded, and what if it is used for a whole city or a country? So it is interesting. There are many kinds of sustainable energy. They are all good, but the problem is that it's not easy to store the excess electricity obtained from this sustainable energy. But instead, we could convert the excess electricity to hydrogen or liquid hydrogen, and then distribute both liquid hydrogen and electricity to end user. So the general perspective is that to use renewable energy to produce electricity, and the excess part can provide liquid hydrogen, and this liquid hydrogen can cool the superconducting pipelines, and to provide the smart grids for us. Okay.
Thank you.
Yeah, you're welcome.
Hello. Yeah.
Yeah. So it's Kasper. Right?
Yes.
Go ahead.
Thank you. I'm Kasper. I'm a master student at the Department of Chemistry. I'm a part of the NAFUMA group, and I work with batteries. And more specifically, I work with sodium-ion batteries. And this is the material I work with, which is called bismuth ferrite. Probably none of you have heard about this before. And also, like, why do we want to use sodium-ion batteries? We have lithium-ion batteries, which are great, but the world's resources are finite, so we need to be clever with how we use the materials. As you see in this pie chart, you see here that lithium is only 0.002% of the Earth's crust. And sodium is 2.35%, which then means you have a lot more of sodium that we can use. And also, sodium is from all over the world, The lithium we use in the batteries today are mostly from this area in South America. And to ship lithium all over the world from South America is not very eco-friendly. And also, if there were to be anything crucial to happen in this area, the whole world would then lose all transport of lithium. So, sodium-ion batteries, what is it? I guess many of you have heard how a battery works, and you have an anode and a cathode, and they are connected with an outer circuit, and between them you have a electrolyte and a separator. So, if you have a sodium-ion batteries, then it means when you discharge the battery, you get electricity out. The light bulb starts to glow. The electrons move then from the anode to the cathode, but also you have sodium ions moving from the anode to the cathode through the electrolyte. And when you charge the battery, you want to keep the power in the battery, you want to store it. Then you plug it in and you reverse the whole equation. Electrons go from the cathode to the anode, and sodium ions go from the cathode to the anode. But if this is this exact same way as lithium-ion batteries work, why can't we just use the same technology today and just replace the lithium with sodium? Well, in a lithium-ion battery, you have graphite anodes, which means you have an intercalation process, which means you store lithium between these graphite layers. And these are just carbon. But if you were to use sodium instead of lithium, you stumble across a problem. Sodium is too big. It's too fat to fit in between these layers. So, what do we do then? Certainly we cannot use graphite as an anode. And this is where I come in. My work is with bismuth ferrite. This is the structure of bismuth ferrite, and it doesn't look like this at all. So what do we do? Well, we do a conversion reaction where you let sodium react with this structure, and the bismuth and the iron are split up, and you get this nice structure, bismuth. But what do we use this bismuth to? Well, now I present to you sodium bismuth. And this is where we store our sodium. Instead of storing them in these layers, we push sodium into this alloying reaction. An alloy you have probably heard about. So, when we charge the batteries and discharge, they go from sodium and bismuth to sodium bismuth and back. Thank you so much for the attention.
Hello, you can hear me? Good. My name is Karen Hjelmvik Nærbø. I don't have a fancy presentation. There are no animations, I'm sorry, but hopefully we can find it anyway. So I am a PhD fellow at the Department of Public and International Law, and I'm doing my PhD project on prior assessment, thank you, of long-term and cumulative environmental effects of decisions. So first, I have collected a few environmental goals here for you, and I'm sure you're familiar with them. The first one is from the Glasgow Climate Pact, reaffirming the 1.5 degree goal. The second one is Norway's emission reduction target, stating that by 2050 we should have reduced our greenhouse gas emissions by 90 to 95%. And the bottom one is more energy related. It's from the EU Directive on Renewable Energy, stating that the energy consumption of the European Union as a whole should, at least 32% should come from renewable energy sources. So what do these environmental targets have in common? So for one thing, they have long-term perspectives, so they have a longer time frame, and their attainment is also dependent upon several smaller decisions, right? So what I take from this is that we need knowledge about the long-term environmental effects and the cumulative environmental effects of the decisions that we make in order to reach our environmental goals. And that is why I'm doing research on environmental impact assessments, or EIAs. And EIAs are a procedure to assess the environmental consequences of a decision before the decision is made. And they have at least two intentions. So the first one is a democratic one. So they seek to improve the decision-making process by informing decision makers. And second, they also seek to ensure that environmental consequences are taken into account when we make decisions. So my first research question is, what are the legal obligations to assess the long-term and cumulative environmental consequences of decisions in Norway? So here I'm going to use a legal doctrinal method, which basically means that I want to analyze what the law says today. What are the legal obligations today? And the thing is that most decisions are actually made in several steps. So first, we pass a law that allows for a certain type of activity, for example, wind turbines at sea. And then we pass more regulations with more detailed rules on this activity. And then finally, we decide on the specific projects in administrative decisions. And this regulatory system here also affects how we do impact assessment. So we actually do impact assessment at all of the stages of the decision-making process, but we mostly do it before the administrative decisions. So I want to understand more about what information we get at the different stages of the decision-making process. And I also have another research question, which is a more practical one, and that is, how are long-term and cumulative environmental consequences of decisions assessed in practice in select cases? And here I want to use an empirical method to study how we actually do assess the consequences of our decisions. And I want to look at all the stages of the decision-making process to see when do we get the information about long-term environmental consequences? When do we get the information about the cumulative environmental consequences? And when do we need them in this process? When are they most important?
1 minute left.
Yeah. So I think that was everything, actually. Yeah, thank you. That's it.
Thank you. Yeah.
Okay, thank you. So my name is Lynn, and I'm here to talk about materials for a new paradigm in electronics. Now, I want you to think about materials as Lego bricks, and that's actually not as far away from the truth as you may think, because in reality, I work with molecules. And both of these have different shapes, different sizes, and different functions that we want to exploit in order to make the best materials possible. So one major difference, though, is that instead of making these three-dimensional, grandiose, actually even visible structures, I make something called thin films. And they're so small that if you were to try to see them, it would be like trying to spot this Lego brick from an airplane 320 meters above the ground. That's how thin they are. And a fair question to ask now is, how would you even, or how can I claim that something so small can have such a large impact in electronics? In order to understand that, we need to go back in time, way, way, way back, all the way to 1965. That's when Gordon Moore predicted that silicon would be the basic material in electronic components, and that the number of the transistors on a device would double every single year, which is known as Moore's law, as you see here. Now, 50 years later, it has worked perfectly, but the problem is that our devices and our transistors have become so small that we're running into another problem. We're actually approaching the physical limits of what's possible. That is, the physical limits of silicon. For example, in 2007, this blue layer here used to be silicon dioxide, but then we switched it out with hafnium dioxide, and the transistor could be made even smaller and more capable. And that was the most major modification that has been made to the transistor in over 4 decades. So the direction we're going in is trying to find materials that can either replace silicon or work in fundamentally different ways so that we can have more sustainable electronics that work in the same way that we use them now. And a friend of mine, she's there, said that complex problems require complex solutions. And luckily for me, I am in the field of complex oxides, so that sounds like a good solution. Now, a complex oxide just means that you have an oxygen that is accompanied by 2 other elements. And it just so happens that if those elements are a rare earth element, one of those from the bottom row, and nickel, you get something that's quite magical. You get a material that can be switched on or off. And for our purposes, that's just what a transistor is. So I'll show you how. This is a phase diagram or a map of the rare earth nickelates. And we can simplify it to just focus on the important things. What you see here in the brown area is that there are some rare earth nickelates that will be metallic, that is, they conduct electrons, they conduct current, and that represents an on state. And then there are others that are insulating, and that's an off state. So they function like a transistor. But the problem is that right now, none of them actually work at room temperature. So part of my job is to make something that lands right at that intersection point so that they're actually viable for use in daily life. And luckily, we have a trick up our sleeves. That trick is called atomic layer deposition. So very briefly, it relies on chemical surface reactions, and that enables us to use lower temperatures than other deposition techniques that just bombard atoms onto the substrates. And importantly, it's compatible with silicon dioxide, or silicon oxides in general, which means that you can implement it with a technology that already exists. But most importantly, we actually do this, or we grow these thin films layer by layer, such as this, which means that instead of ending up with this chaos or disorganized matter, you actually have a structure that works in the way you want, and you have very precise control over the thickness, so you can grow them atomically thin. And that represents a reduction in the transistor size.
1 minute left.
Great. So we're envisioning a complete oxide transistor where, for example, the materials I'm looking at could be used to decrease the dimensions of this channel. And that not only makes it smaller, it also improves the performance by saving energy and also being faster at the same time, which is great. Now, my master's project lands in the realm of, or in the realm between fundamental research and application. So what I'm really trying to do is just bridge this and show that we can do research that is feasible for electronics and that can actually change that the way we use them. And of course, this is still a work in project. So in June 2022, hopefully, I'll be able to open my bridge. And if it's successful, maybe I can call myself a Lego master. Thank you.
Thank you. And then final entry. See, Mohammed, there you go. And the floor is yours.
Hello, I'm Mohammed from Department of Geosciences, and I'm gonna talk about salt aggregation during CO2 storage. We might know about global warming and its fatal consequences. We also know that greenhouse gases are the main cause of global warming. And among these greenhouse gases, CO2 accounts for 76% of the global emission. And most of this CO2 comes from energy sector, and we need energy. So what should we do? Here comes CCS, which is a technology that captures CO2 from its major resources, like power plants, transfer it, and store it permanently under the ground. So CO2 is supposed to play a big role in meeting the climate targets. But it should be implemented in a very large scale at many storage sites with high injection rates. There are several options for CO2 storage. And for all the options, CO2 needs to go all the way through the well and its near wellbore area to go into the reservoir. So this area is a gate and a door to the reservoir. Something that happens here is when CO2 is going to push that super salty water here, some of the water molecules evaporates into the CO2 stream. That makes this super salty water more and more salty until we reach to the point that this salt forms and close our beloved path. So to make it more simple, there's a road there, and we better keep this road open. And in order to understand how to do that, we need to know the physics behind salt formation, and we need to be able to model it. Therefore, in 2015, our team revealed that there are two types of salt formation during CO2 storage. One, big crystals that in the liquid phase, and the aggregates of small crystals in the gas phase. And all of the previous research are about these big crystals, and nobody tried to model the behavior of these small salt crystals, which at the moment there are several experimental and field evidences about that. Therefore, we developed a model to do that. Here is a video of how the salt accumulates there. Now, remember that there is two types of salt formation, and different things close the road in a different way. And in my field, the way that solid phase closes the porous media is formalized by something called clogging models. Now, the question is, can the widely used clogging models capture aggregates behavior? And the answer is here, and the answer is no, because the physics behind all the widely used clogging models that are being used in the commercial softwares, and which shows that we need more research to be able to develop a proper clogging model for 1 minute left. Yes, for this kind of clogging behavior. Thank you so much.
And thank you. That was fun, right? That's a lot of science in about 1 hour. And if you didn't learn something new during this round, then I don't believe you, basically. I think those saying that, people at the university are not very good at communicating, they haven't been here. This was excellent. I really, really enjoyed it. And of course, now comes the difficult part. Because now you have to bring out your mobile phones, and we'll check if they can be repaired, right, Maya? No, bring them up, and we will start this Mentimeter thing. Let's see. There. So we have to go to menti.com and use this long code 99339729, and you have to make a decision. Who should you vote for? And then if you ask, what should be the criteria here? It's kind of up to you. But of course, the research is one thing, but the communication skills is what. Yeah.
Could the people stand below the bar so I know who's who?
Yeah. We can just come up. We're missing Magnus because he had to leave, but if you then switch around, so we get Yngve on the right side. Yes. So you have, I'll present you. We have Yngve, Nora, Johanne, Mazi, Kasper, Karen, Lynn, and Mohammed. And of course, you all remember what they talked about, right? Okay, so keep voting. And we'll see, we have 25 votes, 27. I'll give you another minute or so, 28, 29. $32. And if there should be a draw, we haven't really talked about what we'll do then, but well, we'll see. So, anyone who hasn't voted yet? No? 33 votes. 3, 2, 1. No, nothing happened. Interesting.
Maybe click on the results.
Ah, results are hidden. That's just
You need to press H, I think.
okay, H. And then, ta-da! Lynn! Woo! So, you'll all get chocolate, which is really, really deserved. So, up, up, yeah. So there you go, there, and then we have an extra prize for the winner, I think. Yeah, it hasn't been unwrapped actually, but we'll do that very, very quickly. And as I said, the main prize is a set of Interrail tickets. So we hope it's possible to travel this summer and that you can use this in a nice way, going somewhere that's also useful for your research. But you'll get this one. It claims to be environmentally friendly grown. No idea what that means, but I had to pick that one then. So congratulations. And Øystein, are you here somewhere? No? Yeah? He went out. Yeah, because we would like some pictures of everyone here. Yeah, give them a big round of applause. Very good. Let's see if we can get the camera quickly, but I think food should be ready outside. So you're free to head out, except you, because you have to stand there a little bit longer. Men for han har ikke satt igjen deilig. Okay, let's do this just with my camera. See, smile. Let's take a few. Okay, very good, then you're free to go. Thanks again. So, tapas, something to drink as well outside, and you can just hang around for pretty much as long as you want.